The particular aspects or peculiarity of the lifetime data is incomplete observations. There are various reasons for this incomplete observation. If you look at this particular example, which is a study on malignant melanoma data in Denmark, we conduct that study, then observation on 255 patients are made from 1962 to 1977. Individuals alive at the end of 1977 were considered to be censored because these individuals are still surviving, and we do not know exact failure time or death time of these individuals. Then various types of censoring are there. Right censoring, there's a particular case is, the above case is the right censoring, which includes the type 1 and type 2 censoring, and another one is left censoring, interval censoring, double censoring, middle censoring, etc. What I'm going to focus here is on a particular type of censoring or interval censoring, case 1, which is also referred to as current status censoring. The peculiarity of this censoring is very informative. That is, we do not actually observe the lifetime continuously. The only available information on lifetime T is whether the lifetime T exceeds a random independent monitoring time U. That means each subject in a study is observed only once at a random monitoring time, and only the information whether the event of interest, that is the failure or relapse or death, has occurred or not prior to the monitoring time available. That is, we do not have the exact lifetime. What we have is, we have another random variable which is denoted by U, referred as monitoring time. Then each subject is observed only once at a random monitoring time. And the information about the failure is the following. That is, the event of interest that occurred or not prior to the monitoring time. If it is occurred, we can say that one individual or one subject has failed. Otherwise, it is still surviving. Then there are various examples. One example is breastfeeding data from Pakistan Fertility Survey. This is a big study, and they collected the current status information whether a child is still breastfeeding or not at the time of survey, along with age of child, which is a covariate for 3,350 children. Another one is wheel cracking data, which is given in Lawless book, and which was earlier considered by Nelson 1982 and Meeker and Escobar 1998. The data from a study on the time to appearance of crack in a metal turbine wheels, where they have collected 432 wheels and they determined whether a crack had appeared yet or not. I am giving a sample of this data set, and this is inspection time. We have the monitoring time or inspection time at 4 hours, 10 hours, 14 hours, 18 hours, like that. Then number of wheels observed at 4 hours is 39 observed. Out of 39, number of wheels cracked is 0, and number of wheels not cracked is 39. Then if you look at the monitoring time 10, total number of wheels observed is 53. Out of 53, 4 cracked and 49 still surviving. So the next case 14, they have observed 33, then 2 cracked and 31 survived, and like that. So total 432 wheels were observed at a different monitoring time. We do not know exact lifetime of those wheels. So actually, we have the information that the first set, that is 39, were survived after the monitoring time 4 hours. We are not going to observe those 39 later. We are going to observe only the rest of the 432 wheels. This can be naturally arise in the study of infectious diseases, where the individual can be observed only once. For example, HIV infection study, one can refer these papers. Then structure of the current status data is each subject is observed only once at a single random monitoring time. Then actual lifetime T remain unobserved. We have a random variable U, which is a non-negative random variable. In addition to U, we have some information on patients or subject that is usually referred as covariate. So we observe the vector U, delta and X. What we mean by delta is the indicator which takes the value if the subject is lapsed or failed before the monitoring time U and 0 otherwise. So the sample data will be UI, delta I, Xi. This is up. Then generally the monitoring time is independent of this lifetime T, and monitoring time U has the distribution function G. It may be noted that the monitoring time of all subjects need not be distinct. A group of individuals can be observed at the same time as we saw earlier. The common question is how to get the information about the lifetime of T, F. So often the interest is focused on estimation of F. In many cases, the relationship between F and a set of covariate X may be of primary concerns. Some others study the parametric form of F, but most of them deal with the non-parametric method. In the case of covariate, regression models are popular. Semi-parametric regression models are commonly used in such a context. So estimation of distribution function F, the simple method is delta is given by indicator function T less than or equal to U, and we have some nice representation using the expectation. Expectation of delta will be given U is nothing but the distribution function F. So one can use this information or this expectation, corresponding empirical value of the expectation. You can get the idea about the or information or estimate about the distribution function FU. But the problem here is that this FU should be should satisfy the monotonicity constraints. That is, the property of F is it is always non-decreasing. Then the popular method is use the likelihood. That is, the likelihood can return in terms of F or calculated at UI, because we have the information only UI and delta I. When the covariate is absent, you can write the L in terms of F of UI delta I and 1 minus F of UI into 1 minus delta I. Then this can be given in this form. Delta is replaced by this quantity Rj. They are the number of subjects who are observed at Uj, and the Nj total number of subjects who are observed at Uj. So then what we have obtained here is you have likelihood function in terms of F. And if you assume any particular parametric form for that F, for example, if F is the exponential distribution, you can put that exponential model here, and you can use the maximal likelihood method to estimate the parameters of the density function or the likelihood function. Then this expectation, but the problem, as mentioned earlier, when you consider this a non-parametric setup, then this likelihood is nothing but this is a arising in a M sample binomial setting. So L depends on F only through its values at UI, and then the maximization of that L is equivalent to minimization of this quadratic function. Then there are various methods for finding this F. One popular method is this one, that is using pooling adjacent Violate's algorithm. We have the estimate for F, which is given by this formula. That is that. This is referred as NAIME estimator of it. So this is important. Then we have some properties. I am not going to discuss these properties. The limiting distribution of this F hat is not Gaussian, but a more complex distribution associated with the two-sided Brownian motion, and this is a Chernow distribution. And they have these people, they have considered this Chernow distribution, and finally they could prove that this is a limiting distribution of this distribution is like normal distribution with this particular mean and variance. Then coming to the regression models, we have some additional information. Then there are various methods for the regression model. I'm going to consider the popular one is proportional hazards model. In terms of cumulative hazard function, most commonly used regression model is capital lambda t given z is lambda naught into expectation of z prime beta. Then consider the earlier likelihood, that is in terms of product I equal to 1 to n f of ui raised to delta I into 1 minus f of ui raised to 1 minus delta I. You substitute this value, this capital delta, you can represent in terms of the survival function, and you can write the likelihood in terms of this capital lambda naught and beta, and your likelihood will be in this fashion. Then to estimate the maximal, estimate the parameters of beta, what we do is we have to assume that the distribution of the baseline quantity, this S0, that is of the form some exponential part, that is piecewise exponential model, and we have representation of S0t in terms of alpha. And once you know these alphas or estimate these alphas, then you can get S0t. From there, you can estimate, substitute those values, and then you can estimate beta. That is the idea. So the likelihood can be replaced in terms of alpha and beta, and then log likelihood function can be obtained in terms of alpha and beta. And finally, these estimates can be obtained by maximizing this log likelihood function. Sometimes it's not very easy, and we have to use numerical method for finding these estimates. That is the idea. Then topics in current status which are being studied extensively are bivariate current status data, current status data with the competing risk outcome, doubly censored current status data with masked cause of failure, and current status data with the QR models. And bivariate current status data, this Prof. Jewel has done some work on that, and current status data with the competing risk, Matthias, they have done some work, and myself and Sridevi, we have done some work, and the doubly censored current status data, we have done some little work, and current status data with masked cause of failure, I think Professor Anup Divanji is doing some work on this direction. And current status data with the QR model, this topic is not completely discussed in literature. We are focusing on this topic right now.
Shankaran, just a reminder, you just about 10 minutes more.
Now coming to the competing risk refers to observation in which a subject is exposed to two more or causes of failures. And we have fundamental quantities, that is cause-specific hazard function, lambda jt, cause-specific subdistribution function, fjt, and cause-specific survival function, sjt. Our objective here is to estimate these quantities, one of these quantities, they are related. So one of the quantities using the data available here. So this competing risk data was extensively studied by many authors. This is Porta et al. 2007, Carrier and Kochar 2000. Kochar has done many works on that. Diwan and Nimbalkar, they have also done some work on that. Then current status data with the competing risk. One particular example is the menopausal history of 2,423 women, which is obtained from National Center for Health Statistics survey, which was analyzed in another contest by McMahon and Horstar. Then these four, each subject whom experienced menopause, type of menopause is categorized into two, operative and natural. That this is the data. And at the age 27.5, respondents 380, and operative menopause 4, and still menstruing 376. Like we have data. Then here, what the likelihood can be also written in this case using cause-specific subdistribution function, that is the Fj and 1 minus F. F is nothing but summation Fj. Likelihood can be written in terms of this. Here the delta ij is nothing but delta. In the earlier case, we have only delta I because I indicator function t less than or equal to ui. Here you have indicator function t less than or equal to ui, and the cause of the failure is ci equal to j. This is so you can find the log likelihood function, and this can be maximized and subject to the constraint that total sum of fj less than or equal to 1. And there are various estimator. One estimator which is actually extension of the earlier one, fj hat is the maximum of minimum summation dlj divided by summation nl, where lj is the number of subject failed before this particular monitoring time, given that these are failed due to cost j. Okay. Then these are some advantages of this one. Then split the estimation into now. And they have proved these two papers. They have proved the limiting distribution of NAIME estimator, and again they have proved that this is a Chernoff distribution and consistent with the rate of convergence. Then there is another paper by Matthijs and Hudens considered two more different models of current stat data, in which observation times are x but with the discrete support, and observation times are grouped. And they have also proved asymptotic properties of estimators and derived the confidence intervals. I'm not going to. Now these current status data with the competing risk and covariate. This is an example, clinical trials to determine the efficacy of vaccine against HIV. Then participants in a trial is available for follow-up only once current status censoring. HIV virus can be distinguished into several subtypes, and simultaneously infection with several subtypes is very rare. So here also data on menopausal history of 2,423 women used for illustration. Here we have an additional information, the covariate, that is xi, ui, delta I, ci, that is the cause, and xi is the covariate. Then one can consider the regression model in terms of sub-survival function as defined earlier, that is xj is s naught j raised to e to the power of beta j xr. Then we can write the likelihood in terms of lj, where lj can be represented in terms of sj. That you can see here, lj can be represented in terms of sj. Then estimation of this can be represented using the maximal likelihood method. The maximization of L is equivalent to the maximization of Lj. So one can maximize Lj as before. This is we have done this work and use the log likelihood and equation 6 and maximize using Newton-Raph's method. And we have proved that this is the estimators are consistent, and we have investigated the rate of conversion and finally proved that they are asymptotically normal. Then second problem here is the testing problem. Testing whether these cause-specific hazard functions or cumulative hazard functions are equal or not. Then which is equivalent to testing the cause-specific survival functions, they are equivalent or not. Then the hypothesis say it can be written in terms of S bar, where S bar is nothing but summation Sj. Here, S bar is nothing but summation Sj. then one can consider a quantity which is actually a departure of this Sj, and based on the equation 9, departure of Sj and S bar by K. If this departure is large, we reject the hypothesis. If departure is small, we can accept the hypothesis statistically. That is, we can construct a quantity Vj based on this departure, and we consider Vt, that is V1t, V2t, etc., corresponding to different causes, j equal to 1 to k, and then this Vt follows a k-variate normal distribution with a mean, zero, vector, and covariance matrix. Then the quadratic form follows chi-square distribution. So reject H0, then this quadratic, this value is greater than equal to chi-square value with the degrees of freedom k minus 1. In practice, it is very difficult to estimate sigma t, this matrix, sigma t, that variance covariance matrix for the chi-square value, and we use the bootstrap sampling method. To illustrate this procedure, we consider a prostate cancer data. 506 patients with the prostate cancer. There are 2 stages of cancer, stage 3 and stage 4. They are considered as covariate. 9 causes of death. 1 is prostate cancer, 2 is heart vascular disease, etc. And we are interested on prostate cancer, so we classified the cause into 2 categories, prostate cancer and other causes. So this is the data. Stage 3 and stage 4, prostate cancer and other causes, and alive at different points. So they are the monitoring time, observation time, they are the monitoring time, and monitored 27 at the 2.5, and 2 failed due to prostate cancer, and 25 due to other causes, etc. The other cases also, stage 4 also. Then we have used different weight functions.
Please try to wrap up in 2 minutes.
I am going to complete within 2 minutes. So these are the weight functions, and we analyze this data set to test whether the effect of 2 different causes vary with the time in the presence of covariate, and we have estimated the regression parameters beta 1 and beta 2, and then we use the test statistic to check whether there is any difference between prostate cancer and other causes for the lifetime. Then we have considered the different weight function, and finally see that in all cases, or if you consider all the weight function, they are significantly different at the 2 different stages. These are the covariate. So indication that the survival function resulting from the 2 causes, prostate cancer and other causes, are significantly different, which can be seen from this estimator of sub-survival function. This is a plot of survival. Okay, we have also considered the comparison at the different covariate values, which is also done, and finally this is also seen that in all cases these 2 causes are different in terms of covariates. Conclusion: we proposed a semi-parametric regression model using survival function for the analysis of current status committing data. The estimators of survival functions and regression parameters were derived. Asymptotic properties of the estimators were discussed. A test procedure for comparing sub-survival function of a current status committing data in the presence of covariate was developed. This model has significant importance as current status data exposed to multiple risks with covariate arise naturally from cross-section studies and in some reliability experiments. We did not consider 3 causes, but we can consider the 3 causes also. We have done extensive simulation work, which was not reported here due to time case. And we have considered the second part. In some cases, lifetimes may not be continuous, it may be decreased. And we have considered this work also, and it was published in Journal of Indian Statistical Association 2 years back. This is complete. These are some of the references in this area. We have published 4 papers in this area. Later on, it's not included. Thank you very much.
Thank you very much, Shankaran. I'm sorry, we have no time really for any questioning, but I'm sure Professor Shankaran will be happy to respond to any questions or comments sent via email. Please reach out to that, and because we have the next session coming up in a minute time. So meanwhile, we like to thank Professor Shankaran and all of you as well. Like to request everybody to unmute. A big clap to Professor Shankaran.
Okay, you can send the emails.
Okay, so Dr. Satish Kumar, are you going to say something to end the session?
Thank you, Professor Dilanji, for chairing this session, and Professor Shankaran for your nice presentation. And in fact, we are very much glad to have the concluded in time, and now we have to go to the next session. Once again, giving a big clap to the chair of this session, Professor Dilanji, and Professor P.G. Shankaran.
Okay, those who want to send some queries or any clarifications, so you can free to mail me so that I will reply. Okay. Thank you very much.
Thank you.
Very good. Very good. Now, next session is a special session on the biostatistics. We have 2 speakers and 2 invited speakers and 4 contributing speakers in that session. In fact, we have to chair this session. We have the Professor Rakesh Srivastava of MS University, Baroda. He's an expert in the area. In fact, he has more than 35 years of experience, and in fact, is the vice president of our ISPS, and he has a member of several committees, reputed committees like NAC Peer Committee, PHN Committee, UGC Sub Committee, etc. I'm very glad to invite Professor Rakesh Srivastava to chair this session and for its further proceedings. Please carry over. Thank you. Thank you.
Thank you, Satish. I hope I am audible.
Yeah, Professor. It's audible.
Thank you, Professor Bala and Satish, for giving this opportunity to chair this session. And I am very much glad to see the very first speaker is one of my great favorite, all-time favorite, Professor Anil Gorey. My association with Professor Anil Gorey goes back to almost 20 years back when we started meeting in some of the sessions of the Indian Science Congress and at many other places in the various conferences where he was very much visible, and I was also attending those sessions as a very young researcher. Professor Anil Gorey is an excellent speaker. I don't need to say anything about him, but I am very sure by the end of his talk, maybe many of you will become his fan. He was my chief guest in Baroda in one of the national conferences in biostatistics. Professor Gorey has a very huge biodata, which I don't want to waste my time on that, because I just want to say that I want to listen to him. Rather, all of us want to listen to him. But few things I wanted to mention is that Professor Gorey right now is the vice president, if I am correct, of CITEL Pune. And he has been very kind enough and very cooperative and very encouraging for the students. Very much encouraging for the statistics students to get placed in biostatistics and in CITEL. So with these few words, sir, I am very small kind of a person to introduce Anil Gorey, sir. I will not take much time once again between you and him. I just hand it over to Professor Anil Gorey for his very enlightened, I think, talk, Statistics for ODDD. Again, as usual, he has some very interesting words to put in everywhere. So I welcome you, sir, on the board for your very first lecture on the Biostatistics Session 1. Professor Anil Gorey, it is over to you, sir. Sorry, sir, just I forgot to mention one thing. You have 25 minutes of time, 25 minutes of time with 5 minutes of interaction. Thank you, sir.
We can't hear anything.
I think he needs to unmute himself.
Yeah. He needs to unmute. I think so. Professor Gorey?
Professor Gorey, you have to unmute yourself, sir. Can you hear me, sir? Sir, you have to unmute you, sir.
Yeah, there is.
Okay, I did that. Am I audible now?
Yeah. Now it is audible. Yeah.
Thank you. Let me share my slides, and Srivastava sir, when you see my slide, kindly let me know.
Sure, sir.
Can you see my slide?
Yes, sir. Yes, sir. It is visible. Can you make it full screen, sir?
Yeah, it is already made full screen. Yes.
Okay, sir. Thank you.
So, good morning, everybody. I'm very happy to join this conference and use this opportunity to share some of my activities. Let me first thank Dr. Bala and also Dr. Srivastava. Bala for inviting me and Srivastava for saying some nice things about me. So this is the title, Statistics for ODDD and Serendipity. This is joint work with my colleague, Dr. Paranjape. And I'm going to, of course, explain to you what the title is and then explain the word serendipity. Then we'll talk about obesity and dieting and diabetes. And then this thing called Dixit diet, some of you may be aware of it. And then we'll come to the statistics part, which is how to design a trial for this problem and the difficulties therein and some analysis. So that is the content of my lecture. And one request to Dr. Srivastava is, when I take 20 minutes, will you please give me an alert?
Sure, sir.
Okay, thank you. So, ODDD stands for obesity, diabetes, Dixit diet. Okay, so these are the things we are going to talk about. And then the last word is serendipity. And you can check the word serendipity in the dictionary. It is an Indian word that has entered the British language. Originally, it has something to do with Suvarnadweep, which is the old name of Sri Lanka. And there is some story about a prince of Suvarnadweep who went out looking for something, a thing A, and found thing B, and he was very happy. So when this happens, a chance event is very useful, a beneficial one, then it is called a case of serendipity. And something like that has happened in the problem or research that I'm going to talk about. And in science, there are many examples of serendipity, which means a person was looking for one thing and found something else, and that was very interesting and useful. I will give a short list. There are more. So the discovery of penicillin is a serendipity, insulin, quinine for malaria, X-ray, Teflon, microwave oven, Velcro, and so on. These are interesting stories in their own right. I don't have time for talking about all of them. I will only talk about one. And this is the story of Alexander Fleming. And people know a part of that story, but don't know the other part. So this is Mr. Fleming, who received the Nobel Prize for his discovery of penicillin. And what probably a lot of people know is that this discovery came through an accident. So he was trying to study these bacteria called Staphylococcus. And so you have to grow these bacteria. And the standard system is you take a petri dish, just piece of glass, and put some food and then inoculate it with the bacterium and then incubate it, and they grow up in large numbers. In this case, he found that there was a blue-green mold spot of it on that plate, and around it all those staphylococci had died. This is the accidental discovery, which means that his dish was contaminated. He did not have a colony of pure Staphylococci. And this is not something that happened only to Alexander Fleming. It happens all the time in microbiology laboratories. And the common thing to do is to curse your bad luck and discard that stuff. But he did not do that. And what we know is that he found there was an active principle in that fungus, and that active principle then was isolated, and the humankind received their first great curative medicine, penicillin. This was before the Second World War. Anyway, what people don't know is, why did Alexander Fleming behave differently? Unlike his other microbiology colleagues, why did he not discard those petri dishes? Because there had been a previous accidental event, and that was with his own tears. So what happened was that he shed a tear into a bacterial sample, and where that tear fell, bacteria disappeared. So he wondered, does the tear contain something that kills bacteria? And then he found it. It was an enzyme, a certain kind of protein, and it is named lysozyme, which kills these bacteria to some extent. It's a mild antibacterial. So he knew that such things exist in nature. Therefore, when he saw that fungus, he knew that it was another natural thing, and then he thought of exploiting it. So because of this history, he could make sense of that accidental event which others had missed. They all had seen the same thing, but only Fleming identified it as a potentially useful thing. So that is serendipity for us. If he had not had this experience, he says, I would have thrown the plates away, as many of my colleagues did. Okay. Incidentally, Fleming was not the first to discover that these fungi have ability to kill bacteria. In fact, this is known for 1,000 years. What is this? This is stale bread, and you can see some black spots on it. This is fungus. Okay. Whenever you have stale food, fungi in the air settle down and grow. So this says Egyptians applied moldy bread on their wounds because it works as an antibiotic. People knew that for a long, long time. So throughout history, repeated evidence of mold being anti-infection has been noticed and has been put into use. Fleming went several steps further and worked on it. Then industry took it up and they could create a synthetic penicillin. Now we have it as an everyday thing. So the question is, if Egyptians knew it for 1,000 years, and they probably told this as old wives' tale, and we missed it. So should we take old beliefs seriously? All old beliefs seriously? This belief was genuine. And the answer is, don't take them too seriously. Don't believe the claims, but treat them as hypotheses and check them. And then if you get confirmation, then better to believe. And we are going to try and do something like that in the case of the present problem. So what is obesity? Obesity, of course, is this guy. You can make out he must be a senior citizen and has a tremendous punch. And, pictures like this, caricatures like this of fat people, they are at the receiving end of jokes all over the world. This is an exceptional picture of a fat woman. This woman was, I think, 500 kilograms in weight, and therefore simply could not stand up or do any normal activity because her muscles did not have the strength. Can you imagine walking about with 500 kilograms on your back? Impossible. So she was in the news some time back because she was flown in a special plane to Mumbai for a surgical treatment. And I think she went back to Egypt with a lot of it, her weight eliminated. And obesity is not a property of old people. This teenager is also obviously obese. So obesity is something which is very much around amongst us, especially in the modern times. If you go to tribals, you will find it very difficult to locate an obese person. But in cities, in plenty. So some obesity facts that in the world they say there are 65 crore obese people. You can get all this on the internet. And US has probably the worst situation. Japan has the best, and India is in between. And India has 13 crore people who are obese. And half of them have morbid obesity. What does that mean? It means not only they are fat, that fatness is causing them many other health problems. What kind of problems? You develop high blood pressure, diabetes, heart attack, and so forth. Why are people obese? Partly because of their diet, partly because of their lack of exercise, partly because of their genes, many different reasons. Now, genes you cannot change. And therefore, people who are worried about obesity try to work on their diet and on exercise. So gyms and diets are big business among rich people. So this diet business, some experienced people, wise people tell you that weight loss is 80% based on food and 20% on exercise, and 0% on massages and machines and belts and pills and so forth. But those are the things that people sell. Okay, so there is a lot of fake advertising. I lost 3 kilograms in 1 month just using green tea, things like that. Why is this dishonesty very much around? Because the obese people do not want to put in the effort to reduce their weight. Okay, they want it easy. They want shortcut. They want quick result. Whereas obesity is a consequence of a bad lifestyle, and you have to change your lifestyle to go back. That is difficult, painful. Okay. So here is a typical ad. I was 90 kilograms, now I am 60 kilograms. This is the first thing in the picture, and then they tell you, we know how to do it. And then they tell you, just pay us the money, and it's very easy. If you pay us, it's very easy. Okay. What kind of cost are we talking about? Again, you can see on the internet. I'm only going to quote one number, that US FDA approved pills for 1 year, and the cost is 1 lakh rupees. This is in the US, but even in India, in Pune, I know that the gyms and so on, slimming centers charge a lot of money. All right. So now we go to the topic, Dixit diet. So this man, the picture you see, is Mr. Jagannath Dixit. And he is Associate Professor of Preventive and Social Medicine in a government medical college in Aurangabad, Maharashtra. His recommendations and advice are all free. Okay, no cost at all. His recommendation is extremely simple, easy to practice if you make up your mind. What is the recommendation? In a day, you eat only 2 meals. Any other time, you only drink water. This is a simple recommendation. And there is a lot of following for this man. His lectures are organized all over the place. I know he had a lecture series in US recently. And he has given lectures in very big halls, Shanmukhananda Hall in Mumbai, with a 3,000 capacity and only standing room. So he has become a celebrity, very rare for a professor of preventive and social medicine. This is considered sort of the backwaters of a medical college. So what is his plan? His plan is very popular. He is on YouTube, many lectures, and millions of people have viewed his lectures. He has WhatsApp groups for exchanges of experience and advice. And there are thousands of people on these groups. And one claim I have seen is in 3 months, 8 kilograms weight loss resulted. Now, Indian Medical Association, Maharashtra, is not very happy with this situation. So there is this gentleman named Suhas Pingle, he's the secretary, and he says, there are real dangers with the diet. Now, for a moment, I was worried. What is the danger if somebody undergoes fasting? What is the danger? But he's talking about diabetes. See, what is it? Oops. So where is the serendipity? So Dixit recommended his plan for reducing weight. And many people reported that his plan helped them to reduce weight. This was as expected, no serendipity here. Then some people reported that not only it reduced their weight, but it helped them in controlling sugar. This was not expected. This is the serendipitous discovery. And Dr. Dixit thought that this is even more important than loss of weight, because for India, of course, obesity is a problem, but diabetes is a greater problem. Okay? Very serious problem for Indian public health. So in a sense, he seemed to shift his emphasis from obesity to diabetes. And in diabetes, if you do something wrong, it can really hurt you. That is why some of the medical practitioners are concerned. So there are lots of people in India who are diabetic, 30 million diagnosed patients of diabetes. And it's a chronic problem. It is a lifelong friend. You have to handle that friend with kid gloves all your life. Progressively, your body degenerates. So these are all the special problems of diabetes. So if something simple can help diabetes patients, that is wonderful. But doctors are not convinced. Okay. So one question is this evidence-based? This is only anecdotal, you see. There are no studies mentioned in PubMed or any other standard sources where medical research is given. Okay. Dr. Mohan Agashi is a psychiatrist, but a practicing doctor. He says we need scientific validation of these claims that diet plan of Dixit will help you in diabetes. Okay. Vijay Varad, he says we should have randomized control trials. See, now here statistics begins to enter the field. People not only want evidence, they want evidence collected through appropriate statistical experiments. They want randomized control trial. And there will be, what is control then? Well, you will have healthy obese people, diabetic people who are obese, and so forth. Dr. Amitav Banerjee, yet another authority in medicine, he says the study of this kind is very difficult. It is not feasible to administer a diet plan on a population level and keep all variables constant over a number of years. It takes a long time. So these investigation of this serendipitous conjecture is very, very difficult statistically. Difficult to keep participants restricted to a rigid lifestyle. See, swallowing a pill is very easy. Maybe someday in future we will develop an understanding of what is the link between genes and diet and disease, and then maybe. But till then, these commercial advisors who sell their things, they continue to prevail. Okay, so this is I've stated the problem. Now let us come to attempted solution. So I'm going to talk about two more doctors. One is Shyam Ashtekar. You see his picture here. And this is Ratna Ashtekar. This is his wife. This is a couple. They work in rural areas of Nashik district of Maharashtra state. I know Shyam since many years. When he was an MD student, I remember he came for assistance in statistics, and he had an interesting question. People thought that blood pressure, diabetes, all these are problems of people in urban areas. And he showed that in fact, these problems exist very much in the rural areas also. Anyway, he also is a very remarkable person in the sense you should see his biodata and his contributions to the area of public health. So they are both socially committed, okay? And they decided that this serendipitous conjecture deserves systematic investigation so that it will become scientifically acceptable. And so they have organized this study and they will write papers on it. And it is their study. I'm talking about their study. It is their data. And Dr. Paranpia and I are their statistics consultants. Okay. So data that I am going to show you are really not quite genuine. They are a bit synthetic. Okay. So what does he do? He says, or We agree that randomized control trial is not possible. Randomized control trial will mean that you will have subjects and you will toss a coin and say, you go into the Dixit diet, you go into normal diet. People don't accept that. Only voluntary basis work is possible. So randomization is not possible. Blinding is not possible. How can you hide the fact that you are practicing Dixit diet? Not possible. Okay. Randomization not possible. Blinding not possible. So if you do an experiment, it is at best a quasi-experiment, not a genuine, statistically designed experiment. So what will such an experiment do? Check those who follow Dixit diet plan, and also check a few who do the traditional management of diabetes. Okay? So we are talking about people who are taking up Dixit diet as a possible solution to diabetes. Now, what is the variable of interest, or in medical terminology or in clinical trial terminology, endpoint? And it's not sugar, but something else. It is called HbA1c. And it's an indicator of long-term sugar control. It reflects cumulative history of 3 months, and it's a reliable measure of sugar problem. Okay. And generally, for a healthy person, the HbA1c level is 4% to 5.6%. Whereas 5.7 to 6.4, this range is considered pre-diabetes. And 6.5 onwards is considered diabetes. So it's a good indicator of diabetes and widely accepted in the medical world. So what is the aim? The aim is that if you are diabetic, which means your level is above 6.5, with Dixit diet, hopefully it will go below 6.5. You will become not cured, but at least pre-diabetes. Okay, this is the idea. What is the plan of trial? You have 2 groups of diabetic subjects, one under conventional allopathic medication, you take insulin pills or injections or whatever. A second does Dixit diet. And what will we do? We'll measure HbA1c level before and after that period of, let us say, 3 months. And check which group has greater reduction. Well, you have 2 sample problems, so a simple 2 sample t-test will do the job. So this looks like almost a trivial problem statistically, but not quite. So what are the problems? And as consultants, we advised Shyam and his wife that the first thing you do in a clinical trial is to register it. And now this work is registered with the appropriate authorities of the government. Why do you register? And again, this is a statistical matter. So we all know that if we were to apply to sample t-test, we'll use an alpha level of 5% or something. And if we don't have the law to register, what can a unethical scientist do? He does an experiment. If it is not significant, he simply throws away and repeats the experiment, and so on and so forth. Now we know that even when null hypothesis of no difference is true, in 5% cases, the difference will be significant. 1 in 20 cases, difference will be significant. So this unethical scientist goes on taking samples and comparing, and the first time you get significance, that is the trial he shows to you. This is possible. Sometimes people have done that. To avoid this, the rule is you want to do an experiment, you want to claim cure for something, you must register and tell us before you start the experiment. So you can't hide the results. Okay. So the idea was there should be about 300 people in each group. What is the cost? So the cost, see, all are volunteers. Shyam Ashtekar is volunteer, his wife is a volunteer, all doctors, a whole bunch of diabetologists and others participate, all are volunteers, social work. But the pathology laboratory, which will examine your blood, is not voluntary. They charge you. And therefore, if you have no money, then you want to minimize the number of observations you will take. Okay. So the doctor said, I remember that meeting, that we'll have one measurement at the beginning, one measurement at the end, and that's enough. And I intervened and I said, no, you must have at least 3 measurements. And they said, why? What for? And remember, here our statistical training becomes very useful. And I said, curvature can be estimated then. They did not quite see that. And I said, can I use the board So I remember that day, there were 20 doctors and diabetologists, and I was the lone non-medical guy. So I went to the board, took a whatever colored pen and drew a graph. So I said intermediate value is extremely important because it will tell us how we progress. And there are three possibilities, and I drew this curve on that whiteboard. And I said to them, look, let us assume that you are at 0 in the beginning, at the end you are at the desirable level, and suppose the intermediate steps are linear, a straight line. Then it means that the effort you put in gives you proportional reward. On the other hand, if you are following the top concave line, I call it concave, I don't know what you call it. If you concave, then initially you will do much better and then you will reach a flat area. On the other hand, if it is the third one, the convex one, then initially situation will be very discouraging and you will get results only towards the end. This distinction is very important for counseling the patient. So a middle value, at least one value in between, which will allow us to check the linearity and non-linearity is very, very important. Okay.
Sir, it's 20-minute reminder, sir.
Thank you. I will quickly go to the...
Sir, you can go 5 minutes easily, and after that 5 minutes for the discussion.
Okay, excellent. So what are the problems? So Dixit diet people are available in plenty, but the control, that is people who are managing diabetes traditionally, are not available. Why are they not available? What do they care? What is the benefit for them? Nothing. You will impose discipline on them, make them do things. So nobody is available. We said whoever comes is fine. Again, this is not a very good thing for a randomized clinical trial. But what to do? Remember, in statistics, methodological innovation comes up when there is a practical difficulty. All the designs that Fisher proposed were to overcome a grassroots level difficulty. So this is a great difficulty in this particular experiment. We don't have any methodological innovation to report, but we certainly do have a lot of practical difficulties to present. Okay, so you cannot randomize. This is not an experiment. At best, it is quasi-experiment. All this was happening, and then there came Corona, and everything stalled. Okay, so then some kind of quasi-observational study was done, and people are in the process of analyzing and writing papers. What's the null hypothesis? That the reduction in HbA1c is similar for two arms. An alternative is that Dixit diet gives better reduction. And you can't really apply two sample t-test because two groups may not be similar. There may be differences. The change in HbA1c may be affected by gender, age. Remember, we are talking about volunteers, so we can't control any of these things. Age, duration of disease, heredity, duration of treatment, and so on. So what do we do? Change strategy. If we cannot manage something during the design stage of an experiment, then we try to manage it in the analysis stage. Okay, we cannot choose subjects, we cannot randomize, we cannot do any blinding. So we just do at the analysis stage, and that is the last thing I want to show you. So we said we will do multiple regression analysis, and all the confounders will be treated as covariates. So age, we will include age value as a covariate. Gender, 0 if female, 1 if male. Duration of disease, again, will include how many years are you suffering from diabetes. Duration of treatment, okay. Then genes, parent diabetic or not, things like that we will add as covariates. Here is a illustrative output, and you can see look at the column for p-values. So the age in years is not significant. It doesn't seem to matter. What is the next? Distance from targets. You want to go to 6.5. If you are far away from it, much worse, then the result is better. But if you are close to it, then the result is not so good. Duration of treatment is this gap V last minus V1. V last is last visit, V1 is the first visit. The difference is the duration. It's not significant. Diabetes duration is mildly significant. Dixit diet is way significant. No question about it. usual management of diabetes does not reduce HbA1c. Dixit diet seems to reduce to some extent. Okay. What else? Gender, diet type, nothing is significant. This is the analysis. We have some people who have been doing Dixit diet for a couple of years. And I will just show you two graphs. What does the evidence about their HbA1c? And these individual plots are called spaghetti plots. Nothing serious about that name. So look at this. Each line is one subject. And what conclusion am I drawing from this? That for patients with level around 6 point, that red line is the 6.5. And most of these patients are a little bit above, a little bit below. And nothing much is happening. HbA1c is not really changing much. Okay. There is some up and down, but nothing great. On the other hand, if your situation was very bad, here you are. We are talking about HbA1c 16, 17, quite high. Then what happens? Then with Dixit diet, HbA1c levels crash. And you come to the 6.5 level, roughly speaking, and then oscillate. Okay. So for patients with very high levels at start, in the first 200 days, there is a big decline in HbA1c. And then that curve is flat. It doesn't really go very far below that 6.5. Fall in the first 100 days is sharp, then flat. Okay, so this is our finding from long-term adopters of Dixit diet. So what are my concluding remarks? That randomized control trial with blinding, the best design for treatment, not possible for Dixit diet. Observational study suggests that dieting for 6 months can cause substantial reduction in HbA1c and reduce risk of complications. And the last thing I will say is, I have done similar studies of other traditional medicine, and this is the general situation, that traditional medicine is mild in its effect. It takes time. It doesn't show any dramatic results. But my conclusion over the years is these methods are default options. You should first try them out. And if you get what you want, you are done. If not, then maybe you can go to current practice of going to the allopath first is probably not recommended. So my purpose was showing you a real problem of the society, a potential solution, namely simple fasting, and a statistical study to show that it does seem to work to some extent, but nothing dramatic. Okay, so I will stop there. Thank you.
Thank you very much, Professor Gorey, for touching a very, very important problem of diabetes in India. First of all, I just wanted to, I think Satish can help me. If somebody wants to ask a quick question, 1 or 2 questions, I think Professor Isha Diwan has raised her hand. So please open the queue. Professor Diwan, please.
Yeah. Thank you, Professor Gorey. As usual, your talks are very, very interesting. I just wanted to say that intermittent fasting is become a lifestyle where lots of friends are now eating twice a day and nothing to do with Dixit diet. So most of them seem to be eating at 10:30 and 7 p.m. And I remember when I used to visit Pune, you all used to eat twice a day. You would come to the department after a meal and then go back and have your meal. So...
Yes, you are right. Twice a meal, or what you call the intermittent fasting, is not a new thing suggested by Dixit. A lot of people practice it and a lot of people benefit from it. So Dixit luckily does not have any tall claims. He's an extremely simple man. And I want to point out to you the problems with such kinds of medical recommendations. That these problems, these recommendations or research based on these recommendations does not get financial support. Because if Dixit diet helps people, who makes money? Dixit is a very simple man. He's almost a saint. He says, "मेरे को तनख्वाह मिलती है, मेरे को पैसा नहीं चाहिए. Everything I do is free for the society." Whereas the pharmaceutical companies, they make so much money by selling their monopoly medicine. That is why they can afford to do these trials extensively at great expense. And so the society that is wise will look at these studies as very important potential social benefits, and the government will have to support these activities, whether it is whether it is Ayurveda, whether it is homeopathy, or it is Dixit diet. We need a different kind of financial system to promote research in these areas. Because I know Sham and his wife, they work among tribals. What kind of money you think they make? Yeah, nothing. And therefore, they can't really afford an elaborate study. So you are right. This is not a great new thing. We have now discovered that it may be helpful too. So it's a serendipitous discovery, which is probably of momentous importance for public health in India.
Thank you.
Thank you, Professor Gorey. I think I just had one question in my mind, which I just wanted to share with this august audience. When we talk about diet, drug, and exercise, basically the diet, and when we talk about, like as you today told us about the Dixit diet, I was just wondering about what is the correlation between the calorie and the sugar count. Because ultimately, if it is all the calorie count, and if it is ultimately the diet which you are taking is going to affect your sugar level, or the spikes in the sugar level, you eat some sweet, suddenly the sugar level will go up if your body is not producing enough insulin. So, sir, are there some studies like connecting that the calorie and the count of blood sugar, keeping age to be fixed?
Yes. So Dr. Srivastav is asking a technical biochemistry question. I am not quite qualified to answer it, but all I will say is the following: that Dr. Dixit and his colleagues will go to great lengths to explain to you why eating only twice is their recommendation, whereas what you eat and how much you eat, they do not restrict you at all. So you can eat. Yes. So they seem to claim that if you have intermittent fasting, then the calories that you eat doesn't matter. They have some connection, with how insulin is generated in our body and so on, which I don't understand. You'll have to read a little bit more. But they are very clear. It does not matter. You can eat whatever you want in as much quantity you want, and it will still give you benefit for controlling your sugar. This is the claim.
Okay. Thank you very much, sir, for very enlightening talk and very guiding.
Sir, can I have a question, sir?
Sure. One quick question from Ramaya MS.
Sir, excuse me, sir. Good afternoon. Can the diabetes is reversible through proper diet? Right.
What we are saying, what the claim is.
Kindly mute behind the noises coming. And then
the only claim is that if you follow intermittent fasting as prescribed by Dixit, then your HbA1c level over a couple of 100 days goes down from very high level to something which is the boundary between diabetes and pre-diabetes. That is the claim. It is not very strongly supported, but that is what we are saying.
Absolutely. Thank you very much, sir. I think this discussion can go on. I'm sorry that I have a limitation of time because we have another distinguished speaker with us. I think I wanted to make sure that Professor Shobhashish Das Gupta is there. Professor Shobhashish Das Gupta, are you there, sir?
Yeah, I am here. Can you hear me?
Well, yes, I can hear you, but I cannot see you, Professor Das Gupta.
I am traveling actually, so it's
okay. No problem. No problem.
Yeah, so,
no problem. No problem. Thank you very much for joining us, even while traveling. I wonder. I just wanted to share one thing. Another speaker in the tomorrow's session is also traveling somewhere in Mexico. So I will not take much time. Professor Shobhashish Das Gupta, I got some of the basic information from LinkedIn contacts. I have never met him, but I have seen some of his posts, and he is a PhD in statistics and machine learning. He has a very good connections in India and abroad. Right now, I think he is working as associate director in Pfizer, and as well as he is associated with the Chennai Mathematical Institute as an adjunct professor in India. I will not take much of the time between the audience and the very learned speaker, Shobhashish. So I just welcome you on the behalf of the ISPS and thank you for joining us. I wish that I can give you 25 minutes maximum, sir. 20 minutes of your presentation and 5 minutes for your interaction with the learned audience. I welcome you once again and thank you very much. Even while traveling, you are joining us. Thank you.
Thank you. So let me share. So Google Meet I don't use. So let me see.
You just
It's very easy. I'm meeting
a window. Yeah, a window or a window, right? Sharing a window, and then yeah, I think so.
first you open the,
Share. I think
first you
this is.
open your slides.
Can you?
Now it is coming.
Yeah, it is there. It is there.
You can make
Can
it
you
full
see
screen.
now? Now it is okay.
Yeah.
Is it fine?
Yeah, we can see.
Okay.
Make it
Great.
full
Yeah.
screen.
Thanks.
Professor Dasgupta.
Yeah. I just made it full screen.
Thank
I just
you.
made it full screen. Control.
Thank
Is it okay?
Yeah. Okay. Please go ahead.
Okay. Thank you so much for inviting me, and thanks, Professor Balakrishnan, the president of ISPS, for the invitation. So there might be some trouble in the internet access. I am currently sitting at Srinagar. So so there are some, though we are having a kind of Wi-Fi here, but the strength is not that much good. So I came outside of the hotel, and
We
I
can
think
hear you.
here.
No problem, sir.
Okay, good. Thanks a lot. So this is a talk on applications of statistical machine learning in biomarker selection that our global team is doing at Pfizer. And I would like to acknowledge my summer intern Ritvik from IIT Kanpur, Department of Statistics, who is working with me for some months now, and my global colleagues Jay, Shibing, Russell, and the entire Avolumab team of Pfizer. And because we got the data from the Avolumab team, and they are the domain expert, and we kind of regularly interact with them. But due to confidentiality of the data, because the paper is under review in Nature, so here I am going to mask the data, and I'm not going to tell about all the data description, but I can always kind of mask it and cleverly give you the overview, and that's not a problem at all. So first the data description, and then exploratory data analysis, and then modeling. And first, a bit of background here, that platinum-based chemotherapy is a standard of care, which is the first-line treatment for advanced urothelial carcinoma, but the durations of overall survival are limited by emergent chemotherapy resistance. So in the phase 3 trial, they call it Javelin Bladder 100, the patients with unstable locally advanced or metastatic UC without disease progression, they got the first-line chemotherapy, and they were randomized to receive the maintenance Avolumab. That's the kind of injection, plus best supportive care, which is kind of chemotherapy. Like, so it's a randomized patient for 700. Some of them go dropped later, but that's okay. At the moment, initially 700. Maintenance Avolumab plus BSC significantly prolonged the overall survival versus BSC alone. And we can see that the median overall survival from randomization was 21.4 versus 14.3 months respectively. So the conclusion was maintenance Avolumab plus BSC significantly prolonged overall survival versus the best standard of care alone in patients whose disease had not progressed with first-line chemotherapy for advanced UC. And last year in June 30, the FDA approved Avolumab for maintenance treatment of patients with locally advanced or metastatic urothelial carcinoma that has not progressed with first-line platinum-containing chemotherapy. So this is the work that was, done for our entire Avolumab team, and then I was interested in the data because I was thinking in a different direction. So that I can get the data and use my ideas to kind of give a different perspective, different insights. So going to a point of data driven approach, data scientific approach is this. What we got is 189 variables and 688 observations on patients. As I told you that some of the patients were dropped right from the clinical trial. So from 700 to 688. But you can see 189 variables is too many variables. So kind of high dimensional with respect to the sample size here, because we have a lot of missing data also. So we have to remove that. And so let's see how the complication started here. So basically, two are related to the outcome. There was which is kind of binary, censored or uncensored, and the overall survival time is there, which is of course in months. And then there is one treatment arm, which is avelumab plus BSC is the treatment arm, and the BSC is the control arm. And there are equal, participation, 344, 344 each observations in the treatment group and the control group. And there are 4 baseline patient characteristics as sex, age, Strati 1 and Strati 2, where Strati 1 is best response to first-line chemotherapy, and Strati 2 is metastatic disease site at first-line chemotherapy. Now, the remaining 182 are all biomarkers of interest, and among them, one biomarker is binary, and rest are treated as numerical. But we will do some feature engineering based on our domain expertise and how they wanted us to kind of incorporate their domain knowledge. Among those 680 patients, you can see only 429 have complete data. That means over 37% missing observations. It's very difficult to handle all the missing observations because we have high dimensional data, and there are different biomarkers. They have lots of different types of restrictions on that. So the missing data analysis is very complicated and open research problem in this kind of high dimensional and low sample size problem. So we, at the moment, we removed all the missing observations and we exclude all the missing observations. So you can see initially it was 222 observations in the treatment group and 207 observations in the control group, and then 17 variables out of 187, excluding the responses, have at least 30% zeros in their observations. So what we can see here, that then again, there are huge sparsity in the data, right? Now come to censoring. We have 688 survival times, the original data without eliminating the missing observations, out of which 320 are uncensored and 368 are censored. So here, in the original data, 53.4% is censored. In the complete data, that means excluding the missing observations, we have only 429 survival times, out of which 198 are uncensored and 231 are censored. So here also it's a little bit increased the censored observation. So what we are getting, this is a snapshot of the original data. I just masked them. I just kind of giving them a biomarker 1, 2, 3, 4 like that. And this is a snapshot. You can see a lot of missingness, a lot of sparsity, and different types of spatial values, and that depends on the particular biomarker, whether that biomarker is taking those kind of specific values or not. So those are very interesting. So in this case, feature description, you can see that numerical variables and categorical variables, we can divide that. 182 numerical variables, 5 binary variables out of the categorical variables. What are those? As I told you, treatment, of course, sex, Study 1, Study 2, and there is a biomarker 5, which is one biomarker which is binary. And then we did some feature engineering in this case out of domain knowledge. And then you can see that BM4 was recorded as 1 if it is greater than or equal to 2, and it's recorded as 0 if it is less than 2. Biomarker 8 was recorded as high if it is greater than or equal to 25, and low if it is strictly less than 25. Another new binary feature, CBM, we are calling combination of biomarkers, was created by combining 2 numerical features, of course, according to the domain knowledge, as per the following rule. What is that? BM6, if that is 1%, and BM7, if that is 100%, then we are calling that new combined biomarker CBM as high. If BM6 exceeds 1% and biomarker 7 exceeds greater than or equal to 25%, then CBM is high also. Otherwise, we treat CBM as low. This kind of feature engineering we did for some of the biomarkers. And then our final feature description is this. We have 178 numerical variables, 8 binary variables, and as you can see, all those 8 binary variables are there. So our data is now came to 429 cross 186, n cross p. So this is a high dimensional, a bit of small sample size problem. Why I'm coming now. So before we go through the modeling, of course, exploratory data analysis, data visualization is important. And we have identified 12 inconsistent features. Note that here I am just roughly calling it is inconsistent. It is not a statistical technical term, right? Inconsistent means there is a huge proportion of zeros here, and depending on the number of unique values, as you can see that BM11 is taking 141 number of unique values. The proportion of zeros is over a bit 60%. If you look at BM177, there are only 2 number of unique values, but the proportion of zeros is exceeds 99%. So we have identified some of the biomarkers, and we are calling them inconsistent not in a technical term, in a sense that they have the different types of unique values, and proportion of zeros are all based on complete 429 observation. So those variables are kind of creating problems, but we need to see how we can go ahead and analyze this data. And you can see from the histogram for inconsistent features, and here you can see a lot of zeros, like those biomarkers are taking a lot of zeros, and very, very few non-zero values they are taking, right? So those are also, all those histogram of those trouble, creating troubles, those type of biomarkers, right? Some of the categorical variables we can do examine that by kind of a log rank test, and if you can see that we have that treatment, and the p-value of course is significant, but for when we did that for sex, the p-value is high. For other different binary variables, we have also done those log rank tests, and some of them came to significant, but we decided since there are very few binary variables, we will keep it. We are not going to discard it. So it's the main problem of inferential variable selection. That's the main idea here. Which biomarkers are significantly coming out of the high dimensionality. So that is the main inferential goal that we wanted to study here. So initially, there are a lot of biomarkers. How to screen by kind of an exploratory data analysis. So we did this variance inflation factor, and you can see that's 1 over 1 minus RI square, and if RI square exceeds 0.9, that implies VIF is bigger than 10. In that case, so whenever we have bigger than VIF bigger than 10, we can just kind of a threshold is 10, and we can screen it accordingly. Like for example, biomarker 31 has VIF 516.12, very high biomarker. This implies that 99.82% of the information present in biomarker 31 is being explained by rest of the numerical features. So here, one screening is this variance inflation factor. If we just go through the exploratory data analysis, and in this case, there is a huge collinearity among the numerical features. So if we can look at the correlation, so 105 numerical variables out of 178 have correlation more than or equal to 0.8. 158 numerical variables have variance inflation factor higher than 10. So if variables were to be eliminated until VIF is less than 10, we would be left with only 68 numerical variables. So what I've done, screening is basically using VIF 68 numerical variables, but all the 8 binary variables we did not want to exclude. So we went ahead. So you can see that before the elimination of numerical features whose VIF the variables, and huge number of variables are on the right, extreme right side. But after that, the screening based on VIF, we can get all in terms of below 10. Good. So at the end of the day, using the exploratory data analysis, we have using VIF, we have created a list of 76 variables. Out of that, 68 numericals, 8 binary. And you note that 68 out of 68, there are some inconsistent features came into the picture when we screened using VIF. So it's not that we have eliminated those inconsistent features, and all the 8 categorical variables were there. Now we come the modeling part. As I said that there's some background noise coming in. Okay, thanks. So as I said, that why this is a big problem, because if you just take the data and use a Classical Cox will be kind of give you a failing result that not converge because it's high dimensionality problem, low sample size. So you have to screen, you have to do variable selection. Classical Cox otherwise fail in this type of situation. Why? Because severe collinearity among the explanatory variables, high dimensional data with not enough sample size, only for 29. You have high dimensional over 150 variables. Sparsity in the data is over 8%. High percentage of censored observations, 53.8%. So in that case, we need to do some kind of variable selection. Otherwise, we are not going to use classical Cox. So what we have done here, use that exploited analysis using VIF, and we did classical Cox, and the p-value came significant. And then out of those 11 variables to be significant came 5% level of significance, and the C index, which is a kind of a measure of how the model is doing, performance metric that is 0.770 to high C index. The model is basically, we are saying, a good fit. So here I can list down all those biomarkers which are coming significant with the unpenalized Cox, or which is classical Cox. But what I wanted, let us take all the variables, let us not throw out any variables using any type of exploratory data analysis. Let us use regularized Cox. Let's use statistical machine learning approach. And of course, under the umbrella of Cox, we are at the moment we have stick to under the umbrella of Cox, but we also went out of umbrella of Cox. We did also random forest, which also gave us some of the very interesting, significant biomarkers, which are all basically kind of consistent with regularized Cox also. So here, what we did, we have taken all the data, of course, excluding missingness, and we did lasso, ridge, elastic net, and adaptive lasso. And we all know that the regularization, all different penalty, right? We just can have different L1 penalty, L2 penalty, and a combination of L1, L2 penalty will give you those different kinds of regularized Cox regression. So for lasso, it's L1 penalty, as you can see. For L2 penalty, it's a ridge. And then elastic net is a kind of combination of L1 and L2. And there's an adaptive lasso where we are giving weighted sum of the absolute value. So we are adaptively weighting with the penalty. And that weight is basically over absolute value of beta j curl, where beta j curl is our ridge estimate, because ridge is not going to give you exactly zero estimates, whereas lasso, elastic net, and adaptive lasso, they are going to tell you that, hey, these coefficients corresponding to these biomarkers are exactly zero. So basically, they're not significant compared to the non-zero coefficients. That's the simultaneous variable selection and inference Cox, regularized Cox, those models are doing. So and for that, this is a statistical machine learning approach. We have to do cross-validation because there are a lot of tuning parameters. So for the tuning parameters, so basically for lasso, adaptive lasso, and ridge, there's a tuning parameter, penalty parameter called lambda. For elastic net, there are two different tuning parameters. One is alpha. You can see here elastic net alpha, and then another one is lambda. So basically, you need to do cross-validation, and then the cross-validation error is called partial likelihood deviance. So you need to minimize this partial likelihood deviance to find out which is the optimal lambda. And then also for elastic net, there is another loop over on the top of the lambda. There's alpha. So the grid search algorithm is going to have a lot of values of alpha. Which combination of alpha and lambda gives you the minimum cross-validation error, aka PLD. And at the end of the day, you finalize the model, you fit the model, and then you find the corresponding C index to find out, and that model is going to tell you which are the non-zero coefficients corresponding to which biomarkers. Those are significant biomarkers. Okay, some of the I am hearing some background noise. Please mute yourself. Okay, please
and sir, last 5 minutes, Professor Das Gupta.
Yeah, thank you. So, and then what we are going to do, so this is not one time. So this is any statistical machine learning, we need to do multiple times. There are 100 iterations of the data, but it's a random, kind of a different type of random realizations of the same data, right? We need to do that multiple times. For each of the random realization of the that data, we need to do cross-validation to find the optimal parameters, and then we'll go for the statistical machine learning model, lasso, elastic net, or adaptive lasso, or ridge, right? So and then at the end of the day, we can find out the average partial likelihood deviance, and to find out which model is the final model, and then we can calculate the corresponding C index for the final model. Okay, so this is the comparison between all those penalized regression models that we can say, and you can see that we have number of non-zero variables. Out of 186, lasso is saying 6, and this is 32 times out of 100. 32 times lasso is saying that this is 6 non-zero variables are coming. Ridge, of course, ridge is a different penalty, L2 penalty. L2 penalty does not give you exactly 0, but ridge will give you a very small coefficient value for the non-significant variables, a bit high coefficient values or estimates for significant biomarkers. Elastic net is giving you only 15 non-zero variables, and this repeated 9 times out of 100. Adaptive lasso is also giving 9. So, and the corresponding average PLD and the standard deviation. And after we finalize the model, how we finalize the model, the maximum, most frequency, out of 100, how many times the same model came into the picture, that is, we finalize the model, and then we find the C index. And as you see, almost all the C indexes are quite similar, close to each other. And we can have all those coefficients also. And as you can see, some of the non-zero coefficients for lasso, elastic net, and adaptive lasso, the list, and from there the non-zero coefficients are kind of significant. So it's a variable selection and estimation simultaneously. The stability of feature selection that we can see for lasso here, that the final model is going to give you the 6 significant biomarkers, and out of 100, those are 68 times repeated, right? And then elastic net, we can have those final variables, and then out of 100, 12 times they have repeated. The most stable wise adaptive lasso, and it's kind of expected theoretically. Adaptive lasso has the oracle property, which is variable selection consistent, which lasso and elastic net fails to do. Because of this, adaptively weighted penalty, adaptive lasso enjoys that oracle property theoretically, and here also you can see it's more consistent, and 96 times out of 100 they are selected the same significant variables which are highlighted here, right? And in a similar way, we excluded the control data. We just did the analyzing treatment observation, because the Avulmap team, the domain expertise, they were so interested in our analysis because of identifying the most significant biomarkers for the whole data. They told me, why don't you do that for only treatment observations? And then also we have done the similar thing. I'm not going to go ahead, but for treatment data, of course, it's a bit smaller data. So because we are excluding the control data, but we are also getting interesting results here using the statistical machine learning algorithms. So what we are it is happening that we are not going to exclude any variables initially. Let the data-driven model decide, data-driven algorithm decides which variables, which biomarkers are significant or not, before we decide, right? Of course, after that, we are going to tell the domain expert that, hey, our machine learning algorithms are telling this biomarker is significant. What do you think about that? And they're so much interested that, okay, we are also thinking these variables are should come significance, because a huge number of biomarkers, different types of biomarkers, and complicated data, high dimension, low sample size, huge censoring, and huge missingness. A lot of different complications are there. So it's difficult to analyze unless you come out of the the traditional statistical zone and go for a more advanced machine learning area. So what is the summary here? I am coming out one of our most efforts here to evaluate different feature selection models in this data. It looks like most models provide consistent feature selection. We find that the data suffers from various problems such as severe collinearity, high dimensionality and low sample size, high sparsity and high amount of censoring. In our modeling framework, we consider 5 types of model. The first one is the classical unpenalized Cox proportional hazard model, but we have to do feature selection because classical Cox model fails because of the high dimensionality problem. Okay. Then penalized Cox for lasso penalty, ridge penalty, elastic net, adaptive lasso penalty. Here we don't have to, we don't have to screen the variables. We can feed the model with all the variables. Let the data-driven model decides which variables are significant and which are not. Adaptive lasso method is found to be more stable in selecting features than elastic net and lasso method respectively for our data. As expected, theoretically, adaptive lasso enjoys oracle property, and in practical situation, in reality also, it shows us that, okay, variable selection consistency holds. We also conduct a separate analysis of treatment only observations, and we note that the problem of collinearity becomes more severe in case of treatment only data because the data reduced, right? All the models based on treatment only data have a higher C-index and lower partial likelihood deviance than the corresponding models based on the complete data. This is a bit interesting results because we have confined ourselves to only treatment data. There are some common non-zero features found by penalized regression models in case of both complete data and treatment only data. And as I told you, the work is still going on. We have done random forest, and we have come across with significant variables which are very much consistent with the regularized Cox. But random forest is totally outside the Cox paradigm, right? It's a very new, it's a decision tree idea, and that approach also gives us a different types of insights about variable selection. And future work is, of course, post-selection inference for regularized Cox models, because regularized Cox models, after you find the coefficients, non-zero coefficients or just zero coefficient, you can have an idea that which variables are significant, which are not. But there are some post-selection inference work is going on that. It's not easy to get the p-values, right? It's a confidence interval for the estimates. When you do this regularized Cox, it's not that much straightforward when you do just the classical Cox. With classical Cox, we have all the machineries established. For regularized Cox, it's all depending on machine learning tools and techniques and all a data-driven approach. So that is very important, and this is a very exciting research, post-selection inference for statistical machine learning algorithms like regularized Cox models. And we are also, of course, we need to explore Bayesian approaches for variable or model selection, because we want to see that if we just go ahead and do Bayesian machine learning, where we can have different priors like horseshoe prior, right? All those penalty prior, where we can have the shrinkage prior, and that idea can help in future. So those are the main idea now for model selection or variable selection. This type of data are very common in reality for clinical trial data, and this is a kind of a work and kind of an innovative work. We want to see that how the research is developed and how we can apply in real clinical trial data, the real world evidence data, right? Real world evidence, that's a new thing also, right? The real world data. So those kind of thing, those type of new types of data, we can have lots of different machine learning approaches along with our classical statistical approaches and get the new insights. But also, I just want to point out here, prediction is very difficult here. We have tried to predict, but prediction is not working well. It's very difficult to build a good predictive model. Though we can identify which are significant, which are not, but there are no good predictors, strong predictors that you can build a strong predictive model, even if you just go advanced machine learning methods. It's fading. Okay. Thank you so much for listening.
Thank you, Professor Das Gupta, for a very, very interesting exposing a very interesting research area when we talk about the data-driven model selection. Before I give my concluding remarks, or I ask one question from you, it is open for one or two quick questions from the audience, if anyone wants to ask. Please go ahead. Anyone from the audience? Okay, if not, sir, as you have already answered one of my questions, that as you are saying that it is not very good for predicting, because whenever we go for the model selection criteria and your C index coming 0.7, model is assumed to be good. Maybe, as you said very rightly, that we have to explore not by the stepwise regression, forward, backward, or the type of thing which we teach in the class from Draper and Smith. The idea here is that it has gone to the machine learning approach, and as you very rightly pointed out, random forest, and you have also mentioned about the exploring the Bayesian approach. I was just wondering, I'm not at all into this area, but naive-based classifiers can be helpful. I think, I don't know, but how much they can be helpful. But
for classification.
Yes, sir.
Naive-based, for classification, but for variable selection, we need to do a different Bayesian variable selection approaches.
Exactly, sir. Exactly, sir. So final, it's a very interesting area, I think, which you have exposed to our young researchers. I think many of us may be interested in contacting you and all those things. Thank you very much for your very enlightening
Thank you.
talk, and hopefully we will be still in touch after this ISPS and maybe many conferences you are attending.
Sure,
and presenting. So it's thank you very much on behalf of the ISPS and on my own behalf.
Thank you.
Thank you for joining us.
And I would also like to say thank you to all of you, the organizing committee, and Professor Gorey. He just presented before me, and he was my teacher while I was doing my masters in Pune, and it's so it's like both of us giving in the same session. So
really, it's a pleasure.
And good to see Professor Gorey online. Yeah. So, thank you.
Professor Gorey, I know him for the last 20 years, as I mentioned. He has been very quiet, very, very cooperative, and very kind person. Anyways, thank you, sir. And now we move on.
Thank you so much. Thank you.
Yeah. Now we move on to the contributory paper session. I just wanted to, before I start, I just wanted to make sure that the presenters for this session are you, all of you are there? Kindly raise your hand, just put your video on for a minute, and then we'll go just as per the sequence provided to me by the organizing committee. So the first speaker today is Mr. Faiz Noor Khan. Are you there?
Yes, sir, I'm here, but I'm sorry my camera is not working.
Okay, no problem. Faiz, and the second one is S. Saranya.
Oh, yes, sir, I am here only, sir.
Okay, can you put on your camera for a moment?
Yes, sir, yes, sir.
If possible. I mean, I know that there is a bandwidth problem, net connectivity problem, all those things are there. I am not, you should not present right now. Please don't present.
Okay, okay, sir.
We'll go as per the sequence. Okay, doesn't matter. While presenting, we can see you. And the third one is, of course, because I have been approached by somebody, and this Aditya Adhotra will be presenting in some other session. He is not presenting in this session. So the last speaker in the session today is Ramaya MS. Are you there?
Yes, yes, sir. MS.
Ramaya MS is. Oh, okay.
Yeah,
okay.
sir.
So thank you very much for all the presenters remaining present in the session. The general instruction is that the total time given to each presenter is 15 minutes, but out of that 15 minutes, you have to make your presentation for 12 minutes, not more than that. And the last 3 minutes will be open for general question answer session or the interaction session, whatever you call. So with this opening remark, may I invite Mr. Faiz Noor Khan to present and share your screen. Mr. Faiz.
Yes, sir.
I'm not sharing the screen. How it has come?
All right, so can you see my screen?
Still not. Please share your screen. It is, I think, Sarvanan's screen is there. Please, Sarvanan, if you can hear me, please stop your presentation. Faiz, you can go ahead.
Sir, I have already started.
But I am not able to see your screen. Are others able to see? Satish, are you there? Professor Satish Kumar?
So this is input port.
No, sir.
And this input port is always forward.
Anybody here can see the screen of Mr. Faiz Noor? Yeah, now I can see Mr. No, it is not Faiz, somebody else.
No, sir.
नहीं दिख रही ना अनीता?
Not visible.
Not visible, yeah.
It's not visible.
Faiz, you log out, just, I mean, don't log out, you just join again. I mean, try to present your screen again.
Okay.
Yeah, the screen is not visible to any one of us.
Yes, sir.
If you are finding any difficulty with net connectivity or anything else, we can move on to the next presenter.
Sir, I think so, because it's saying that it's not able to grant permission to share screen. I have tried it 2 times.
Okay. You do one thing, you leave the meeting and join again.
All right. Okay.
Last time. Otherwise, I will move to the next speaker.
All right. Okay.
And you can present in the end, of course.
This resistance is very low, and that's why.
And please mute others are requested to please mute your mic. Other participants are requested to please mute your mic. Mr. Noor Khan, you please leave the meeting and if possible, join again.
So I think it has started now.
I hope so. Yeah, it is there.
All right.
Please go ahead.
Okay. So I'm going to be presenting on a topic about diabetes also, and it's about the complications that are caused from diabetes. So I hope you can see my screen right now. And what my work is related to is predicting the heart disease complication in Indian type 2 diabetes mellitus patients. This is a collaborative work with my supervisors. Just a brief introduction. Diabetes was first of all found in Egypt in 1552 BC, and it has grown at an alarming rate ever since then. And in order to control it, since there is no proper cure or proper removal of the disease, it will be best that we can control it regarding the risk factors or using the risk factors by forming predictive models. Currently, worldwide, there are 464 million diabetes patients, according to International Diabetes Federation. And in India alone, 77 million total are already there. And out of which, or not out of which, but extra, 42 million are undiagnosed. So it is very important to be able to monitor and predict the undiagnosed patients also. Now, there are three types of diabetes: type 1, type 2, and gestational. In this study, we'll be only covering the type 2 diabetes. What we have is, suppose that in order to manage and control the disease, we need to study the data regarding the diabetic patients. So, the important variables that are related to diabetes, the exposure, and the outcome, whichever we are interested in. Now, the outcome can be the disease status, clinical any variable, and drug effect variables. Risk factors can be the independent variables, which are anthropometric, demographic, clinical, and medications. Now, the risk factors for diabetes, there are many of them. First of all, there is being overweight or obese, leading an inactive lifestyle, age, having a sibling or a parent or just any family history of diabetes. Gestational diabetes is also another risk factor, and cholesterol level, lipid profile, and high blood pressure. Now, having uncontrolled diabetes, it leads to many complications in brain, teeth, nerves, kidneys, heart, and eyes. And in this study, we'll be focusing on the heart complication. Now, what are risk scores? Risk scores are probability of disease, incidence, and prevalence, while knowing that there is an absence of an exposure. Now, it means that suppose that we are interested in an outcome, and now for this study, suppose that we are interested in the heart disease caused due to diabetes, and we are calculating, or we want to predict the incidence or the prevalence probabilities of developing a heart disease complication. The difference between the two is that prevalence is the number of population that actually has the disease at this moment, while incidence is we will be predicting for a future event. Suppose that the probability that patient without a disease develops a disease during a preset time interval. Now, disease scores have been started or have been initiated or developed from 1976, and most famous is Fleming heart study. There are others also, and these are all related to heart studies that are mentioned on the screen. Regarding diabetes, the first one was introduced in 1993 by Stern, and then after that, different scores, different prediction models have been developed worldwide in different countries. In India, we have two predictive models, and they are developed by Mohan et al. And Ramachandran et al. And they were both developed in 2005. And the main thing is that these two models that were developed in India, they predict the prevalence of diabetes, not the complications, but only the prevalence of diabetes. Now, because complications are so important, and they are so serious also that needs to be controlled. There are several risk scores that are specifically focused only on the complications, and we have different scores that only focus on stroke or renal disease, heart failure, and heart disease. There is also one on dementia and others that focus on diabetic nephropathy. The main methods, the main statistical methods are regression methods that are used to develop such prediction models. There are three types: linear regression, logistic regression, and survival analysis. The linear regression one is the most basic one, and logistic regression is used when we are only studying yes or no outcome variable, or an outcome variable which only has two variables. Survival analysis is another type of regression in which a time variable is introduced. The most common one is known as Cox proportional hazards regression. And the difference between logistic and this type of regression is that a time variable is introduced. So we have a binary outcome variable in which only two outcomes are possible, 1 and 0 if we quote them numerically, and another outcome variable in which we are introducing is a time variable. Suppose that we want to study that in the upcoming 3 years, how many patients actually develop this particular outcome. So the following equation is used in which the hazard ratios are estimated and a linear model based on that is calculated, and then the formula is given here. Now, following the regression methods, we have a set of diagnostic tests in which sensitivity, specificity are the most common ones. And graphically, we will be showing these results with an receiver or operating characteristic curve. Difference between sensitivity and specificity is that sensitivity.
Guys, I'm sorry to interrupt. You can skip all these basic definitions and come to your main finding.
Okay, all right.
Otherwise, you'll be consuming more time in these basic concepts.
Okay.
You can go to your finding.
All right. Okay, sir. So these results we will be using, and another one is a Udin's index, which we'll be using to calculate the cutoff value. The formula for calculating the t-year probability is shown here. Now, the main example which I want to show is that since we're focusing on the heart disease, I want to say that it is the most serious complication caused by diabetes, and it increases by 2 to 4 times in diabetic patients. We will be focusing, what we have done in this study is that we have verified or validated 2 separate risk models for heart disease that were developed. One was developed in Sweden and another one was developed in China. And these 2 models have both calculated the incidence probabilities of heart disease. The event of interest, we have taken our left ventricular hypertrophy, right bundle block, cardiomyopathy, infarction, angina, and etc. And in both of these studies, Cox proportional hazards regression was used. And the time taken, or the time which was followed, was 5 years. So in considering the Indian patients, we have collected a sample of 402 type 2 diabetes patients. And on this particular sample of Indian patients, we have verified or validated the 2 models from Sweden and China. Now, considering the Swedish model, this is already developed by the Cederholm et al. And these are the characteristics of the regression output found by them. Considering the equation, this is the 5-year risk. It considers age, duration, sex, duration, HbA1c, BMI, medication for hypertension, and lipid-lowering drugs as well. Now, considering the Chinese model, these are the characteristics for the regression output. And in equation form, these 2 equations will be used. The first one is the risk score, and the second one is the 5-year probability. Now, considering the Indian sample, this was the descriptive characteristics of our sample, in which out of 402 patients, 40 of them developed the heart disease in the followed up period of 5 years, and whereas 362 did not develop. The considered or the collected risk factors were age, sex, duration, HbA1c, and the rest of them are shown in the table here. Now, when we applied these 2 models on the Indian sample, the probabilities were determined as shown in the scatter plots in these 2 diagrams. The first one on the left is the Swedish model, while the second one is the Chinese model. The Chinese model, it can be seen that it is a bit more spread out and the probabilities are ranging on a higher basis. the ROC curves were calculated, and both of them can be seen that they're approximately the same. But we want to estimate that which one of the two models has a better fit on Indian patients. So regarding or considering the Swedish model, the ROC curve found an area of about 75%, and the optimal cutoff point was 7.3% with particular sensitivity and specificity values. Out of the 40 patients which had or which developed the heart disease, 75% were correctly predicted by the Swedish model, whereas the patients that did not develop or that were considered as the negative status patients, 65 were correctly predicted by the Swedish model.
Last 2 minutes.
Yes, sir. Now for the Chinese model, 74% was found as the area under the curve, and the optimal cutoff point was 33.2%. 57 positive patients were correctly predicted, whereas 80% of the negative status patients were correctly predicted. Now regarding coming to the conclusion, it can be seen that when we look at the ROC curve, both the models performed about the same. But the Swedish model predicted the positive cases better, whereas the Chinese model predicted the negative cases better. So both of these models can be used depending on which type of patients we are actually predicting, depending on the positive or the negative cases. And this is the type of work that I have done. And I just want to say that this is just a validation study, and we have already developed a particular or a specific heart disease model regarding for Indian patients, in which we have calculated the 5-year predicted probabilities of heart disease, and in which we have considered more risk factors, about 30 to 40 patients, or sorry, 40 to about 40 variables we have considered, and we have already developed that, which I have not shown here.
Thank you, Satish.
Thank you, Professor, for chairing this. Thank you, Professor Srivastava, for chairing this session in a nice way and concluded in time, in fact. There are also, on behalf of our society, ISPS, we would like to extend our gratitude to all the speakers, especially 2 invited speakers as well as the other 4 contributing speakers. And
who is assistant professor in Department of Statistics in Cochin University of Science and Technology. His area of research is distribution theory and statistical inference. I invite him to speak. Over to Irshad. You have 25 minutes.
Yes, sir. Yes, sir.
Yes.
Okay, good afternoon all. Today I am going to present a topic entitled on Muthu distribution and estimation of a parameter by use statistics. In this talk, first I am revisit a short history related to a forgotten probability distribution. Secondly, I have proposed some inferential aspects of the parameters of the distribution. So this is the outline of my presentation. So introduction. The baseline model under consideration has been first introduced by the French biologist Dixit, 1934, by considering mortality of several domestic animal species dying as a result of pure aging. Using empirical analysis of several species, the author discovered that animal mortality does not follow the human one as advocated by the Gomber's law. Lawrence, 1975, obtained an alternative version of Dixit's model and studied its several characteristics. Muth, 1977, discussed some additional properties of this model through Lambert's W function and observed that it displays heavier tail compared to the well-known lifetime distributions like gamma, log normal, and Hubble, etc. Later, Rinne, 1981, used this model to estimate the lifetime distribution for a German data set based on prices of used cars. For decades, this probability model has been forgotten until a short survey on univariate distribution relationship by Lewis and McCusker in 2008. They called this distribution as Muth distribution. After that, this distribution have been overlooked in the literature and no work is seen in the available literature till the work of Jodra et al. 2015. So, move on to the definition of Muth distribution. A continuous random variable Z is said to have a Muth distribution with shape parameter mu. Its probability density function is given in equation number 1, where mu is the shape parameter. This is the graph of the Muth distribution for different values of the shape parameter. One of the important characterizing property of this distribution is this mode of this distribution obtained in closed form, and it includes the golden ratio. That is, the golden ratio psi can be defined as the positive solution of the equation, quadrant equation this, and it is psi is equal to 1.6180, etc. So in the case of Muth distribution, mode is obtained in closed form and it includes the golden ratio. Further, Jodra 2015 considered its scaled version. Okay, then this scaled Muth distribution is a weighted version of famous Gomper's distribution with weight function Wx is equal to e raised to mu x by sigma minus mu, and normalizing constant expectation of Wx is equal to 1. Also, if x follows scaled Muth distribution, then this transformation e raised to mu x by sigma minus 1 follows a type of linear distribution. From these references, we observe the following. That is, the Muth distribution, the speciality of this distribution is the Muth distribution is the only probability distribution whose mode involves the golden ratio. It corresponds to the classical exponential distribution when the parameter tends to 0, that is, the shape parameter decreases to 0. Its probability mass in the right tail is less than those of the standard gamma, log normal, and viewable distribution. It satisfies the variate generation property, that is, the condyle function of Muth distribution is obtained in closed form. So, pseudo random numbers can be easily generated from the Muth distribution. Also, it satisfies mode, median, mean inequality. Next. There is no technical barrier to assuming the negative values of mu. That is, we can assume mu less than or equal to 1 also without changing the intrinsic nature of the Muth distribution. After the work of Jodra 2015, the study of Muth distribution has gained momentum in the theoretical as well as applied perspectives. In 2021, Visser et al. Studied inferential aspects of a geometry process with the scaled Muth distribution. An intermediate Muth distribution was proposed by Jodra and Arshad 2021. Sharma et al. Proposed exponentiated T-sub distribution, Muth distribution with Bartlett-shaped hazard rate function. Transmuted version Muth generated class of distributions were developed by Al-Bartain et al. 2020. Similarly, other notable works in the literature are Singh et al. 2021, Astrova et al. Since Aigawa 2021, and Visser et al. 2021, etc. Now we consider a data to establish the competency of the Muth distribution to some other well-known lifetime distributions. That is, the data set was taken from the Bureau of Meteorology of the Australian government. It is the rainfall data collected from January 2000 to February 2007. This is the data set. So next, we consider the maximal likelihood using maximal likelihood estimators of the parameter. Using the maximal likelihood estimator, we fit this data to Muth distribution So we consider the maximal likelihood estimators of the parameters of the distribution. As seen, as you've seen, this is MLEs are not obtained in closed form. This is the solution. Maximal likelihood estimators are solutions of these two equations. So we fit the data to Muthu distribution and estimate the parameters together with the K statistics and the p-value. Along with we fit gamma, log normal, exponential log normal, viewable, log logistic, exponential log. From this, it is seen that Muthu distribution performs well for this data set because the largest p-value and the smallest K statistics. Okay. While considering MLE, it ends up with some limitations. That is, when the sample size is small, maximal likelihood estimator, MLE is not even unbiased in many cases. Also, one may obtain asymptotic variances of the MLEs. The exact variances for the small sample cases are generally not obtained in combined form. In this case, the procedure of obtaining those, that is best linear unbiased estimators of the location and scale parameters of a distribution by order statistics is considered as a very effective method of estimation. So next we estimate the parameters of, that is the scale parameter of this distribution by order statistics. So that consider the vector x be the vector of order statistics of random sample of size m drawn from PDF. Define YRM is equal to XRM by sigma R is equal to 1 to m. Then YRM are distributed as the order statistics of a random sample of size m drawn from the standard Muthu distribution. Standard in the sense it is independent of the scale parameter. Let alpha be the mean vector and V be the variance covariance matrix of order statistics of random sample of size n drawn from this F naught Y. That is equation number 6. Then by using generalized Gauss-Markov setup, Gauss-Markov theorem, the best linear unbiased estimator of sigma involved in the PDF, namely sigma tilde, is obtained in this form and its variance is obtained in this form. From this, that is sigma tilde, it is again the class sigma tilde is equal to sigma ERM XRM, that is a linear combination of order statistics where ERM are the constants independent of sigma. Also, for obtaining this estimator, we want to evaluate the mean vector and the variance covariance matrix, of the order statistics arising from the corresponding standard form of the given distribution. We have evaluated those values, and using those values, we have calculated the coefficients of vector x in the blue and the variance of the best linear unbiased estimator. That is given in table. That is for different values of the shape parameter. These are the coefficients of the vector x in the best blue, and this is the variance. Okay. Okay, thus for small sample situation, the procedure of obtaining blue of a scale parameter by order statistics is very effective method of estimation. However, when the sample size is large, the computation of means, variances, covariances of the order statistics arising from the standard distribution leads Lloyd's procedure is very difficult. In this situation, Thomas and Srikumar 2008 proposed another method of estimation, that is by estimator based on U statistics. So I discussed some basic definition of U statistics. So this is the definition of U statistics. Let x1 to etc. xn be independent samples arising from a population with a CDF fx theta. The U statistics for the estimable parameter theta corresponding to the symmetric kernel h dot of degree m is given by equation number 9, where A is the set of alpha such that alpha 1 less than alpha 2 less than alpha n is one of the NCM combinations of m integers chosen without replacement from the set 1 to n. Also, this kernel is unbiased and is expectation of x square, xn is to etc. xn finite. By considering two random variables, exactly omega sample observations in common, then let psi omega m be the covariance between these two random variables, and the variance of the U statistic estimator is given in the variance of the U statistic estimator is given in this equation. Next, we consider by taking the Westlinger unbiased estimator of sigma is taken as the kernel, and then construct a U statistic estimator. That is U statistic estimator based on blue of sigma as kernel. Okay, let xn is to etc. xn be a random sample of size m arising from original distribution. The blue given in blue Westlinger unbiased estimator of sigma is also written in this form, where E1, E2, E2m, etc., EMM are constants. Now, by considering h of xn is to etc. xm as a kernel of degree m, using the results of Thomas and Srivar, the U statistics estimator based on this kernel of sigma is given in this equation, that is equation number 13. That is, this is the U statistics estimator proposed for the scale parameter of the Gupta distribution. So let psi dm be the covariance between these two random variables. Then the variance of this U statistics estimator is given in this form. Okay, clearly psi mm is the variance of the Westlinger unbiased estimator and is given in equation number 7. Now we evaluate the values of psi dm for d is equal to 1 to m minus 1 using the methodology developed by Thomas and Srivar as explained in the following steps. That is, next our job is the procedure of obtaining the values of psi dm. So define the vector b m plus k prime is this form. Then the expression for um plus k for k is equal to 1 to m minus n is obtained by putting n is equal to m plus k in 13. So um plus km is this, where xm plus k is this vector and its variance is obtained in this form, where vm plus k is the dispersal matrix of the vector of order statistics of a random sample size m plus k arising from the distribution of the PDF f naught y. Okay, it's the standard distribution. Consequently, we can write the matrix equation as this. So, if we write H to denote the coefficient matrix in the left side of 18, this equation, and W to denote the vector in the right side of 18, then we have this. Okay. So, once we obtain the values of psi dm, so from this we get the values of psi dm, this equation. Okay. Psi dm is actually included in the variance of the U statistics estimator. Okay. So once we obtain the values of psi dm, then the actual variances of the U statistic estimator for estimating sigma based on any sample size n can be obtained by using the variance equation, that is equation number 14. With this equation without any further direct evaluation of moments of order statistics. Okay. That is, if one obtains the blue Westlinger unbiased estimator as kernel based on sample size m, then the evaluation of variances or covariances of order statistics arising from the corresponding standard distribution up to sample size 2m minus 1 are necessary to obtain the explicit expression for the variances of the U statistic estimator, whatever is the sample size. Okay. For example, suppose the value of the given value of the parameter mu, that is given shape parameter, we use sigma tilde as given in 8 for m is equal to 5. Then the evaluation of moments of order statistics arising from f naught y given in 6 for sample size up to 9, that is 2m minus 1 sizes are enough. One can obtain the explicit form of appropriate U statistic estimator of sigma and their variances for any sample size n. Okay. Throughout this So next we evaluate some numerical values of the psi dm for d is equal to 1 to m to 1 to 5 for different values of the shape parameter mu. Okay. Next we consider throughout the procedure we assume that the shape parameter is known, but in real life data it is unrealistic to assume that the shape parameter assumed is known. Through this theorem, we propose an estimator for the shape parameter. That is, suppose x1 is to xn be a random sample of size n arising from tau. Let tau denote the sample correlation between xi and their ranks. Let kappa be the sample correlation coefficient of variation. Then an estimator for the shape parameter mu is obtained in this form. Proof. Simple proof. This is using the result of Stewart. The correlation between xi and their ranks Ri is tau is equal to this equation. After some simple algebra, this quantity is obtained is of theta minus sigma by h into mu plus 2. Substituting this in equation number 21, we get the required result. Next, we consider some comparison of U statistics estimator with some standard unbiased estimator. For that, first consider an usual unbiased estimator of sigma, namely sigma cap, and this is simply x bar, and its variance is obtained in this form, that is equation number 23. Next, we consider the relative efficiency of U statistics estimator with the unbiased estimator sigma. Also, we consider the asymptotic relative efficiency. So, the asymptotic variance of the U statistics estimate is given in this. Therefore, the asymptotic relative efficiency of U statistics estimate with the unbiased estimate is given in this. Now, we evaluate the numerical values of the U statistics estimator, asymptotic unbiased estimator, and the relative efficiency. From the table for different values of the shape parameter. From the table, it is observed that the variance of the U statistics estimator decreases as n increases. Also, the variance decreases the shape parameter, the value of the shape parameter mu increases. Also, the relative efficiency and in all cases exceeds the unity. That means U statistics estimate is much better. Also, as far as asymptotic relative efficiency is considered, it also exceeds unity and it increases with the increases in sample size. Sorry, increases in the value of the shape parameter. So this is the table. Next, consider the empirical illustration. For the empirical illustration, we consider the Kerala data, that is the rainfall data discussed in the previous slide. In this case, the value of the estimate of the shape parameter mu given in 20, that is the estimate of using this data, we obtain the estimate of mu as 0.43. This is actually close to the MLE of mu. Thus, by taking 0.43 as the node of the shape parameter mu, we have used the method explained in this paper to obtain U statistics estimators. That is, mu is equal to 0.43 as the node value. We compute the values of U statistics estimators for different kernels. These values are given in this table, that is for n is equal to 2, the value of the U statistics estimator, kernel size n is equal to 3, the value of the U statistics estimator, n is equal to 4 and n is equal to 5. Together with the K statistics and the highest p value. That is, from this we conclude that K statistics value computed based on U statistics estimate for each of the kernel are less than that computed based on the MLE method of estimation. That is, based on ML, yes, ML estimates, the K statistics are higher than these K statistics values. Also, P values are higher compared to the ML. Okay, so this is my conclusion. That is, this supports our claim that statistics estimators are highly efficient as they are unmasked and possess the optimal properties of both blue and those of statistics. So this is the conclusion of my work. That is, in this work we propose the statistics effectively propose the statistics estimator for the scale parameter of the Mukta distribution, as well as we compare the competency of the statistics estimator with the maximal likelihood estimator, and we conclude that the statistics estimator is much better in this case. Okay, so this is my conclusion. These are the references. Thank you. Sir.
Hello, Professor Pakala. Professor. Hello, Professor. Since there is a network issue with Professor Pakala, I hope anyone can ask questions or any clarifications needed. Please interact with it. Hello.
Sorry, there was a...
hello, Professor.
Yeah, there was
no
problem.
problem.
There was some network problem. Yeah. Any questions? I think he has answered some questions. I have a question.
Okay, sir.
Yeah. So, is there any condition? Could you derive any condition when MLE will be unbiased? Is it
no,
possible?
Here, in this case, MLE is not obtained in closed form, sir. So, yeah, that is the problem. So, we propose order by order statistics, statistics estimator.
Okay, empirically you can obtain in such cases. Yeah. Sorry, there was some network problem. Okay. Hope we can. If there is any question, if there is no question, we can move on to the next speaker. Is it all right?
Hello?
Someone has.
Can you hear me?
I think Professor Navarro is checking his mic.
Can you hear me? Good afternoon.
Good afternoon, Professor. Good afternoon, Professor Navarro. Just a minute, you please. Just a minute, you please wait, because the chair has some network issues. If there is problem, we can continue. No problem. Hello, Professor Pakala. Hello.
I think Professor Satish Kumar can invite Professor Navarro.
Actually, I have two connections, but I'm losing the connection. Okay.
Now you are ready. Okay, now you are ready.
Yeah. Okay. Professor George Nauro is a professor of statistics and operational research. He's in University of Murcia from Spain. Welcome you, sir. And his research area is reliability. Many areas are there: reliability, applied statistics, reliability engineering, multivariate analysis, sediments, distribution theory, and several such areas are there. Now, I request Professor George to deliver the invited talk. You have 25 minutes and plus 5 minutes for discussion. Over to you, sir. Yeah.
Okay, thank you.
Yeah.
Okay, is it visible?
Yeah. Yes.
Okay, thank you. First of all, I'd like to thank the organizer for inviting me to this conference. It is an honor for me to be in that conference and also in the birth centenary celebration of Professor Rao. The conference is based mainly on these papers. This is the outline of the talk. I'm going to show you first the usual concept of distorted distribution, which is the univariate case, with the definition and some example, and especially the application to systems. And then I will move to the new concept of multivariate distorted distribution, which is the main topic of the talk, with the definition, main properties, and how to apply to quantile regression predictions. I will show you some example if I have time at the end. Well, this is the notation. X is a random variable. This is the distribution function. This is the survival or reliability function. And this is the probability density function, the mean, expected lifetime in different ways, and the hazard rate, which is the ratio between the density and the survival function. The distorted distribution were introduced in the context of theory of choice and the risk, with the purpose to allow a distortion, a change of the initial or past risk distribution function. This is the formal definition. We say that this distribution function is a distortion of another. It can be written in this way, where Q is a distortion function, which is a continuous and increasing function from 0 to 1. Of course, if we change the distribution F, we obtain always a proper distribution function. So this is a way of obtaining different distribution function by changing the original one. If Q is strictly increasing, then both distributions have the same support. We have a similar representation in terms of survival function, this 1.2, with another distortion function, which is called the dual distortion function. Both expressions are equivalent, but sometimes it's better to use this expression instead of the other one, for example, in reliability studies. We can obtain the density from both expressions in this simple way, and we can also obtain the hazard rate, the connection between the new hazard rate and the original hazard rate with this function alpha, which is obtained from the distortion. This expression is used to study preservation of aging classes and to obtain also ordering properties for distortion distribution. This concept got extended in this paper as follows. We say that a function is a distortion of n univariate distribution function, fq, if it can be written in this way, with q is a distortion from this cube, n-dimensional cube, which is also increasing continuous and goes from 0 to 1. This is, of course, an extension of the preceding concept of a distortion with just one distribution function. Again, we can change the distribution function in that expression to obtain new distribution function here. Note that this is similar to a copular representation, but that this is a univariate distribution, and this Q is not necessarily a copula. So it is not a copula representation because we are in the case of univariate distribution. We have a similar expression for the survival function with another distortion, which is also called the dual distortion. And again, both expressions are equivalent, and we can work with one of them if we prefer. The density can also be obtained from both of them, but this is not so simple. And again, we can obtain the hazard rate, but again, it's not so simple. This expression is not easy as the one before. Let's see some example. The most popular one is the proportional hazard rate Cox model, which can be written in this way. So it is a distortion with this dual distortion function. The density is that one, and of course, the hazard rate of the distortion is proportional to the original hazard rate, as so is named. This is a very well-known model where theta is the risk parameter. It is not so well known the proportional reverse hazard rate, which is defined in the same way, but with the distribution functions. Here, the distortion is simple, but the dual distortion is not so simple. The density can be obtained in a simple way, but the hazard rate, the connection between the hazard rate is not so simple. We need this alpha function. Of course, the reverse hazard rate is proportional to the original one. Another important example is the case of order statistic from a sample of IID the random variables. The ordered values in that sample has this survival function, and so this is the dual distortion, and the original distortion can be obtained in the same way. Note that both are polynomials, so the distortion are really simple functions, and we can work with them in a closed form. Particular important cases are the case of the minimum, which is also the series system with IID components, which is this just the power of the reliability function, and of course belongs to the proportional hazard rate model. Hazard rate is proportional, and the same happens with the maximum, which belongs to the reverse proportional hazard rate model, and so the reverse proportional hazard rate function are also proportional. These results are very well known. In the case of generalized distorted distribution, the main examples are the mixture. We have n population and we mix them with some weights. This is of course, this expression holds also for the survival function. And so in this case, both distortion coincide, and it's simple, it is just a linear combination. We have the same expression for the density, but we don't have the same expression for the hazard rate, which is also a linear combination with some weights, but these weights depend on t. Let's see the last example, which is the case of general coherent system with arbitrary component which can be dependent. We will model the dependency with the joint distribution function of these random lifetimes, and with the marginal of each component. We are going to use the copula representation from Clark's theorem, which is that one, where C is a copula, and this copula is unique when these distribution functions are continuous. A copula is just a multivariate distribution function with uniform marginal over the interval 0, 1. However, we just need this copula in this n-dimensional cube. We have a similar representation in terms of the survival or joint reliability function with the marginals and with the similar Clark's theorem for the survival function with a copula which is called the survival copula. Note that this copula is of course a copula, it is a distribution function, and it is not a survival function. Okay, so the name survival copula means that it is a copula, not a survival function. Well, for example, if we choose the case of a parallel system, then of course the distribution function of the parallel system can be obtained from the joint distribution function just by using TTT. And so using the copula representation, we have this expression for any kind of dependency. So we have the generalized distorted distribution with the distortion exactly equal to the copula. Okay, so all the copulas are distortion function, but the reverse is not true. There are some distortions that are not copula. The same happened with the series system. In that case, we prefer to use the survival function, and the reliability function of the series system is just the survival function in the diagonal. And so, using the class theorem, we can obtain the reliability function of the series system with the survival copula at the margin. So the dual distortion is the survival copula. Okay. In general, it can be proved that the lifetime of any coherent system, the reliability of the lifetime of any coherent system, can be written as a generalized distortion of the component reliability function. This distortion depends on the structure of the system and on the copula. That is the dependency structure between the components. This expression is very convenient in practice because we have here in Q the distortion, all the information about the structure of the system and the dependency between the component, and then we can change the kind of component. I mean, we can change the reliability of the component by changing, for example, the engine in a plane or the wheels in a car and so on. But the structure is the same, that doesn't change. I mean, the proof can be seen in that paper, for example. We have particular cases from that one. If these components are identically distributed, possibly dependent, then this can be reduced to a distortion representation, with the distortion being equal to the diagonal section. And in a more particular case, in the IID case, this distortion is a polynomial. Actually, the coefficient in that polynomial are the minimal signature coefficient, and in the original distortion are the coefficient of the maximal signature. This signature have been computed. In this table, we have the minimal and maximal signature of the system with 1 to 4 components, IID components. And there are also computed for system with 5 and 6 components. Okay. Note that some system can have the same signature. So in the IID case, they will have the same distortion and the same loop. Okay. These representations are very useful in terms of comparison of system and also to study the preservation of aging classes. In that paper, for example, can be seen the result for comparison in the IID case, and in that paper, the comparison for non-IID case, that is heterogeneous components, and in that paper, the result for preservation of aging classes. Now, I'm going to move to the second part of the talk, which is the main topic of the talk, which is the new concept of multivariate distorted distribution. This is the notation. Again, we have a random vector with this joint distribution. I will have the copular representation for this joint distribution in terms of the margin. Sometimes it is not easy to obtain this copular representation because the copula is complicated or even the marginal are complicated. So what we want is to obtain an alternative representation for this distribution that doesn't use marginals and doesn't use the copula. Well, the same can be applied to the joint reliability function. Okay, this is the definition of the multivariate distorted distribution. We say that the n-dimensional distribution function is a distortion of n univariate distribution function, not necessarily the marginal. It can be written in this way, which is exactly the same as the copular representation, but here D is not necessarily a copula, and G1, Gn are not necessarily the marginals. Here D is what we call a distortion, which is defined here. We say that this function is a distortion, is defined in this n-dimensional cube. At 0 is 0, at all the ones is equal to 1, and it is n increasing. It can be extended to Rn, and in that case, it will be a distribution function n-dimensional distribution function with supports included in this set. This is the simple definition of a distortion function in the n-dimensional case. According to Isps-Kup theorem, as we have seen, any multivariate distribution can be expressed in terms of the marginal and a copula. And this representation is essentially unique when the marginal are continuous. We have a similar Isps-Kup type theorem for these representations, which is given in that proposition. If we have a joint distribution function and arbitrary continuous distribution function, which just we assume that they are strictly increasing in the support of the variables, then there exists a distortion, unique distortion in this set, the set of distortion of dimension n, to breed the joint distribution in that way. So note that we can choose the G's, and then with the G's fixed, we can get a distortion. The converse is also true, and actually we can use this expression to obtain new multivariate model when we fix a distortion and we change the univariate distribution. It is similar to the copula one, but in a more general case. We can obtain the distortion from the copula using this representation. We just need the inverse of these G distribution functions. And as we choose them, we can choose simple one with the inverse in a closed form. We can do the reverse. We can obtain the copula from D, but it is not so easy because we need the inverse of the marginals, and the inverse of the marginal are not so easy in several cases. Note that C is also the copula of D, and so D has all the information about the dependency structure as the copula. We have a similar representation for the joint reliability function with another distortion, which is called, again, the dual distortion, as in the univariate case. And a relevant property of this representation is that all the marginal are also distortion. For example, the joint distribution function of the first m random variable can be obtained in this way with this distortion, which is obtained from the original one just by adding ones at the end. So it is quite simple to obtain the distortion of the marginals, and in particular, the distortion of the univariate marginal is obtained just by putting ones in the other variables. So the distortion is simple, and the GIs are equal to the marginal if and only if this distortion is equal to U. But this is not always the case. And so the distortion representation is more general than the copular representation. It is well known that the density can be obtained by the partial derivative of the joint distribution function. So we can do the same in the distortion representation to obtain the density in this way, just with the partial derivative of the distortion function. So it is simple to obtain the density. And the same happened with the conditional distribution. All of them are distortion too. For example, we consider this one, which is what we need to do quantile regression. It's the conditional distribution of x2 given x1, which can be obtained at a distortion of G2 with this distortion in a closed form with the partial derivatives of the function D, and with this mild condition about a limit of this partial derivative. We also need this condition because we need the existence of this conditional distribution. So we can obtain the conditional distribution in a closed form, and so we can obtain quantile regression, as we will show you in the next slide. We can also obtain the mean regression curves to predict x2 from x1. We just need to obtain this expectation with this integral, where the d21 is just the derivative of the other distortion. Here, the problem is to do the integral. However, we can instead use the conditional median regression curve, which is just the quantile, the conditional quantile of this distribution, to this purpose, we just need to use 2.6, the preceding expression, obtaining the inverse of G2 and the inverse of the distortion in a closed form or using numeric procedure. So it is easy to obtain that, and even more, we can obtain confidence band for that estimation with 2 quantiles, for example, with a confidence alpha. For example, we can obtain center at 50% and 90% quantile confidence band using these quantiles. It is the same because it's just to change skew if we are able to compute the quantile. Let's see some examples. The first one is the origin of this. The representation is the case of residual lifetimes. The residual lifetime of a random variable is that vector, and it is well known that this is the reliability function of that residual lifetime, and this is the mean residual lifetime is a well-known function. However, we consider a random vector with the component lifetimes with a common time, and at time t, all of them are working. What we have is this random vector. This is the joint reliability function of the random vector, and it is not easy to obtain a representation for that vector. For example, the copular representation is really difficult. However, we can obtain a distortion. We can represent this reliability function as a distortion of the univariate reliability function of the residual lifetimes, just with this simple distortion, which depends on t. Okay, so the representation is simple. Note that here, these reliability functions are not the marginal of this random vector. The marginal are that one, which are more complicated when we have dependency here. So what we have is not a copular representation because it is not based on copulas, and we don't have the marginal, and so it is not always a coupler. In the case of exponential, we can replace that one with that one because we have the lack of memory property. The second example is the case of ordered paired data. We have two paired data, for example, lifetime of lungs or kidneys, eyes, etc., with the same distribution. So we have a copular representation. We can also assume that this is copular permutation symmetric, but we don't need it. We just need that they are identically distributed. That what we call ordered paired data are when we know L, which is the minimum, and we want to predict the maximum. That is, we know when the first failure occurs, and we want to predict the second failure. So we need this distribution, this conditional distribution, in order to use median regression and confidence. In some cases, we can assume that we have a training sample from X and Y, but in other cases, we just know the first failure and we want to estimate the second one. Of course, we are going to need to estimate F and C or parameter in that functions from the training sample. So what we need is a multivariate distorted distribution representation for L and U in terms of this F and C. And this is quite simple. With simple algebra, we can obtain the joint distribution of L and U, which is given here. And so, as you can see, that distortion of based on F, the same distribution, F and F, the original distribution of X and Y, with this distortion function, which is quite simple in terms of the couple. These are the marginals, which are obtained just by putting ones here. And in the particular case of independent random variables, we obtain that distortion, as you can see, are not equal to U. So we don't have a distortion, a copular representation, but a distortion representation. This is the distortion in the case of IID, in the IID case. So we can obtain the regression, mean regression in terms of the quantile by using this expression shown before, with this expression in the general case and this expression in the changeable case. Finally, the third example is the case of coherent system, which for any pair of coherent system can be written in terms of the original distribution function of the component when they are homogeneous, they are identically distributed. in particular, it can be applied to K out of n system. This order statistics with dependency or with the IID case included. And of course, to series and parallel system, which is the preceding case of ordered paired data. I don't know if I have time. I will show you some application to quantile regression. I think I have 5 minutes.
You can take 2-3 minutes. Yeah.
Okay.
Yeah.
Let's see the IID case. Then we have a sample from a random vector, and we have the minimum and the maximum. And note that even if the original are IID, this minimum and maximum are dependent. So we obtain the distortion as saw before. This is the closed form, and we can obtain the mean regression. This is the sample from X and Y, which are independent. But when we take the minimum and the maximum, as you can see, there is some dependency, with a weak dependency. The regression, usual linear regression doesn't work here. But we can obtain, as show you before, the distortion, the inverse of the distortion function. And so the exact quantile regression curve is that one for the exponential, with the exponential reliability. We can do the same with other reliability functions. And this is the centered confidence band. And we can also consider lower confidence band where X and as a fixed point on the left. Then we can control the data in this way. In the left, we have a centered confidence band. Red one is the median regression curves. In the blue, dark blue, we have the 50% confidence band. And in the light blue, we have the 90% confidence band. And we control the data in a good way. Here we have the lower or the bottom confidence band. We have the 50% here from the actual data and the 90%. And these are upper to the 90% quantile. We can predict, for example, the first data. The first data are 10 and 14. And with the median regression, we obtain 17. It is not a good prediction because of the variance, but we can obtain confidence band for that value, which are better prediction ways. We can do the same in case of dependency, but I think that I don't have time. With a copula, here we have a Clayton copula, and we can do the same. And we'll show you just the plot. This is the algebra, and we have similar curves in that case and no lines with the confidence band in a closed form in both cases. And we can also use estimation for the parameter in the copula or in the distribution. For example, in that case, in the IID case for the exponential, we estimate the mean, and we obtain good approximation in practice. And we can do the same when we have a parameter in the copula by using, for example, the Kent-Antal coefficient. Finally, we can also use the library of quantile regression to obtain estimation of these exact curves as shown in these papers. These are the curves obtained with this package in the statistical program. These are the reference, and that's all. Thank you for your attention.
Okay, thank you. If there are some questions from audience. Yeah.
Professor Navarro, this is from kitchen. Actually, most of this distorted distribution, the distributions are either IID or ID. So, how do you comment on that?
The IID assumption is not crucial here. We can assume the IID assumption to obtain the distortion distribution, but we don't need to do that. Even more, we can also drop up the ID assumption. We can consider different distribution, but of course the distortion are more complicated. However, in the case of paired data, for example, with lungs, kidneys, and so on, or even engines in a plane, I think that to assume that the distribution is the same is reasonable in practice.
I agree.
I think so.
So most of these reliability systems, we are assuming is either ID or IID concept most of the time.
Yes, I think so in practice, but it is just the first step, and it is a and let's see what happens in the future. I don't know.
Okay, it was a nice talk and quite informative.
Yeah. Thank you, Sunak. Thank you.
Yeah. Any other questions? Is there any applications other than in reliability? These can be used in some other area as well?
Yes, I have a second paper which is almost accepted, which is about record values. This technique can be applied to record values, can be applied to order statistics, can be applied to sequential order statistics. The one record is already done, but the other are up to future investigation.
Okay. Thank you.
Thank you.
Thank you for your nice talk. Okay.
Thank you. Welcome.
Okay. And now next is contributory. I'm sorry. So we have 6 speakers. I just want to find out if all of them are here. I'll just call their names, and afterwards you can give the presentation. First of all, Bindu PP is here.
Yeah.
Yes. Then Subhadrav Desen. Subrat Dev Sen. Subrat Dev Sen, right? Is he here?
He is here. Yes, raised his hand. Yeah, please raise the hand. That facility.
Shreyasi Basak?
Yes, sir.
Yeah, yes. Then Fasana K?
Yes, sir, I am here.
Yes. Then Sirisha?
Yes, I am here, sir.
Yeah, yes. Then Faiza Rehman?
Yes, sir, I'm here, sir.
Yeah, okay. All of them are here. So let us start with the Bindu PP. So she will be delivering on skewed double exponential distribution, extended exponential distribution and its applications. Okay, you can take 12 to 13 minutes and 2 minutes or 3 minutes for discussion. Over to you, Bindu.
Good afternoon, one and all. Am I audible?
Yes, audible. You are audible.
Good afternoon, one and all. Myself, Dr. Bindu PP, Assistant Professor, Department of Statistics, Government Arts and Science College, Kerala. Today, I would like to present the paper on skewed double extended exponential distribution and its application. And this is the skewed generalization of double extended exponential distribution introduced by myself. This distribution is capable of handling multimodality and asymmetry also. And you know that recently there is an increase in interest in developing more flexible distributions that could describe skewness, kurtosis, multimodality, and heavier tails observed in the data. And since we know that in many studies, the regression error distribution need not follow Gaussian law. Because of this, there is a lot of interest in introducing new skew symmetric and heavy-tailed or multimodal family of distribution. And the construction of this distribution is basically using the method introduced by skew symmetric distribution introduced by Assalini 1985. I made use of this lemma, and I introduced the asymmetry in symmetric distribution F using the equation given in equation number 1. And I have used another here. In Assalini's paper, he took F as the normal and then capital G as the CDF of normal. And there are several generalizations of these skew-symmetric families are introduced by various authors. And one generalization is by taking the queuing function G as a queuing function which is a Lebesgue measure function, which take values between 0 and 1, and also this is a continuous function g of x such that g of x plus g of minus x equal to 1 almost everywhere in the R. And Chakravarti et al. in 2012-13 introduced multimodal skew logistic and skew normal distribution by considering periodic trigonometric skewing function. In this present study, I used g of x as this trigonometric skewing function and introduced today's work is based on that work. And regarding the extended exponential distribution, this is actually this positive range random variable extended exponential distribution is introduced in 2014 by Gomez et al. And in the present study, first I will introduce the extension of this to the entire real line, and I called this as double extended exponential distribution. And this is the PDF of the extended exponential distribution introduced by Gomez et al. In 2014. And I have extended this to the real line, and we can see that this distribution is a generalization of the Laplace distribution. And this is the equation number 4 give the CDF of the double extended exponential distribution, and these the plots of double extended exponential distribution for various values of the parameters. Here are two parameters, beta and gamma, and here if gamma equal to 0, this distribution is reduced to the standard Laplace distribution. And for the value of gamma between 0 and 1, the distribution is unimodal, and bimodal for values of gamma greater than 1. And this is the plot of the CDF. I have plotted for a value of gamma between 0 and 1 and greater than 1. And from the plot also, we can see that gamma equal to 0, this distribution reduced to Laplace. And also from the earlier figure, we can see that for gamma greater than 1, we have bimodality also. And the mode again, the multimodal if bimodal for gamma greater than 1 and gamma not equal to beta. And this is Condell. I have derived the Condell function to generate sample from the DE distribution. This is the survival function, and this is the expression for the hazard rate function. And I have plotted hazard function and also computed the reverse hazard function and computed mean various properties of the reliability measures related to these distributions. And also have computed the moments also, ortho moments. Since it is a symmetric distribution, odd order moments 0 and even order moments are given in by the equation number 11. And then I have computed the variance and fourth moment. And also I have derived the absolute moment also, expression for the Rth absolute moment, and also derived the expression for the moment generating function, and also characteristic function, and also computed the coefficient of kurtosis, and also the entropy measures related to this distribution. And also I have studied the order statistic for this family of distribution, double extended exponential distribution, and also computed the Rth moment, kth moment of Rth order statistic. It is given by this expression. And maximal likelihood estimation. For maximal likelihood estimation, I use the R package by directly maximizing the likelihood function, not by solving the equations. We are using the optimum function. I directly maximize the likelihood function in the R package. And now I introduce the skew double extended exponential distribution, and this distribution we have this is 4 parameter distribution, alpha, gamma and alpha. Is capable of introducing the gamma. This distribution is already bimodal, and additional alpha will introduce trimodality also. The alpha parameter introduced in this study lead to the multimodality of this distribution. Lambda is the skewness parameter. Beta is the scale parameter. And I have plotted the graphs of the skewed double extended exponential distribution, and from the graph I have plotted for gamma lies between 0 and 1 and gamma greater than 1. For gamma greater than 1, we can see that the distribution also have trimodality also, and for depending on the value of alpha. For alpha equal to 1, we can see that the distribution has trimodality also, alpha 1 and 2. And I have studied some properties. I have derived several properties, but not included. Only few properties of this included. And I have studied this distribution is invariant under scale transformation, just like skew symmetric distributions. And also, if lambda equal to 0, the distribution reduced to the double extended exponential distribution. That means the lambda is the skewness parameter. And also, if alpha tend to infinity also, the multimodality parameter alpha tend to infinity, this distribution also reduced to the double extended exponential symmetric version. And again, I have showed that this distribution, extended exponential, is also a special case of this distribution. And from this result, we can see that if you transform this as absolute value of x, the half double skew double extended exponential distribution is same as the extended exponential distribution. And I have, for the data analysis purpose, I have introduced the location parameter. Now I have defined the 5-parameter distribution, and a maximum likelihood estimation procedure is used to estimate the parameters. And I have directly optimized the likelihood function using the de-optim function of using the BFGS algorithm. And I have, for application, I use the faithful data set by taking a subset of that, the long data set that is selected.
Maybe within 1 minute or 2 minutes?
Okay, I will conclude, sir. Eruptions greater than 3, I has for application, I have taken that as, and for comparison, I used the asymmetric Laplace and also the skew multimodal Laplace distribution for comparison. This distribution introduced in this paper is an extension of the skew multimodal Laplace distribution. And this is the plot of the long data set. And the red one indicate the intensity introduced by myself, skew double extended exponential distribution. And the green dotted line is the skew multimodal Laplace. And the blue dashed line indicate the asymmetric Laplace distribution. In the table, I have given the estimated value of the parameters, and AIC value is lower for skew double extended exponential distribution compared to skew multimodal Laplace distribution. And AIC value is, and also computed the AIC and BIC using this formula. And you can see that the AIC value is least, that is 187.125 for the skew double extended, and compared to the asymmetric Laplace as well as skew multimodal Laplace distribution. And in this paper, I introduced an extension of the extended exponential distribution by reflecting it to the extending it to the real line, and also introduce asymmetry. And this distribution is capable of modeling asymmetric data as well as multimodal, asymmetric and multimodal data set. These are the references.
Okay. Okay.
Thank you, sir. Thank you.
Yeah. Any questions? One or two questions?
Professor Pakala, I have two things.
Yes.
I could not see the first two slides, but this is an interesting distribution in the sense that like normal distribution, this is a symmetric distribution having both negative and positive part.
Yes.
And this has, I think, like a normal distribution, some specific application, regression analysis and time series analysis. Bindu, can you try to develop some application in that direction?
Yeah, I am trying for, yes, sir.
Regression analysis or time series analysis.
Yeah.
Especially in the case of unimodal.
This distribution has application in biology studies, RNA sequencing data, and one of the problem is I don't have much time because of the teaching and other work, and because of this conference, I am very much
then not for the conference, next, whatever.
Yes. Yeah, thank you, Shankaran sir. Very good suggestion. Thank you very much.
Yeah, Professor, thank you. Yeah, thank you. Any other? Otherwise, let us thank. Okay, thank you, Bindu.
Yeah, thank you, sir.
Okay, we'll move on to the next speaker. So, next speaker is Shubhradev Sen. Okay, his topic is the circular version of X gamma distribution problems and applications. Okay, you have 30 minutes. Oh, yeah. Yeah.
Good afternoon, sir. Good afternoon, Shankaran, sir. I think I'm audible, sir, properly?
Yeah, you're audible.
Yeah, thank you. Professor Shankaran, good afternoon. I'm Dr. Shubhradev here to present my research work related to... is my slide visible, sir?
No,
not yet. Not yet.
No. Slide is not visible.
Okay.
You present it now.
Is this now visible, sir?
Yes.
Yeah. So this is the circular version of X gamma distribution, its properties and application. This is myself, Dr. Shubhradev, along with me, Dr. Hazem and Dr. Mohammad Zanoon from Jordan participated or collaborated for the study. This is typically, I will just go line with an abstract, calling that this technique of wrapping we have utilized for an univariate probability distribution, which is very effective tool in getting the circular form of underlying density. In this article, we have introduced a circular or a wrapped version of X gamma distribution. X gamma distribution was introduced by myself and others in 2016. And we have studied in this particular paper different distributional properties of this wrapped form, and such as characteristic function, invariance properties, distributional function, central and non-central trigonometric moments, and related measures. To estimate the unknown parameter, for the time being, we are proposing maximum likelihood method. And a Monte Carlo simulation study is also performed to understand the behavior of the estimates for varying sample sizes. To illustrate the application of the proposed distribution, two different data sets are analyzed, which are circular in nature and compared with other circular distribution available in the statistical literature. As a first illustration, data set on long axis orientation of feldspar laths in basalt rock is taken, and the second data set is taken on the mean unit vector of NNR daily wind direction of 10 meters from period of October 2005 onwards. For the south burning sea is recorded in degrees. So these are the two data sets we have analyzed for the proposed wrapped version of X gamma distribution. So let us formally start with the presentation outline with this way. So I will give a small brief summary of what X gamma distribution is. X gamma distribution was introduced by myself in myself and others in 2016 for modeling lifetime data set. Subsequent works on X gamma distribution along with its different variation is going on. For last 5 years, this particular distribution is gaining popularity in the field of reliability and survival studies as well as modeling time to event data sets. For more details, we can see Sen and Chandra, Sen and others, and Jadhav et al., Maiti and others, Altun and Hamidani and Altun et al. In 2021 for different aspects. So X gamma distribution is having a density in this particular format, and this is a univariate distribution with having a single unknown parameter lambda which regulates the shape of the distributions as well. Now this X gamma distribution is typically having this kind of cumulative density function, much resembles with the Lindley distribution. So I have done a recent study on comparing Lindley and X gamma distribution, and different aspect of that is also been studied. We have some discrimination analysis has been done on these aspects, whether for a given data set X gamma has to be selected or Lindley has to be selected. Now for the circular or wrapped version of X gamma random variable, we have taken a random variable called theta, which is equivalent to x mod 2 pi, such that the theta belongs to 0 to 2 pi. The PDF can be derived with this particular format, and this is the format of the PDF as a z theta. Finally, we define a circular random variable theta belongs to 0 to 2 pi is said to follow a wrapped X gamma distribution with parameter lambda greater than 0 if its PDF is of the form this. And we denote it with WRXG lambda. So we have a single parameter here as a lambda which is unknown, and theta follows that. Theta is a circular random variable. For different values of lambda, we have plotted the density curve, and which goes in this direction. So this is the circular X gamma distribution plot. This is a probability distribution function, density function, and this is cumulative distribution function for the wrapped version. We also have what you called a zoom view, or you can call it a top view of the circular version or the wrapped version of X gamma distribution as given here for a different value for the parameter as 0.1, 0.5, and etc. When lambda is greater than 1, it goes into a circular version in touching the axis in the circumference. Distributional property wise, we have studied cumulative distribution function, which has this following format, and then we have also seen that depending on the Muster and Tenio and others, the circular distribution WRXG has the property of invariance under changes of initial direction and the property of invariance under changes of system orientation as well. Only thing that for a given delta for all eta in 0 to 2 pi, there exists a lambda star such that the wrapped X gamma to theta and lambda and wrapped X gamma and delta theta minus zeta lambda star for all theta belongs to 0 to 2 pi. So we have seen that WRXG is not ICID and ICO. It is enough to find a particular random variable theta in that range to 0 to 2 pi, and there is no lambda star satisfying this particular equation then. So in that sense, they are invariance in the particular parameter lambda. Characteristic function wise, by Rao and Sengupta 2001, the trigonometric moments of order P for a wrapped distribution corresponds to the value of the characteristic functions of unwrapped random variable, that means univariate random variable x, say phi xt, at the integer value P. So phi theta P, which is a characteristic function of the wrapped distribution, is same as phi xp actually. So this was the characteristic function of x gamma distribution found by Sen and others in 2018, and this is the form for the characteristic function. When this has been transformed by Sengupta's formula, we got the characteristic functions of the wrapped version as phi p theta with this particular form for p's plus minus 1, plus minus 2, etc. This is some characteristics we have tabulated from the particular forms we obtained. This is a mean direction, resultant length, circular variance, circular standard deviation, non-central trigonometric moments. I have not shown here in this particular presentation the mathematical forms of those. Rather, I have shown it for different lambda, how that behaves. Obviously, mean direction changes as lambda increases. Similarly, resultant length also increases as lambda increases, and so on. Coefficient of skewness, coefficient of kurtosis. So these are as a whole the value of different characteristics of wrapped x gamma distribution for varying lambda. As a parameter estimation, as I have told at the very beginning of the abstract, that we have proposed for the time being as a maximum likelihood method of estimate, but further methods will be also investigated in due course of time. These are the theta 1, theta 2, theta n, be a random sample of size n drawn from wrapped x gamma lambda. Then the likelihood function goes in this way. Definitely the particular lambda cannot be estimated with a concrete format here. We have utilized our software or numerical methods to do that, and the maximum likelihood estimates are being obtained for different values of lambda for 0.1, 0.7, 1, 2.5, 4, and 8, and different sample sizes 30, 80, 100, 200, and 350 also been taken as a simulation study with 10,000 generation of the samples. And we have tabulated bias, mean square error, and mean relative estimates, and this is the simulation result, which shows obviously very good result as lambda increases. Definitely with the different variation of lambda, as the sample size increases, the bias decreases and the estimate gets closer to the actual value. Coming to the application part, this section encompasses the application of wrapped x gamma model to illustrate the modeling behavior on real life data sets. We have taken two data sets. This is a glaciologist data in which glacier related stone, pebbles, and rock deposited by the receding glacier has been selected. The data thus collects a special kind of circular data, popularly known as axial data. And to illustrate the applicability of wrapped x gamma distribution, this data has been analyzed, which is available in circular package of our software, also reported by Agostinelli and Land in 2017. This dataset contains the measurements of long axis orientation of 164 feldspar laths in basalt rock. It contains 60 orientation observation recorded in degrees. We, along with that particular ML estimate, for a comparison, we have taken wrapped Lindley distribution introduced by Joshi and Professor K.K. Jose in 2018, wrapped exponential distribution by Jamalanka and Kuzugoski in 2004, and we obtained this as a model with a -2 log likelihood, AIC, CAIC, BIC, HQIC, Watson statistics, and Ks value and K statistics and P values, in which wrapped x gamma showed a very nice result, obviously in terms of AIC, BIC, etc. For a data set 2, the illustration is done in the applicability of wrapped x gamma distribution. We analyzed the wind direction data reported by Varun Mastrelli et al. In 2019, available within the website of this address. This data represents the daily mean unit vector of in and out daily wind direction at 10 meters from period of October 2005 at southern Bering Seas. The ML estimation corresponds to standard error of the parameters of the wind direction data set for the wrapped x gamma theta, with 4 well-established distributions of wrap type are being also compared, which are nothing but John Perucci distribution, wrapped normal distribution, wrapped Cauchy distribution, and von Mises distribution. And this is the result obtained at the final stage of the data analysis, in which wrapped x gamma showed a very successful result in comparison to the other comparative models. So that's all for my conclusion. That's all for my conclusion, that we have found that the wrapped x gamma can do as a better circular model than many of the particular circular distribution available in the literature, but definitely for the distribution, parameter estimation part, we need to concentrate more. Thank you very much.
Okay. Is there any questions from the participants? Maybe quick. Yes.
This is very interesting, actually, new circular distribution. And X gamma distribution itself is a new distribution because it has been introduced as a mixture of exponential and gamma distribution.
Right.
I have one doubt here. Actually, you have taken the parameter of the mixing also as the parameter of the distributions. Both the distributions are based on theta, and the mixing parameter is also that the weights, that is theta by 1 plus theta and 1 by 1 plus theta.
Yeah, Shomesh sir, you are talking about the x gamma distribution.
Yes,
right?
yes.
Okay, yeah.
So, what is the logic for that? That if you are
no, actually, during that synthesis of the x gamma distribution, I followed the route followed by Professor Lindley in synthesizing the Lindley distribution. So same pattern actually I have taken, and it worked nicely. So there was no logic of doing that. Although I know that any particular parameter, when it is taken and based on the estimate, when we talk about the shape itself should not be taken as the weights, but since it is a weighted measure, I found it very realistic sometimes.
Okay, and my second question is just related to this itself. So you have actually given that maximum likelihood equations, likelihood equations for solving this one. So what if we actually do separate estimation and do some sort of plug-in, because better estimates for exponential as well as for gamma are available. So it is something like combining. So if we can do that, is it possible? Has it been tried?
I have not investigated yet. I will look into that. I will look into that. Yeah.
Thank you. Yeah.
Thank you, sir. Thank you, sir.
Okay. Thank you.
Thank you, sir.
Okay. Let me invite next speaker, Shreyasi Basak. She will be talking on estimating the mean direction of the wrapped Cauchy distribution.
Yes, sir.
Yeah. You can presentation. Yes.
So good afternoon, everyone. I'm Shreyasi Basak. Today I'm going to present my talk on the topic of estimation of the mean direction of a wrapped Cauchy distribution. So this is the joint work with Professor Shomesh Kumar and Kanika. So this is my outline. First, I will introduce this distribution. Then I will evaluate the Pitman estimator of a rotationally symmetric distribution. Then I will evaluate the Pitman estimator of a wrapped Cauchy distribution. Then I will study the simulation study between 3 estimators of wrapped Cauchy distribution. And lastly, we will talk about the robustness properties of the wrapped Cauchy distribution. So the motivation of using the circular distribution is that we have considered the wind data set, which represent the wind direction of a particular place, which is known as Col de la Rua, and these measures are this wind data measures the wind direction every 15 minutes from January 29, 2001 to March 31, 2001 from 3 am to 4 am. And if we plot the linear histogram of this dataset, then we can see that there is actually a bimodal histogram. But if we plot a circular histogram like Rose diagram of this dataset, then we can see that there is actually a periodic nature of this data. So in the linear histogram, this periodic nature is not taken care of. So this is the motivation of fitting the circular distribution of these on this particular data set. So fitting of circular distribution on these type of data sets will be more appropriate. So in the introduction, we can say that standard statistical techniques cannot be used to model directional data due to its different geometrical structure than Euclidean data. Several techniques have been used for modeling directional data. One of the well-known approach is the wrapping approach. Several well-known circular distribution can be obtained by wrapping the corresponding linear distribution on the linear line over the circumference of a circle. Some well-known wrap distribution are wrap normal, wrap Cauchy, wrap double exponential, etc. And the wrap distribution can be obtained by wrapping the corresponding linear distribution on the circumference of a circle. And the density of a circular random variable which follows a general rotationally symmetric distribution on the circle has the form proportional to f of cos of theta minus nu, where nu is the direction of symmetry. And the mean direction of directional data is not the usual mean direction, and mean direction is defined by this formula tan inverse of s by c. And for estimating the nu by delta, the loss function is defined as the circular version of the square error loss function, which is given by L1 of nu delta 1 minus cos of nu minus delta. Now, next, we have also considered the robustness properties of a wrapped Cauchy distribution, and we concentrate on the SB robustness property of the mean direction of a wrapped Cauchy distribution. An estimator is defined as B robust if its norm of influence function is finite, and SB robust if the standardized influence function is norm is finite. We will show that the directional mean is B robust but not SB robust for finite dispersion measure for a wrapped Cauchy distribution. So to find the PDF of a wrapped Cauchy distribution, we have first considered the Cauchy distribution on the real line, and after that we have wrapped this distribution on the circumference of a circle, which is given by equation number 4. And after some algebraic manipulation, we have found the closed form density function of wrapped Cauchy distribution, which is given by equation number 5. And this is the literature review of our work. In the year 2011, Laha and Mohesh derived the robustness of the directional mean for different families of circular normal distribution. They showed that the directional mean is not SB robust for some family of circular distribution. In that case, they derived circular trend mean to prove SB robustness of that family of distribution. They introduced the concept of equivalent dispersion measure and proved that if an estimator is SB robust for one dispersion measure, then it is SB robust for all equivalent dispersion measure. In the next literature review, Laha also proved the SB robustness properties of various estimators of mean direction and concentration parameter of wrapped normal distribution. So our main mark is dependent mainly from the extension of this work from these 3 papers. So this is the main theorem of our work. If we consider theta 1, theta 2, theta n be n random sample from a rotationally symmetric distribution, then the Pitman estimator for the circular location of such distribution will be given by tan inverse of ratio of 2 integrals, where f of theta 1 minus nu, theta 2 minus nu, and theta n minus nu is the joint probability density function of theta 1, theta 2, theta n. So this is the detailed proof of this deriving this estimator. So to prove this, we have considered the group of transformation G, which is given by G alpha. G alpha theta is given by theta plus alpha mod 2 pi. So this is the to prove this, we have first considered a rotation equivalent estimator of the circular location nu, which will satisfy the rotation equivalent property of circular distributions. And after this, we have found the form of a rotation equivalent estimator, which is given by equation number 7. And to found the Pitman estimator of a rotationally symmetric distribution, we have to minimize the risk of the loss function. We have to minimize the risk of the loss function, and to minimize this risk of the loss function, we have considered the conditional density of theta 1 given phi at nu equal to 0, which is equivalent to the conditional density of theta 1 given theta 2 up to theta n at nu equal to 0. And conditional density is, we all know, it is given by joint density divided by marginal density, which is given by equation number 12. And after some algebraic manipulation, we have found the final derivation final expression of the Pitman estimator of the circular location, which is given by delta star. And using this form of this Pitman estimator of a rotational symmetric distribution, we have found the Pitman estimator of a rapt Cauchy distribution. Since we all know the rapt Cauchy distribution is a rotational, already a rotationally symmetric distribution, so we can use the previous theorem to find the Pitman estimator of a rapt Cauchy distribution. And so this delta star is the required expression of the Pitman estimator of a rapt Cauchy distribution, and here it is the detailed proof. To prove this, we have used the Cauchy residue theorem of complex analysis. So there's a lot of expressions and lot of algebraic manipulation. I'm not going to detail of this proof due to time constraint. So this is the simulation study. So we have first found the mean direction of a rapt Cauchy distribution, then MLE of the rapt Cauchy distribution. After that, we have found the Pitman estimator of a rapt Cauchy distribution. And after comparing the risk values of these three estimators, we have found the Pitman estimator has a very lowest risk value than other two estimators. So this is the several tabulated risk values for known values of concentration parameters. So from these tables, we can see that Pitman estimator dominates the other two estimators in terms of their risk values. So next we have considered the various tools to measure the robustness properties. So most general tool to measure the robustness property is the influence function. So these influence functions were modified by the Hampel in the year 1968 to show. And the modified tools were norm of influence function, which is known as gross error sensitivity. And an estimator is B robust if its norm of influence function is finite. And then these tools were modified by Cohen and Gupta in the year 1988. The modifications were standardized influence function and standardized gross error sensitivity. And an estimator is delta is B robust if standardized gross error sensitivity is finite. So this is the main theorem of our robustness work, that the directional mean of rapt Cauchy distribution is B robust, but not is B robust at the family of rapt Cauchy distribution. So to prove this, we have considered to prove this, we have shown that the influence function is norm of influence function is taking a finite value. So directional mean can be said that it is B robust, and to prove that that directional mean is not as B robust, we have considered a metric d theta nu, which is given by equation number 27. And after considering this metric, we have found the expression of dispersion measure, which is given by equation number 29, and this is the infinite sum of an expression. And after finding this standard dispersion measure, we have found the standardized influence function, which is the ratio of the influence function and standard dispersion measure. And after some calculation, we can show that this standardized influence function is taking infinite value as parameter is tending to infinity. So we can show that the directional mean is B robust, but it is not SB robust for the family of rapt Cauchy distribution. Next, we have proved that the directional mean is SB robust for the mixture of two rapt Cauchy family with different concentration parameter. To prove this, we have considered a family of mixture family of rapt Cauchy distribution with different concentration parameter. So after taking this family, we have found the influence function of this mixture family of rapt Cauchy distribution, and after finding the influence function, we have taken the dispersion measure of this mixture family.
Can avoid the proof? Yeah.
Okay. So so it can be also inferred that the rapt Cauchy mixture of two rapt Cauchy distribution is mean direction is SB robust. So from this expression of 42, we can see that it is always finite. So the directional mean is SB robust at the family of mixture of two rapt Cauchy distribution. So next we have come to the equivalent measures of dispersion for the family of Cauchy distribution. So these are to prove this we have considered. Actually, this is a pre-existent result of this paper, La and Moret 2011. They have considered two family of distribution tau 1 and tau 2, and they have considered 4 dispersion measures and also proved that S1, S2, S3, S4 are equivalent measures of dispersion for the two family of distribution tau 1 and tau 2. So these are the detailed proof of this measurement. So these are all pre-existing theorems, so I'm not going to the details of these theorems. So lastly, we can say that if there is we have also considered the trimmed mean direction of the Cauchy distribution. Since we previously we have showed that the directional mean is not S-Robust at the family of distribution tau 1. So now we have considered the trimmed mean direction, and it can be also shown that the trimmed mean direction is S-Robust for the family of distribution eta 1 when the measure of dispersion is S4. So this is the detailed proof. So there is so much theoretical concepts.
Yeah, leave the floor. Within 1 or 2 minutes, you can.
Okay, I'm completing. So this is the graphical comparison of 3 measures of dispersion. So we have for higher values of concentration parameter, 3 measures of dispersion are showing the almost same behavior, and for small values of the concentration parameter, kg dispersion, which is given by root over 1 minus rho, it is showing somewhat different behavior than other 2 dispersion measure. So this is the references we have used. So thank you for your concentration.
Okay, thank you. Any questions? If there are any questions, please. Okay, now thank you, Shreyashi. Now let us move on to the next speaker, Fasna K.
Yes, sir.
So I invite Fasna K to deliver the talk. Okay.
Hi, sir.
Yeah. First, you presentation. Yeah.
Am I visible, sir?
Yeah, yes.
Okay.
Yes, come.
Hi, good evening to all. Myself, Fasna K, research scholar under the guidance of Professor Jayakumar, Department of Statistics, University of Calicut. Discrete meta-Cleffler Cauchy distribution, estimation and applications. Outline of the study: introduction, discrete meta-Cleffler Cauchy distribution, properties, parameter estimation, simulation study, application, and conclusion. Introduction. The Cauchy distribution is a continuous probability distribution and is also known as Lorentz distribution. And it is the distribution of the ratio of 2 independent normally distributed random variables with mean 0, and is the member of class of all stable distributions, and it resembles the normal distribution family of curves, and it is a heavy tail distribution, and it has no moments, and so the law of large number doesn't apply, motivates researchers to generalize the Cauchy distribution. There are a number of generalization of Cauchy distribution appeared in the literature. Al-Shawarbe et al. 2013 used beta family studied by Eugen to generate the so-called beta Cauchy distribution, and a generalized Cauchy family of distribution has been studied by Alzate et al. 2016. Marshall and Hawking 1997 introduced a new family of distribution with a survival function is given by equation 1. There are many authors have studied various univariate distributions, say Rustic et al. 2007, Jones et al. 2010, and Cordero and Lamende 2013. Jaikumar and Thomas 2008 propose a generalization of family of Marshall-Hawking distribution is given by equation 2, and Nadraj et al. 2013 introduce a new family of distribution having the survival function equation 3. When theta equal to 1, this family, equation 3, is reduces to Marshall-Hawking family. And Pillai and Jaikumar 1995 introduced the discrete Metcalfe distribution and studies its properties. Shankaran and Jaikumar 2016 introduced truncated discrete Metcalfe distribution. Is given by the survival function in equation 4, and the corresponding distribution function is in equation 5. When in equation 5, when alpha equal to 1, this g of x is reduces to Marshall-Hawking family. When f of x is exponential in the equation 5, the g of x become Marshall-Hawking generalized exponential. When the f of x is variable, g of x reduces to Marshall-Hawking exponentiated variable. Similarly, I propose a new generalization of Cauchy distribution. When f of x is Cauchy, then g of x becomes like this equation 6, and it is known as truncated discrete Metcalfe Cauchy distribution with parameters c, alpha, mu, and theta, where mu is from minus infinity to infinity, c, alpha, and theta are greater than 0, and the corresponding PDF is given by equation 7. This is a PDF plot of DMLC, and this is the corresponding CDF plot. Now the properties, the qth condyle is given by the equation 8, and the corresponding median of DMLC is equation 9, and the mode is the solution of the equation k of x equal to 0, where k of x is given by equation 10. This is the hazard function of the DMLC. Now the tail behavior. We can show that the density function of DMLC is heavy tailed. Similarly, a function f is said to be regularly varying at infinity with index gamma in R for any fixed a greater than 0. Limit x goes to infinity, fax by fx is a to the power gamma. So here the density function of DMLC distribution is a function with the regularly varying tails. This is the proof for the theorem. Now a function f is long-tailed if limit x goes to infinity, fx plus y by fx is 1 for all y greater than 0. Here the DMLC distribution belongs to the class L. Similarly, the function f belongs to the class D of dominated variation of distribution if there exists a greater than 0, limit x goes to infinity, fx by f2x is a for all x greater than 0. Here the DMLC distribution belongs to the class D dominated variation distribution. Now we are considering estimation of parameters, and we use condyle methods and maximal likelihood estimation procedure for estimation. Condyle methods. In the case of condyle least square method, and its modification is here considered, and rejecting extreme order statistics significantly improve the properties of the estimators. Hence, here I suggest the truncated condyle least square method. And it is introduced by Gilchrist and Castillo. And the truncated condyle least square method is rejecting a fixed number of condyles. And equation 13 is the function which is minimizing the equation, like equation 15, the truncated condyle least square method for the DMLC. And the estimators of these parameters are the solution of the equations dou g by dou alpha equal to 0, dou g by dou c equal to 0, dou g by dou mu equal to 0, and dou g by dou theta equal to 0. Here the k is a fixed even number. This is the double simulation study of the DMLC by using truncated condyle least square method. And now maximal likelihood estimation. Here the log likelihood function is given by equation 16 and the corresponding likelihood equations are 17 and 18. Here it is not explicit solution. So we are using NLM package in R programming, and this is the result of simulation study of DMLC distribution. And here also the application. Here I am comparing the our new model to the Cauchy distribution and skew Cauchy distribution, and comparing the AIC value, AICC, BIC. And this is the data set. It is a skinfold data from Weisberg 2005. The parameter estimates and goodness of fit for various models. Here we can see that the DMLC is better compared to Cauchy and skew Cauchy. And this is a fitted PDF plot of our data. And many large data sets exhibit skewness and heavy tail. So we use this distribution to model such heavy tail asymmetric data. And fitting the DMLC model with the real data set indicates the flexibility and capacity of the new distribution. And again, also a large class of distribution can be generated from the symmetric Cauchy distribution as a parent distribution. These are my references.
Okay, thank you. So there is time for some questions.
Okay, sir.
So any participants can ask some questions.
Can we have any other method of estimation here? I mean, apart from the maximum likelihood, any other method has been tried here?
Yes, sir. Percentile methods, just like a condyle method. And I'm trying to estimate.
So actually, you went a little faster. I could not see whether there is a comparison of the performance of these estimators. Whether any comparison of the performance of the estimators has been made of the different methods.
Sir, I'm comparing in a data set.
Okay.
Okay.
Okay. Any other? Okay. There is no question. I thank Vasna.
Okay.
And I invite the next speaker, Sirisha, G. Sirisha. Yeah, she'll be talking on properties of compound lifetime distribution. Second. Okay, over to you.
Good afternoon, sir. Good afternoon, everyone.
Your presentation. Okay.
Good afternoon, everyone. This is Dr. G. Sirisha, Assistant Professor, Department of Statistics, University College of Science, Osmania University. First of all, I would like to thank my supervisor, retired Professor R.J. Ramalinga Swami Garu, for his support and blessings. Now, today I'm going to present a paper on properties of compound Rayleigh lifetime distribution. Hope all of you are able to hear me and the PPT is visible.
Yes, visible, and you could hear.
Properties of compound Rayleigh lifetime distribution 2. This distribution was derived by myself. And before going to the distribution, first we need to know certain aspects of statistical quality control and reliability. Generally, these two are the main statistical techniques which are useful in any industrial practice. SQC, statistical quality control, deals with the maintenance and improvement in the quality of manufactured product. And this manufactured product can be assessed, the quality of this product can be assessed by using a suitable quality characteristic. The quality characteristic again will be a random variable following certain probability law. Likewise, when this produced product is put to use, we measure or we analyze the lifetime or the survival capacity of the product. And this survival capacity or survival analysis will
Excuse me. Chikisha madam, sorry to interrupt you. Can you make the presentation full screen?
Full screen, okay, sir.
Yeah.
Thank you for letting me know.
No. Full screen, full screen.
Yes.
Yes.
Now,
yes.
is it visible, sir?
Yes. Now it is full screen.
Am I audible, sir?
Yeah. You're audible.
Yes, statistical quality control is nothing but it deals with the maintenance and improvement in the quality of the manufactured product. And this quality of manufactured product can be assessed by defining a suitable quality characteristic, which in turn, this quality characteristic to assess, definitely it should be projected in terms of some probability law. Likewise, when this produced product is put to use, we talk about the survival time or survival analysis of this manufactured product. Reliability analysis deals with this survival of manufactured product up to some specified time. This lifetime of the manufactured product is again a random variable, continuous random variable, because we are saying lifetime. Life will always lie between 0 to infinity. So this lifetime will be a positive, the range of lifetime will be between 0 to infinity, or the positive half of the real line. These two are very important aspects on which your industrial production process depends on. And so these two aspects can be viewed as the hardware and software of any manufacturing process. Now, coming to my compound rally lifetime distribution is based on certain assumptions. Now, first of all, I am assuming that my production process is capable of producing better products, meeting the specifications. Means my, according to modified control charts, my production process or my products are within the 6 sigma spread. My process is within the 6 sigma spread. Or I can say the same thing is mathematically given to be as U minus L is greater than 6 sigma. My process is satisfying this condition. U minus L is greater than 6 sigma, where U and L are specification limits. My difference, my U and L specification limit spread is much more when compared to your 6 sigma spread. Implies I can even improve my production process. And this can be done by, according to the manufacturer, this can be done by relaxing certain constraints imposed on one or more of the 3 M's. M in the sense, the skilled manpower, raw material used for the production process, or the machinery, conditioned machinery used for the production process. So some conditions imposed on these aspects should be relaxed. When this relaxation is done, automatically the parameter, the quality, there will be an effect on the quality of the quality of the product. In turn, the quality characteristic. And the quality characteristic is a random variable with some parameters. So when I do some relaxation in my m's, obviously my parameter will get affected. So my parameter, instead of being a constant, now it will be a random variable. For my Rayleigh compound Rayleigh lifetime distribution 2, I have assumed this variation in parameter as triangular distribution. See, when I do any relaxation, when I make any changes in the quality of the characteristic, obviously the parameter or the process mean there will be a variation in the process mean. That variation in the process mean mu should be between mu L and mu U, where mu L and mu U can be obtained in such a way that the process is still capable of producing items that meet the specification limits. And the formulae for mu L and mu U, based on this condition and by using modified control limits, is being given in the coming slides. Now, as the parameter now, instead of being a constant, it is moved to a random variable, triangular distributed random variable. When this product is put to use, the lifetime distribution of such produced product will also change. The original standard lifetime distribution of the product I have assumed to be as Rayleigh distribution. So now with this relaxation in the m's, there will be a change in the parameter. The parameter will be, instead of a constant, it will be a random variable. Obviously, the lifetime distribution will change. That new lifetime model I have called it as compound Rayleigh lifetime distribution 2. Now, what do you mean by compound distributions? Definition. Here, my parameter is a random variable. When this parameter distribution is superimposed on the lifetime model, lifetime distribution, or on T basic model, obviously the new marginal distribution, we call it as compound distribution. This is the definition of compound distribution. The same assumptions by clearly giving the density functions. So first of all, I am assuming that the lifetime capital T of the product, original product, is Rayleigh distributed with the density function given in this form. F of T is T alpha power minus 2 e power minus half into T by alpha whole square, T lying between 0 to infinity and 0 elsewhere. Then the other assumption is based on the quality characteristic. I am calling the quality characteristic as X. And this X is assumed to be normally distributed with mean mu and variance sigma square, where sigma square is known. Now U and L are the upper and lower specification limits. And as I said, our main condition is U minus L should be greater than 6 sigma, so that I can go for producing better products. Now the third assumption is mu is allowed to vary according to triangular distribution in the range mu L to mu U. By using modified control limits, the formula of mu L and mu U can be taken as U minus 3 sigma and L plus 3 sigma, so that these two mu L and mu U satisfy the specification limits. And the greater the shift in mu, the greater the deviation will be there from the process mean mu naught. And obviously the lifetime will decrease. When there is an increase in the shift, the lifetime of the product will decrease, or the expected lifetime of the product will decrease. Now the next assumption is the increase in the absolute deviation of mu from mu naught results in an increase in the reciprocal root 2 by pi 1 by alpha of the expected lifetime. and the same is represented by the relation. So when mu is exactly a constant mu naught, your u, absolute deviation, becomes 0. And c will be your v. V is nothing but c when u becomes 0. And this c will be nothing but root 2 by pi 1 by alpha. The expected lifetime of Rayleigh distribution is 1 by c, or I can say reciprocal of this. I want to compare the new deviation in terms of the expected lifetime of the original Rayleigh distribution. For that, we have taken this relation. Lemma 1.1, which gives you the probability density function of u. Here, first mu, distribution of mu is triangular. Now I am transforming it to u. So I need to know the distribution of u. Then this u I am transforming in terms of v. I need to know the distribution of v. Then I should know the distribution of joint distribution of v and t. Finally, the marginal of t. So first, the distribution of u by using distribution of mu. That is given to be as g star of u is equal to 2 into delta minus u into delta power minus 2, where u lies between 0 to delta and 0 elsewhere. Based on assumption 1.3, that is nothing but the distribution density of mu, triangular density. This is according to triangular distribution. The density of mu is framed, and mu naught, where mu naught is 1 by 2 mu u plus mu l, and delta is 1 by 2 mu u minus mu l. Triangular distribution around mu naught. The triangular distribution is symmetric around the mid value mu naught. So obviously mu minus mu naught in the range minus delta to delta, when you take the absolute difference, it will look like a folded triangular distribution in the range 0 to delta. Because I am taking modulus, absolute value, it will represent as a folded triangular distribution. Now when I just simplify this density by changing the variable, writing u in terms of mu, you will be able to get this density. Theorem 1.1, the distribution of the lifetime capital T based on the previous assumptions. As I said, I have obtained the distribution of u. Now I need to get the distribution of v, and thereafter the joint of v and t, and finally t. So in this lemma, I have obtained the distribution of u. Next theorem, I will be obtaining the density of t. To get the density of t, the density of t, f star of t, is given in this form. To get this density, first I need to use this relation, root of 2 by pi 1 by alpha is equal to c plus mu, which is u. And by using this relation and g of u, I can get f1 of v just by changing, writing u in terms of v. U is equal to v minus c by m. If I just make the necessary changes, I will be able to get this density of v.
You have 2 minutes.
Now by using compound distribution concept, yes?
You have 2 minutes. Within 2 minutes.
Yes.
Yeah, 2 minutes you have.
Okay. So from the theory of compound distributions, now I can get the joint distribution of v and t. Then after getting the joint distribution, I should integrate with respect to v. In the range c and c plus m delta, you will be getting this density. The same density can as well be represented in terms of incomplete gamma density. Incomplete gamma density in this form. And this derived f star of t is a proper probability density function. I have checked for the total probability. It is proved to be 1. Then properties of CRLD2, expected value of CRLD2, E star of t is given in this form. Just by using the normal definition, I have got this expected value, that is integral 0 to infinity t into f star of t dt. You will get this expression. Likewise, variance of CRLD we can get by using expected t square minus expected t whole square formula. So V star of t is nothing but expected t square. This expression is nothing but expected t square minus of expected t, this expression whole square. Then distribution function capital F star is nothing but integral 0 to t f star of small f star of x dx. If I just use the formula, you can obtain this distribution function on simplification. I have considered an example from Montgomery book, standard book, on piston rings, manufacturing piston rings. The inside diameter of the rings is the quality characteristic, which I am calling as X, and it is normally distributed with mean mu and variance sigma square. The specification limits are given to be as 75 mm and 73 mm. Mu naught, the target value or the original mean of the quality characteristic, is 74.001. Then sigma is given to be as, obtained to be as, for the given data, sigma is 0.00989 mm. Now I am assuming that u minus L, here the process, if you just impose, substitute these values, you can see that u minus L will be greater than 6 sigma. Means I can use this theoretical aspect which I have derived, and by using the same formula I have obtained mu u, mu L. Mu u is mu u according to this is u minus 3 sigma, the same formula I have used, and mu L is L plus 3 sigma I have used, and delta is mu u minus mu L by 2. I have obtained the values. Now I have just tabulated the expected lifetime values of the new distribution for given different C and F.
Your time is up.
Then I have framed this table. Yes, these are the graphs. Thank you.
Okay. Questions? Any questions? Anyone is having a question, please. Okay, since there are no questions, I thank Shirisha, and I invite the next speaker, the last speaker, Faisal Rahman. Over to you.
Thank you, sir.
Presentation.
Yes, sir.
Yeah.
Sir,
Okay.
I hope my slides are visible and I'm audible.
Yes, visible. You are audible. Slightly louder.
Yes, sir. Thank you,
Yeah,
sir.
yes.
Good evening to one and all present here. My name is Faiza Rahman. I'm MSc Statistics student from Christ Deemed to be University, Bangalore, and I'm carrying a research work on point estimation for the parameters of console distribution under the guidance of Dr. Azharuddin S., Assistant Professor, Department of Statistics, Christ Deemed to be University, Bangalore. Moving on to the introduction, I'll give you a brief introduction on what a console distribution is. So console distribution is a discrete distribution and it was defined and various properties were studied by Console and Shenton in 1975, and later it was modified by Islam and Console in 1990. The probability mass function of console distribution is given by equation 1, and we can see that the PMF of console distribution depends on the two parameter beta and theta, where theta ranges from 0 to 1 and other parameter beta is dependent on the parameter theta. The mean and variance of the console distribution are also the functions of theta and beta and are given in the equation 2 and 3. Moving on, we saw that Famoy in 1997 he obtained this model for console distribution by using Lagrange expansion on the probability generating function of a geometric distribution, and thus it is also called as a generalized geometric distribution. Famoy also studied a few of its properties and applications of console distribution. The properties such as moments, moment generating function, etc. were studied for console distribution, and the applications found that the console distribution has a wide range of applications in a branching process, birth and death process, queuing theory, etc. The console distribution belongs to the family of Lagrangian distribution. Console distribution is considered to be more versatile than other distributions of Lagrangian family. It is by various computer programs, the researchers developed that console distribution is an L-shaped distribution, like a generalized logarithmic series distribution. Moving on to the literature survey, I read this paper titled Generalized Negative Binomial Distribution. This paper generated a generalized negative binomial distribution with an addition parameter beta, where this parameter beta took into consideration the variability in mean and variance. And it was done using Lagrange expansion, and various properties like moments and moment generating function and convolution theorem were proved for the generalized negative binomial distribution with additional parameter beta. The paper titled Use of Lagrange Expansion for Generating a Discrete Generalized Distribution. This paper generated a family of Lagrange distributions using the Lagrange expansion, and its properties were discussed in the paper, like moments and central moments, draw moments, etc., recurrence relation, and few of the double binomial distribution, Borel, Tanel, Heights distribution, etc., were obtained. The paper titled Gita distribution and its property discusses about the Gita distribution, which is also a Lagrange distribution, and its various properties were discussed, and the various estimators, minimum variance unbiased estimators, and so on were discussed. The paper titled Console Distribution as Bunching Model in Traffic Flow. In this paper, the authors derived the model for the console distribution using birth and death process and the branching process. The performance comparison for three different estimators for Nakagami M parameter using Monte Carlo simulation. This paper discusses about M is the parameter for the Nakagami distribution. So Nakagami distribution is a distribution basically which is used to model the multipath faded envelope in wireless channels. So in this paper, they developed three different estimators: inverse, normalized variance, Tolperev, Polyakov, and Lawrence estimators, and they did a comparative study for the same for these estimators, and it was seen that inverse normalized estimator was superior than the other two. This paper on the estimation of Gita distribution and its application by Khurshid Ahmed Mir, it discusses about the point estimators for Gita distribution using three different methods of estimation. Point estimation, that is method of moments, method of maximum likelihood, and Bayes method of estimation. And it was they compared these three methods to check the which one is the more efficient estimator. The distribution, there was this paper written by Khurshid Ahmed Mir in 2011, and this paper discusses about generated size-based console distribution. So size bias console distribution arises in the situation where the units does not have equal chance of getting selected. When there is a weight assigned to them to get selected. So in that those situations, the size bias console distribution was came up. So different properties of this distribution were studied in the paper, and again the comparative study for different point estimation method were done. A note on console and Gita distribution. This was this paper. Paper actually obtained that the Gita distribution and console distribution are particular cases of shifted generalized negative binomial distribution. This paper, Programs in R for Computing Truncated Cauchy Distribution. In this paper, the authors have written three different programs for obtaining 6 quantities like probability density function, mean variance, cumulative distribution function, and random variables for truncated Cauchy distribution. Then the paper titled Parametric Interval Estimation of the Gita Distribution. It generated different types of interval estimators for the for Gita distribution, and the estimators were shortest length confidence interval, unbiased confidence interval, Bayesian confidence interval, etc. And it was shown improved in the paper that shortest length confidence interval was the optimal among all of the other intervals. Then simulation study. This is the simulation study. Here the author obtained the optimal estimators for the population mean using dual auxiliary information and for stratified random sampling, and they proposed this new optimal exponential type estimator. And they used Monte Carlo simulation to validate the result. Moving on to my research work, the results that I have obtained. The first method that I used, my research work is about estimation of parameters for console distribution. So the first method that I took into account was method of moments. I used this method to obtain the estimator for the parameter of console distribution. So this method is basically a point estimation method and was discovered by Carl Pearson. And we proceed in this method by expressing the population moments as the function of parameters and then equating them to the sample moments. And these equations are later solved to get the estimates for the parameters. So the number of equations should be equal to the number of number of parameters to be estimated. And using the equations, so first I equated raw moment to the population, first order raw moment to the first order population moment, and obtained the estimate for the parameter theta, which is given by equation 4. And on the similar lines, the estimator for the parameter beta was obtained as given in equation 5. So we can first obtain, using equation 4, we can obtain theta hat for theta, and then putting that value in the equation 5, we can obtain the estimator for beta using method of moments. Then I obtained the point estimator for the parameters of console distribution using maximum likelihood estimation. So maximum likelihood estimation was introduced by R.A. Fisher, and it is the method of estimating the parameter for the probability distribution by maximizing the likelihood function. And the solution of the equation 6 is if you want to obtain the estimator point MLE for theta, if theta hat is the solution of equation 6, then we say that theta hat is MLE of the theta. Thus, these are the likelihood and log likelihood equations that we obtained given this equation 7 and 8. We obtain on simplifying the log likelihood equation, equating it to 0 and solving it, we get equation 9 and 10. Further, on solving these equation 9 and 10, we would get the maximum likelihood estimate for theta and beta. The next method that I use to estimate the parameter of consult distribution is a Bayesian method of estimation. So far we discussed in both the methods we had took into account the joint density function, joint distribution function. Now in this Bayesian method of estimation, we are taking into account the conditional distribution and g theta, which is the prior distribution of the parameter to be estimated, is assumed. And the Bayesian point estimator for the parameter theta is given by equation 11. This is the general formula for Bayesian point estimator. Since in our case for consult distribution, the parameter theta was ranging from 0 to 1, so we assumed the prior distribution for theta to for the known value of beta to be the beta distribution of first kind. And
okay, you have 1 minute. You
yes,
have 1 minute. Okay.
Oh, okay, sir. Okay, sir. Sir, I'll just wind it up. Yes, sir.
Yeah.
So this equation 12 gives the prior distribution function of theta, and where theta ranges from 0 to 1 and a and b are greater than 0. And the Bayes estimator for the parameter theta of consult distribution is obtained by solving the equation 13. The final estimate is obtained in equation 14. Moving on to the conclusion, as we already discussed that consult distribution has many real life application in many real life situation, but it is not limited to. So branching process, queuing process, stochastic process, and using this method, these are the three methods we used, and we obtained the point estimator, and we can use these estimators formulae to get the estimate for the parameter of consult distribution. These are few of the references that I used. Yes, thank you for your patience.
Yeah, any questions? Questions from participants? If there are no questions, I thank.
Are there any inference studies done here?
Sir, pardon, sir.
Are there any testing problems solved for this?
Sir, I have not done any testing problem, sir, and I did not come across any of the problem that has been studied already, sir.
Okay.
So, inference part is not done.
Yes, sir. No, it's not done, sir.
Okay. Thank you, Faiza.
Thank you, sir.
Okay. So I thank all the speakers. It was a very nice, very timely presentation. Everyone cooperated, especially invited speakers, and everything went on according to the schedule, including the timings. So I'm happy that we have finished a successful session. I thank one and all for participating also, and presenting and participating, and thank you one and all.
Thank you, Professor Pakala, for chairing the session in a nice way, and concluded the session in time. And now, also, I utilize this occasion to extend our gratitude to each one of the speakers and the chair of the session, Professor Pakala, for nicely concluding this session. Now, let us go to the next session.
Okay.
I hope. So 5 minutes, yeah, we can. We are at 6. Okay. Well, let us wait.
I think there is only 2 minutes left, actually.
2 minutes, okay. Yeah.
I think that chairperson has already joined.
Yes. Yes.
Okay.
Good morning and good evening, everybody.
Hi, Professor Rao.
MBR.
Rao, Professor MB Rao. Hello. Yes. Hello. Yeah. Okay.
We'll just give a couple minutes for anybody who's expecting to join at 8:30.
You have 2 minutes left.
Yeah.
Sure.
So, Shailaja, are you working today or taken off?
No, working.
Working.
Yesterday was our holiday, national holiday for Labor Day. Yeah. Yep, it's already September.
Rao sir, you are muted.
Professor, you unmute. Please unmute and speak. Professor is muted. You are.
Dr. Rao, you are muted.
It's not hearing, I think.
Yeah. Sorry.
Professor.
I just click on it later when he speaks.
Hi, Joseph.
Hello.
Oh, can you hear me?
Yeah.
Now we can hear you.
Okay.
Now it is okay.
Turn it on.
Now we can hear.
Something to share.
No.
Raise hand. Present now. Should I click on present? Of course, my talk is at.
Dr. Rao. I'm
Don't
just
worry about that. We will help you in case of
We'll give a brief. Just a second. I'll give a brief introduction, and then we'll have Dr. Babu speak first.
Okay.
So Dr. Babu just chatted that he has some difficulty in opening his camera. So it should be in the panel at the bottom, sir. If not, then
okay. You know, there is an icon here called present now. That's what I should click. When my time comes.
Yes, sir. Yes.
Okay. Now I'm set.
Yes. I know it's great.
Let us wait for Jogesh Babu.
With technology everywhere.
Yeah.
Yeah. So,
Kumar?
Yes, Professor.
I couldn't recognize you.
What, Professor? Hello, Professor.
I couldn't recognize you.
Oh,
yes, sir. Yes, Dr. Babu, we can hear you. Just increase your volume a little bit.
Yeah. We have to wait some more time to take this because of this.
Wow.
I'm still unable to open the camera.
Situation,
So at
the bottom there is a camera. When I clicked it, nothing is happening.
Okay.
Oh,
I don't know.
Professor Babu also joined, isn't it? Let us.
Yes. So he's unable to open his camera.
Okay. In the bottom.
But once you present your slides, let's see if we can see those. As I'm talking, maybe you can also start presenting.
Let me see.
There
is a
red button. Can you see a red button using the camera?
Yeah, red button. That's not opening the camera.
Okay.
When I click it.
So now maybe due to that systems.
Something flashed for a second, sir.
Yeah, it's flashed. I don't know.
There.
Huh? Do you see me?
Yes, and then you're gone.
Jogesh Babu, you are playing hide and seek.
Can you see me? No.
Yeah, you come for a flash of a second and you get out.
What's happening here?
Maybe the bandwidth or
no.
Maybe due to the network issues. If it is network issue, you can rejoin, left hand join. That's better.
Okay, I'll try that then.
Yeah, sometimes it helps to rejoin. I was just about to say that. I see my old buddies, of course, Dr. Balakrishna and TV Ramanathan join.
Yeah,
So
TV has joined just now.
Jyotik Babu.
Now it is okay. Now it is okay, Professor. We can see it. Professor Babu, yeah.
Yeah. Sometimes that helps.
Oh,
Now
Professor
you're
Bala,
muted, so.
Let
So
us
you're
start the
muted.
program. Whether it is
You're
okay
muted.
So you can ask Shailaja. Shailaja, are you ready?
Yes, I am. Yes, I am.
Yes. Satish, then you can go ahead.
Okay. Now we have a special session, in fact, organized by the International Indian Statistical Association through Shailaja Surya Vanshi. Is it correct? She is, in fact, the senior director of a great company, the Merck & Co. Inc., located in New Jersey, USA. She has more than 25 years of experience in the area of research and in the industrial research probably, and both in theoretical side. And she did her PhD under the guidance of our great professor, great giant of our field, Professor C.R. Rao. I'm proud of you. And even though she completed her master's and MPhil programs from University of Pune, I'm very much happy to introduce you, Dr. Shailaja, and I utilize on behalf of ISPS. I invite you to chair this session, and here we have three invited speakers, professors. I hope. Please, Shailaja, please carry over.
Sure. Thank you very much for that kind introduction, Dr. Kumar. So on behalf of the IISA, it is my pleasure to organize this session in honor of my advisor, Professor C.R. Rao, as we celebrate his birth centenary year. May God bless him and all of us with good health during these pandemic times. So a quick plug for the IISA is that it's an association that exists to serve our professional community, and it can do so only with active participation from its members, where your voices are heard and your participation is recognized and appreciated. So if you are not a member of the IISA, please go to the website and discover how you can be one, and be a part of the organization that pays it forward and serves our community in the professional world. So our first speaker today, it's my great honor to introduce Professor Jyotish Babu, who needs really no introduction. He is a giant that spans such difficult fields as astrostatistics and astrophysics, an area that, when he first started working on it, very few statisticians were in that area. So he really pioneered his way through that area for us, and we are very proud of him for doing that. So Professor Babu is the director for the Center for Astrophysics, Astrostatistics, and a distinguished professor of statistics, astronomy, and astrophysics at the Pennsylvania State University. Not only has he been a great collaborator and colleague of Professor C.R. Rao, he and his wife Sudha have a long and deep friendship with Professor and Mrs. Rao and their family. And so without further ado, I will hand over to Professor Babu, who will present his talk to us now. Thank you.
Professor, once again, unmute your mic. Yeah, now it is okay.
Thank you very much, Shailaja, for nice introduction. It is a pleasure to be here to celebrate Professor Rao's 100th birth anniversary, but actually it is 101st birth anniversary. He turned 101 a couple of days ago. I have collaborated on many topics with Professor Rao, including jackknife type of approach to statistical modeling and selection based on co-regular measure of divergence. Goodness of fit test when parameters are estimated in the multivariate setting. This problem was motivated by a problem in X-ray astronomy, consistency of sequential bootstrap, and non-parametric estimation of survival function under depending competing risks, jointly with Professor M.B. Rao and others. But today I shall focus my talk on, let me, how to share the screen. Why is not share the screen?
There is an icon.
Okay,
It's present now.
Yeah, do you see my screen?
Yeah, I see. No, I see your face.
Not yet. Yeah. There is an upward arrow mark at the.
Yeah, I did that. It's not allowing me to. Oh, what's happening? This is upward
There's
arrow. Okay. Then
an upward arrow. You have just to click on that. You have the so that the entire screen can click on the entire screen. Then
okay, I did that. It says
now a pop-up menu comes. Pop-up comes, isn't it?
Yeah, I did. And then,
click on that. Click on that.
Click on the
so that the share button will be active.
Pardon?
Share button. Share is there in the share?
No, there's no share. That's the problem.
So just
entire screen.
Entire screen. You click on entire screen.
And then allow.
Yeah.
It says not.
Then click on that box. A pop-up comes. Is it pop-up?
Yeah, I did that. It's not allowing me to.
Then a small window comes, isn't it?
Yeah, I did. I allowed entire screen.
Yeah.
And then,
so in the pop-up, can you see your slides?
No, I don't see my slides on this.
Oh, okay. Otherwise, maybe you can try with a window also.
Yeah, instead of the entire screen, do that specific window, say, and just like maybe double click. Sometimes
just a click is needed.
Let me try again once more.
Yeah, try again. It's better.
Window, I did that. Then it says meet KUF and entire screen. Which should I? There are two options.
Entire screen.
Entire screen.
Yeah, I did that. And
Professor, first of all, you open your slides.
I did that. I opened my slides.
Okay. Now here in this upward arrow, click on upward arrow.
I did that.
Person now, so that a small pop-up comes.
I did that. Entire screen.
Entire screen. Then another small screen comes up. Comes in from above probably.
Yeah.
And click on that. So that
I did that.
Share will be active.
It says yellow button is blocked.
Professor, whether you are using the Chrome, Google Chrome?
No, I'm using Firefox.
Oh, okay.
Yeah.
Should I use Google Chrome?
This Google Chrome is better, I think so.
Yeah.
Okay, let me go.
If you have any difficulty, you please send to me so that I shall present from here.
Okay. Let me try Google Chrome.
Oh, yeah. If it is there is Google Chrome, this is better.
Yeah. I had to sign in, it says.
Okay.
Okay.
Now you have to drop the other one.
The other.
Correct.
Okay.
Unmute this one.
Now try the same. Unmute, please. Please unmute, Professor. Professor Babu. Oh, yeah. Please unmute. Yeah.
Now.
Okay.
Yes.
And you make the cursor go
And
to
test
cursor.
again. Again, share is blocking.
I think maybe it's our.
Then if you could send your slides to Dr. Satish, he will open it here and you can speak based on that.
Yeah.
Okay.
Do you have my mail ID, Professor? csk@keralauniversity.ac.in.
Just write down in the chat box, Satish.
Okay.
It's in my email to you, sir.
Okay, I shall put it in the chat box. Yeah.
Here set. What's your email address?
Yeah, you just CSK. CSK at Kerala University.
And
.ac.in.
That AC.in.
CSK. Now you can see from the chat box. CSK at Kerala University.ac.in.
Area edu.
AC.in.
AC dot?
Kerala AC.in. IN. I have put it in the chat box. That mail ID put it in the chat box. Just
here is to study, to estimate these rates, both lambda 01 and lambda 10, using discrete time observations.
Chat box, the right side there is a chat box.
Okay.
Chat.
So we have n subjects in our study. And
I hear something else.
Balkrishna, something else is coming.
Yes, sir. Yes.
Yeah.
I will not go into.
Yeah, the other presentation we can hear. I think somebody near, maybe in your room or near to your office.
What about now? Because I was listening to the other talk because there is a time gap now.
Okay.
Because there are 4 parallel sessions going on.
Professor, there's a chat box. Can you see
I saw that. I saw that now.
Okay.
I saw that. I'm sending it right now.
Yeah. That's better.
I just now sent it.
Okay.
Apologies for the delays. And
Professor, now it is okay. We can share it.
Okay. I should share it? No.
I shall share.
Okay,
We shall share from here. Okay, Professor.
Okay, thank you.
Say you just next or previous in that way. Okay. So that we will do the remaining. Professor, can you please check whether it is viewable to you? It is visible?
Not yet.
No, I cannot see. No.
No, not yet, Sadish.
Just a minute. Just a minute.
Now it is coming.
Yeah, now it is.
Okay.
Now it is okay.
Perfect.
Is it
Thank
okay?
you.
Okay, thank you. Thank you very much.
Okay, Professor.
Next, please. Next, please.
Using the maximum likelihood estimation technique.
Next.
And we took the inverse of that, and then that gives us the variance covariance matrix. Rest of that.
Although you need to mute the other meeting, so please.
I think please mute all other speakers and other delegates. Please mute their microphones. Mute.
Dr. P. Venkatesan, please mute your mic.
Yeah.
Shailaja, you may also please mute.
So please.
Okay, thank you very much. So I'm going to focus on one topic, mainly sample quantiles. In one dimension, it's easy to define what's a quantile. But in multivariate population, there is no single way of defining the quantiles. So Professor Rao and I worked on the problem of looking at marginal quantiles and the multivariate distribution in the limit. And when you look at the limit of the distribution of multivariate marginal quantiles, density at a quantile point appear as a nuisance parameter that need to be estimated. I shall also talk about that if time permits. Next, please. Yes, let's recall what's the quantile. Quantile is essentially if f is a continuous and strictly increasing, f inverse is meaningful, and quantile is, let's say 25th quantile is f inverse of 0.25 and so on. When you have a distribution function which has discontinuities or flat, then there's no inverse is not well defined. So here we take inverse to be the smallest value of x such that fx is bigger than or equal to the quantile of interest. Next, please. So similarly, when you have n data points, u1, u2, un, the sample quantile is the npth order statistics, or in other words, Fn inverse of P, where Fn is the empirical distribution function. For example, sample median is simply Fn inverse 1/2. Asymptotic distribution involves nuisance parameter, which is density at the quantile point. So it needs to be estimated. We shall talk about it little later. Next, please. So let's look at the multivariate case. Suppose you have n independent random vectors, k-dimensional, and y1, y2, yk are the corresponding components. look at the marginal distribution Fi. Similarly, we can define ith quantile of ith component, sample point level of ith component by looking at the sampling empirical distribution of the ith order statistics, ith statistics. Next, please. Ith random samples. So the main result is if Fi is continuously differentiable twice in a neighborhood of inverse of a quantile point of interest, then, and if the density at that particular quantile point is positive, then the difference between the sample quantile and population quantile vector when multiplied by square root n converges to a normal distribution, multivariate normal with zero mean vector and dispersion sigma. Next, please. What is sigma here? Sigma turns out to be a very simple positive definite matrix given by the expression given here. Notice that there are few terms here that are of that need to be estimated. They are unknown. For example, sigma ij, that bivariate distribution of I and jth components at the corresponding quantiles, and delta is the density at the ith quantile of the Fi inverse Qi, which is the quantile of the ith component. These two are unknown quantities. First of all, let's look at the estimation of the first term. Next one, please. Next, please. Yeah. The first one can be estimated by empirical version of it. Replace Yj with the empirical distribution of ith component and jth component at the estimated at the quantile points, sample quantiles Qi at Qj. And one can show that this converges to the quantity of interest with probability 1. This is not straightforward. It requires some work using Bahadur's representation of quantiles. Next, please. Next, please. The proofs use the so-called Bahadur representation of sample quantile. In 1966, Professor R.R. Bahadur developed an elegant way to express a sample quantile in terms of empirical distribution function and the density at a population quantile. The result I presented here, result I put down here is the weaker version of Bahadur's representation, which is given by J.K. Ghosh in 1971, and with a very simple proof, straightforward, simple proof. Bahadur's proof is a bit complicated. Here it says that difference between sample quantile and population quantile is approximately minus empirical distribution function at the quantile point minus p divided by density at the quantile point. And the error term when multiplied by square root n goes to 0. So as far as center limit theorem is concerned, we can apply center limit theorem and the error doesn't interfere with the limit distribution. Next, please. The original result of Bahadur is much stronger and it assumes second derivative of f. Of course, it assumes more than what J.K. Ghosh assumed, Professor J.K. Ghosh assumed. Here, they prove almost, Bahadur proves almost sure convergence after multiplying by n to the 3/4, not just n to the 1/2. Much, it goes to 0 at a very faster rate. Next, please. Next, please. To describe marginal quantile process, under those four assumptions I mentioned earlier, which are technical in nature, one can show that the quantile process indexed by the hypercube, k-dimensional hypercube 0, 1, converges to a Gaussian process where individual components are all Brownian bridges. And the covariance function of the corresponding Brownian bridges is given by the quantity below. That is joint distribution of ith and jth components at ith and jth quantities Ts, T and S. Next, please. Now notice that GNQ is same as Vn defined earlier in the single multivariate case multiplied by a diagonal matrix. So as far as multidimensional things are concerned, it's easy to prove, but in order to prove the convergence of the process itself, we require tightness and various other issues. I shall not go into the proofs of those things. These theorems help in developing tests of significance for population medians based on the vector of marginal sample medians. These are similar to what we do in the case of means of multivariate random variables. Next, please. Let's see how we can test for equality of medians of n populations. Suppose you have n k-variate populations and you have sample of size ni from ith population. Let's look at the sample marginal median vectors. And sigma I denote the corresponding estimate of sigma, which I mentioned earlier. Next, please. To test the hypothesis, we look at this statistic, which is similar to what we do in the case of sample means. And we have shown that this is approximately distributed as chi-square with k times n minus 1 degrees of freedom. So we can use this test statistic to test whether all the median vectors are identical or not in the k-dimensional population. Yes. Next, please. As I mentioned earlier, the density at the quantile point appears as a nuisance parameter. Professor Rao and I developed a theory on the rates of convergence for estimators of reciprocal of density at a quantile point. Interestingly, the rates depend only on the number of derivatives of the density rather than the actual values of derivatives of the density, which is the case in the classical definition, classical density estimation. Next, please. The idea is as follows. If U is a random variable with distribution f and second moment is finite, then the density at quantile point is defined as 1 over f at f inverse p. Now, how do we get that? The idea is to use the following. If you look at, essentially we are interested in derivative of f inverse at p. That is, as I mentioned in the last but one line, 1 over h f inverse p plus h minus f inverse p, that goes to f inverse prime p, which is the usual definition of derivative. We use this idea to develop density estimation technique. Next, please. So, instead of looking at a single difference between f inverse p and f inverse p plus h minus f inverse p, we look at weighted averages of these things in a very small neighborhood of f inverse p. And let's look at the corresponding population quantity also. We shall choose it a little later. So if h is a polynomial which has this property that integral of u h u e to the minus u du is 1, and also integral 0 to infinity h u e inverse e to the power minus u du is also 1. As long as that is the case, next please. The theorem says that the difference between the population quantity and sample quantity when multiplied by certain power of n converges to normal distribution with variance given by the quantity below. Now, the whole idea is to estimate 1 over f of f inverse p. Of course, Hn here is not quite that, but if I choose h and eta appropriately, one can show that the difference goes to Hn goes to alpha at a particular rate. Next, please. Now, what are these polynomials that satisfy the property? These are the examples. H1 can be identical equal to 1, or it could be -2 plus 8y plus etc. something. All these satisfy the equations I mentioned earlier, those two equations. Next, please. The convergence rate depends on finding a polynomial Hm of degree m and satisfying the integral equation. That is, it is 1 for j equal to 0 and 1 and 0 elsewhere, so that it kills all the higher derivatives. The construction of such polynomial is surprisingly simple. What we do is we look at m plus 1 by m plus 1 square matrix with ijth entry is I plus j factorial, I and j running from 0 to m. Next, please. So to construct the polynomial, we need to look at the inverse of that function. And one can show that the uj's given here are the quantities that give you the inverse, and hm is summation uj y to the power j. That satisfies all the conditions mentioned there. Next, please. So in this case, if I take eta is 1 over 2m minus 1, we have the result n to the m minus 1 over 2 to the 2m minus 1, which is pretty close to 1/2 when m is large. And dn minus alpha converges to normal distribution with mean 0 and variance sigma square. Next, please. I gave a brief description of some of the results of my collaboration with Professor Rao. I mainly focused on large sample theory for vector of marginal sample quantities and estimation of density at a quantile point. I think I'll stop here. Sorry, I was losing a lot of time because of technical issues at the beginning.
Right. No, thank you very much. I really appreciate that. It will help our other two speakers also. So, are there any questions for Professor Babu?
Yeah. Hello?
Yes.
Hello. You have mentioned about a quantile density function estimation at the end. Okay. That there are other techniques by Jones in 1992, which also give some approximation method and give estimation technique. And recently, 2012, the kernel method was employed to estimate the quantile density function. This is so.
Yeah, the problem there is in the estimation. You should know that at least you should know the estimation involves higher order derivatives of the density, whereas this doesn't involve that. It kills all the higher order derivatives. That's the advantage of this method.
Okay. What about you have already mentioned about the this marginal quantile process? Have you come across or studied about the conditional quantile process and other things because of the multivariate case?
No, we haven't done that. This work was done quite some time ago in 1990s. So after that, we haven't really worked on that any longer. It is possible to do that because the same technique works here. Once you have the giant distribution, it should not be too difficult to get the conditional distributions because we know the marginals separately and we know the conditional. So by multiplication rule, you can get the conditional distribution.
Yep. Thank you very much, Dr. Babu. This is like good segue, but also like thank you for the suggestion or possible potential topic of research that your discussion created. So that's good. Thank you for paying it forward. So our next speaker, it's my pleasure to introduce Dr. Arvind Rao. He is an associate professor of biostatistics, computational medicine, bioinformatics, and radiation oncology. He works in the exciting area and a very important area, which is sometimes very promising and dear to most of us as we go through life facing certain diseases, most importantly in the area of cancer bioinformatics research. Dr. Rao has a PhD from University of Michigan at Ann Arbor and has previously done postdoc fellowships at CMU and also at MD Anderson Cancer Research Center. He's also the president of our outreach committee for the IISA and does a lot of important work over there. Very active and very enterprising, so full of promise there. So thank you, Dr. Rao, for presenting, and I'll let you take the stage now, okay? Thank you.
Thank you, Dr. Chiravanshi. Really appreciate the kind introduction. I'm going to try to see if my end of the presentation works. If it works, that's great. If not, I'll send these slides to Dr. Satish Kumar and to you as well. So I'll just check.
Professor, just to try. If it is there is difficulty, we shall present from here. Okay, Prof.
Is it working now?
Shall I present
yes,
it?
It's working.
It's working. Yes. Okay.
It is working. It is working, Prof. Yeah.
Wonderful. Great. Thank you so much for confirming. So first of all, I cannot even begin to state how grateful I am for the kind introduction and for the invitation to speak at this session. Obviously, Dr. Rao's work has impacted a lot of what we do in many, many fields. And I want to show you that even in fields as far as might seem as cancer bioinformatics, there's still a strong imprint of Dr. Rao's work, as you might expect. It's a great body of work in so many interesting directions. So just a great honor to be presenting amongst all of you. Thank you for the invitation. Also, I'll say that the flavor of my talk is going to be quite distinct from the previous talk. It's going to be very applied. So you might actually not see a single equation, and I apologize for that ahead of time, simply because I think the depth of work is that Dr. Rao has produced is applicable in a variety of settings, and so in the applied setting, I was hoping to give you a flavor of what we've been working with. But if there are any questions in the middle, please let me know. And also, if there are any questions, you can also ask in the chat, or Dr. Suryavanshi or Dr. Satish can let me know. So with that, I'll get started. So I'm going to talk a little bit about work in developing the spatial analytics platform to quantify the notion of tumor-immune interactions in cancer biology, and to use that to predict outcomes, for example, survival and disease grade and those kinds of things. And so this is joint work with my students, Shobhashish Barua, Santoshi Krishnan, Morgan Oneka, who previously at Rice University, and now more recently at the University of Michigan, Ann Arbor. So very, very broadly speaking, the focus of our work is to be able to use statistical ideas to combine different kinds of data sets across different subspaces of representation. For example, genomics live in a vector space, histology images that you see in the center live in an image space, so some kind of manifold, so do radiology images. And now we have this kind of data becoming available in the medical domain, and the question becomes, what is the right way to integrate this kind of data for things like predicting patient outcome and those kinds of things? Now, I come from engineering originally, and so if you're an engineer and you do electrical engineering and you do signal estimation, you will obviously encounter the Kremer-Rao bound and the Fisher-Rao metric. So I've been fortunate to see a lot of work there as well. I don't work in that area of science and technology anymore, but we do use principles from those concepts for our work. So the main thing for cancer biology is the promise of this new modality called immunotherapy, and it's very popular these days. It's become the fourth modality. If you consider surgery, chemotherapy, radiation, and now immunotherapy is emerging and has now been the mainstay for cancer treatment for many years now. And this was evidenced by the giving of the Nobel Prize for immunology and immunotherapy in 2018. One aspect I want to mention is that when a patient comes into the clinic and they need to be assessed for their likelihood of responding to immunotherapy, there are many approaches available to be able to assess this. The most common approach that you might have all heard of is an area called genomic profiling, right? So what you could do is you could take somebody's blood, or you could do a biopsy, and you could take some tumor tissue, you could do some biopsy to understand what cells are present in the tumor, and basically quantify how many cells of different kinds are present in the tumor, and use that to make a rational decision about how to treat the patient. That is what you see on the left-hand side. That's basically genomics. The other way is to take the biopsy of tissue, put it on a piece of glass, and then you can use a variety of different stains or different kinds of markers to color different kinds of cells in the tissue. So what you see here, for example, can you see my mouse pointer here on the screen? I hope you can.
Yes, we can.
Great, wonderful, thank you. So you see this tissue piece, and you see that this is a piece of tissue, and these different colors are really the different kinds of cells. So that's a alternative description that you can obtain for the same kind of tissue. And why is this useful? Let me give you the intuition here a little bit. Actually, let me step ahead for a second. So let's consider two scenarios, right? In the left and the right, you have two different pieces of tissue, let's say. I have stained the tumor cells in red and the immune cells in blue. In the left-hand side, which is called a cold tumor, the tumor cells and immune cells hardly interact, right? They are blissfully unaware of each other. They kind of operate independently. Whereas in the case of what is called a hot tumor, the tumor cells and immune cells are very, very nicely mixed and very, very closely linked, right? For example, you can imagine this to be like an ecosystem where you have goats and grass, right? In an ecosystem where the goats and grass are not close to each other, you can imagine that the ecosystem is going to fail very quickly because there is no prey and there is no predator. But in the case of a hot tumor, where you've got the goats and the grass kind of, all mixed, it's an ecosystem that is more likely to sustain because the each one's providing symbiosis for the other. So that's the idea. And so you can see that in both cases, the number of, if I were to use a measurement of how many cells are there, how many blue cells and how many red cells are there, and show a simple bar plot, right? You can see that the plot in both these circumstances is almost the same because the number of cells overall is the same, right? So if you went, my point with this illustration is that if you went with traditional genomic profiling, which simply looks at the number of cells, both these very different scenarios will look exactly the same in gene expression space. What you need really is some kind of spatial statistic that is able to disentangle these two behaviors. So we actually leveraged a family of functions, as you might imagine. There's fundamental work by Ripley on the K function and the G function and those kinds of things, where you quantify the density of the immune cells proximal to a tumor cell at varying distance. So you pick some kind, let's say you pick the tumor cell as an anchor, and then you ask the question, as you increase the distance from a particular red cell, how many blue cells do you find within radius R of the red cell? And so you can plot this as a curve and get like a distribution function. And as you can imagine, when you have a lot of mixing between the red and the blue cells, the curve rises very rapidly. On the other hand, when it is not very, very mixed, the curve rises very, very slow, as you might imagine. So what we are trying to do is leverage this kind of principle to then ask, can we use these measures and related measures as adjuncts in more complicated clinical models, right? So that's the intuition. And to anybody who's been keeping track, Dr. Rao's work in spatial statistics, especially spatial econometrics, goes back many, many years. There's a beautiful paper by Luke Anselin where he acknowledges the impact of Dr. Rao's score test. And this is the best paper, this is the best picture I could find of it So I apologize if there's a better one out there. But Luke's work in econometrics and spatial panel econometrics talks about the impact of Dr. Rao's core test. And even more recently, I think in 2020, basically about a year ago, Dr. Rao's group had a beautiful paper in PNAS, the National Academy of Science Journal, on estimation model selection in general spatial and dynamic panel data models. So again, spatial ideas have been a very big mainstay of Dr. Rao's work, and we've been fortunate to borrow from it in the context of what we do. So coming back to the problem itself, the Ripley's K function and G function let you do a very nice job at being able to discriminate some very distinct scenarios. So here's 3 situations, all from real tissue, by the way, where I've taken the tissue, I've removed all the noise, background noise, and now all I've left you with are a bunch of point patterns where the green point pattern is tumor and the red point pattern is immune cells. And here are 3 situations, right, where visually an expert can indicate that this is the situation where the green and red is heavily mixed. Here it's somewhat moderate, and here there is no mixing at all, right? And remember that this is not as much an exercise in novelty as is an exercise in bringing something from an allied field to the bioinformatics and the medical literature. So I am not going to make any claim of novelty in this work. I'm just going to say that this work has flowered and grown beautifully in the non-medical domain. What we tried to do was bring these into the medical domain so that people who did not know about it could now use it for medical problems. So that's our only role in this particular exercise. So what we did was we basically leveraged the Ripley's K statistic, and we were able to show these curves. And this green curve corresponds to the first picture on high infiltration. The red curve is this middle picture, and this yellow curve is this last picture. So essentially what you see is that the evolution of the curve, right, the G function or the F function, beautifully reflects exactly what you'd expect spatially. This is not a surprise to a spatial statistician, right? It's not intended to be a surprise. But the fact is, a very nice metric has existed in plain sight for many, many years and has never been leveraged for this problem. So we said, why not leverage this statistic and ask how we can use that to understand immune tumor engagement and perhaps offer a more nuanced insight into the mechanism of tumor-immune interaction. So now, why is this important? This is important because, as I told you, for immunotherapy, the traditional line of using abundance-based profiling is failed, right? You can't use this idea. I'm going to go back a little bit just to remind you, right? You can't use this idea to discriminate these 2 spatially distinct settings because the bar plot for abundance of these cells will look exactly the same. So genomics is not going to work. You will need something spatial. And this is a much more of an emerging modality. So you have this kind of approach where we can use images like what I just showed you earlier to be able to build models that can then be used to predict things of clinical interest. So let me show you the intuition. It will be easier to probably go that way. Where is that picture? I'm sorry, I'm going to have to come back. But let me show you the picture because the picture really speaks 1,000 words. Okay, so the picture that I'm talking about is like this, right? This is the complexity of what we are working with. This is a piece of tissue, real tissue, where every single dot you see is a distinct kind of cell, right? So the red cells are probably tumor cells, the blue cells are one kind of immune cell, but it's a very complex picture, as you can imagine, of multiple kinds of cells existing on a piece of tissue. And you want to make sense of this complexity in a spatial manner and use this to boil it down to a number or to some metrics that we can then use in a clinically relevant model, like a multivariate model, perhaps. So why do all this, right? Where was the field before we got into trying to use spatial statistics? And I just want to give you a quick overview of that. So if the intent was to be able to use images to call different kinds of infiltration, the most common tool was having a pathologist look at it, right? And when you have a human observer involved in scoring an image, like the one I described to you, there's all the concomitant problems of inter-observer variability, intra-observer variability between the morning and the evening, before coffee or after coffee. All these things, they do have an impact on the way these things get scored. So we want to use a more, a sort of objective idea coming from computation and from statistics to help reduce such kind of variability, right? As my advisor used to say, computers are not necessarily going to do things right, but at least when they are wrong, they do it consistently, right? So the good thing is computers are reproducibly wrong. That's a very useful thing to have when you can have variability from a human. So the current solution is really people don't even think about spatial statistics. All they do is simply count the number of cells, and I've already told you that counting number of cells in such a kind of situation where the spatial aspects matter is doing a disservice to the data and to the problem itself. So right now, even modern solutions, all they do is simply count stuff, and we try to use aspects of spatial statistics to be able to understand organization of immune cells better. And then because you've got statistics and you've got a computer vision method to be able to assess these different point patterns, you can be a lot more automated and also a lot more objective about how you want to quantify immune inflammation. Now, why is this important? It's important because we want to really bring this to the masses. If you wanted to do this in a place where there was no pathologist available, there was no fancy equipment available or programmer available, how would you be able to do this? And so our eventual intent is to have this entire infrastructure live on the cloud, so anybody can simply upload a slide and obtain a very good assessment of what's happening spatially for their patient. That's our long-term goal. Again, like I said, software solutions don't normally do this, so we wanted to augment existing software with spatial insights. And so really our question is we want to do better than what's in the statistics. And spatial statistics provides a very nice way to be able to do it. Now, what I want to point out is, and I'll show you again a picture in a few slides, is that the good thing about the spatial statistical approach is that it is scalable in a very nice manner to not just pairwise interactions between the red and the green cells, but you can have a blue cell, you can have a purple cell, you can have as many cells as you like, and you can talk about interrogating higher order interactions between these cells using the exact same kind of framework from the repeat K function, right? And even if you look at Dr. Rao's papers, right, all these papers, they provide a very nice recipe for higher order scalability to more interactions. So really, statistics has got the tools already available to be able to look at the complexity in a much more structured sort of manner. And so we can then, once we can do this, we can incorporate features like this into clinical questions of interest. And I'll talk about what I mean. So one clinical question that you might want to ask is, how long is this patient likely to survive given the condition of their disease, right? So it's basically essentially assessing survival likelihood. And so I'll show you how we can actually use the function itself, the K function itself, as either a functional covariate or as a summarizable metric, like the area under the curve, as a number that you can incorporate into these kind of forms. Now we talk about the how. How do we do this? I already showed you the image, so I won't belabor the details, but these are big images, thousands of pixels, and this kind of data is now becoming a lot more prevalent in the literature. So it's good that statistics is already available to handle these problems. Just that once the data starts becoming available through the pipeline and you have volumes of data, it will be helpful to know that such analytical tools exist. All right, so what I've done here is just shown you a picture like this is the original image. I've simply abstracted the background and stuff like that and simply represented it with a more cleaner image. But as I told you, these different colors are different cell types, and each color represents a different kind of cell. So you can now see a single piece of tissue, a lung tissue actually, how much of complexity it has by way of different kinds of cell types. It's almost like looking at an ecosystem and saying there's goats, there is grass, there is hyenas, there is tigers. All these species coexist in a population. How does one think of the cancer ecosystem in the same way as a traditional ecosystem? And the moment you make this mapping between spatial ecology and cancer biology, the entire field of spatial statistics becomes available to you, right? So that's the idea here. So just to give you a sense of how we do this, we just take this data, we use computer vision techniques to call out different cell types, their locations and their identities. So you go from an image to a simple 3-column Excel file, if you like, where the first column is the x coordinate of the center of the cell, The second column is the Y coordinate, and the third column is the kind of cell it is, right? You basically boil down all this complexity of an image to a simple 3-column CSV file. Now, why am I bothering to tell you this? I'm telling you this simply because transferring these images is a big pain. So if you have lots of images and a lot of patients, it's going to be very hard. When you can compress every image into a CSV file, it becomes a lot easier to transport. Just practically speaking, you can abstract the notion of the image into a simple file and not really lose any information. That's very true. So in a few minutes that I've got left, and please let me know about, maybe with a 5-minute warning, how I'm doing. So we've got 4 things that we want to really look at with these spatial pictures of tumor biology. And if I have time, I'll go through all of them. If not, I'll stop sooner. But to give you a sense, I've already talked to you about ecology, and I told you that ecological features of cancer biology have already been under study for a while, right? So people use things like entropy and then different kinds of indices that indicate the complexity of a cancer ecosystem. This has been published for some time now, and there's a lot of good papers already. So this is an illustration of a review in this kind of area. However, the problem tends to be that these single summary metrics do not capture the heterogeneity of what you observe in the entire tissue. It's like saying that the Nile Valley in Africa is the same like the Sahara Desert because they are both in Africa, right? And that's obviously not true. One's got a very different ecology to it because it's near a river, and the other one is a very different ecology because it's a desert. Simply because in Africa doesn't mean that these are equivalent, right? So there's a heterogeneity to the variation in ecology, even in the African continent, given that there is so much variation from place to place. That's exactly the kind of stuff that spatial statistics is very good at. So now to spell out exactly what a G function is to those people that may not know, right? Here are 2 situations. In both cases, you have 1 tumor cell and 3 immune cells. But in the first case, you have these 3 immune cells are arranged in concentric circles away from the tumor cell in this manner. In the other case, those exact same 3 cells are arranged exactly at 20 microns distance from the central tumor cell. And you can see the G function in this case is very pretty. It actually seems to summarize this behavior very nicely. In the case of this context, where you have a radially outward increase of different cells, this thing arises in bumps, right? First at 10, first at 6, then at 12, then at 20, right? In the other case, you have a straight jump at 20 because all 3 cells are located exactly at 20 microns. So this kind of nuance of the organization of the tumor immune cell combination can be told very easily by spatial statistics, and that's exactly what we do. This seems to hold up very well in real data, right? Here are 2 situations, one where there's very little mixing between the tumor immune cells, one where there's a lot more mixing, and you can again see the curve rises much more slowly here compared to. To those that already know this field, this is not at all surprising. But to those that are outside this field, I'm hoping to communicate the impact of what already has been done and what can be leveraged in the clinical world. And as I said to you before earlier, this system is very, very scalable. It can basically be used to look at not just first-order interactions between 2 different kinds of cells, but as many different cells, 3-way interactions, higher-order interactions, whatever you might like. Now, when you use the real data, here's another example, right? Here's an example where let's look at the cyan-colored cells and the yellow-colored cells. In one case, you hardly see any yellow. It's mostly cyan-colored cells. There is no mixing, right? So the AUC, the area under the G function curve, is very, very small. On the other hand, here you see a lot more mixing, a lot more islands of cyan interspersed with yellow. The AUC is much higher. Again, confirming that the area under the curve of the G function is actually able to do a pretty good job with discriminating this kind of spatial behavior. Of course, you can take this even further, and instead of trying to model just the area under the curve, you can look at the entire function and use functional data analysis, functional modeling, and functional covariates. We won't talk about that today. So now let's see how it actually impacts quality of clinical work. So using the area under the curve of the G function, we were able to look at a whole cohort of patients on whom these kinds of images were obtained, and we were able to do a simple Kaplan-Meier kind of work. And indeed, something as simple as this is able to discriminate survival for patients in a very natural manner, lending additional credibility to the fact that this realm of spatial statistics has actual clinical value. The other way, what we did was,
Sorry, Arvind, about 5 minutes.
Sure, absolutely.
Thanks.
Thank you. So another way that you can use this work is to be able to use spatial statistics to grade disease. So remember that not everybody has access to high quality pathologists, right? There are very, very few trained pathologists for each domain of clinical work compared to the amount of people that get sick with these diseases. So having a computational method to objectively classify the grade of disease using spatial statistics is a very useful tool to have. And we're able to do this in pancreatic disease, in breast disease, in lung disease. You already got papers in this space that confirm that these kinds of tools are available and helpful. Also, just to put the argument to rest, we have done a comparison that asks, okay, why bother with all this spatial stuff? Have you observed how the naive situation of simply counting cell types does? And we did that experiment. So if you look only at counts, the area under the curve is about 0.77. It's good, not clinical grade yet. And this is using ecological indices, the AUC drops further, which calls into question the value of such ecological indices in the bigger problem. But as you start adding more and more spatial information, the AUC starts getting better and better. Again, we are nowhere close to where we need to be as far as clinical deployment is concerned. So I can't start selling a tool right now to clinicians to use. But the point I'm trying to make here is that there is value in augmenting previous approaches on simply counting the number of cells with information that is more spatially relevant. As you can imagine, once you build these tools, you can also ask questions like value of information questions. You can ask questions like which specific kind of interactions are more likely to inform prognosis, and that's the kind of stuff that we've been doing. And the bigger question, as I said, coming back to the original problem is, if you have information like genetics and pathology and radiology, can you put them together to understand how the patient is going to evolve along the trajectory of the problem, right? So will the problem get worse, or is there any way of trying to arrest the problem early? These are the questions that clinicians typically grapple with. And so this is the kind of stuff that you want to use these spatial tools to be able to help them. I'll skip these in the interest of time, but I just want to point out that this tool, as you would imagine, is able to look at heterogeneity of the entire area of tissue in a much more nuanced manner than any specific sub area. So we feel that this is a fantastic tool to be able to interrogate what is called tumor heterogeneity. And heterogeneity is a problem where you have this is basically a piece of tumor that came from a mouse, and what you can imagine is a lump of cells where not every cell in this lump behaves in the same way. Right? There's a lot of variation, just like in this continent of Africa, you have an extreme desert on one side and a beautiful river valley on the other side. The same way, the tumor itself can harbor multiple areas of biological behavior. And so to interrogate tumor heterogeneity, that's a very important problem for a lot of clinicians and biologists. So we think that these spatial tools can help them in asking these kinds of questions. So with that, I will quickly come to the end, which is the summary, to say that this is meant to be a flexible and scalable spatial analytics framework that is automated, objective, and uses spatial locations of cells to quantify immune tumor interactions. We believe that these battery of tools permit quantification of spatial proximity. You can use them to incorporate spatial measurements into larger prognostic models for outcome prediction. You can use them to understand the heterogeneity of the tissue and put these all together to get a better understanding of the biology and the clinical picture of the tumor. So why is all this important? As I said before, the amount of tools that are becoming available for spatial biology are exploding as we speak. This is now going to be a lot more routine. So it's good that we have the tools on the spatial statistics side to be able to handle this kind of data. Because when the data starts coming, there will be no time to look around and think too much. We'll just have to get going because people can become quite impatient. So it's good to know that these tools exist. And again, I have to acknowledge the contribution of many wonderful researchers, but Professor Rao's work is illuminating light in that literature that tells us a lot about how to apply spatial statistics and non-parametric ideas for spatial statistics within the context of real-world data, where assumptions in general may not hold true. With that, I'll close. Thank you again to Dr. Satish and to Dr. Shailaja for their kind invitation to speak today. I have to acknowledge my students. They did all the work, Shoptik, Santoshi, Morgan, and Dr. Carstens, and also fantastic collaborators from both University of Texas and the University of Michigan, who helped us think about these biological problems and gave us data to work with. And also funding from CPRIT at Texas, Universities of Michigan and Texas, as well as from the NIH, NCI, NVIDIA, Amazon, and Agile. Thank you again for your time, and I'm happy to take any questions if we have some time.
Okay, thanks very much, Dr. Aravinda Rao. Fascinating talk. So much statistics in it. And I'm working with oncologists too, but they're working on how to kill the tumor cells using some kind of an ablation process.
I see.
They never told me that immune cells are also penetrating the good tumor cells.
Oh, this is a very big problem, and I'm so glad you brought it up. Tumor ablation in the context of immunotherapy is a very, very powerful new modality of science.
Yeah.
It's very fascinating.
Yeah, sure. Thank you very much. Yeah. I enjoyed your talk. Yeah. Bye.
Yes, certainly. I also enjoyed your talk, Arvind. I work in the immuno-oncology area at Merck, and it's really fascinating what immune therapies are now doing, and looking forward to more different approaches and how our statisticians can contribute to that. So thank you very much.
Thank you.
Without further ado, I'm going to quickly introduce Professor M.B. Rao, and he is a statistical historian beyond excellence. And, it's like, I don't know how many of the 28 people who are on this call, or 27 excluding him, don't know him. He's highly popular, and so I'm not going to go too long into introducing him, but he is a professor at the University of Cincinnati in Ohio. Most importantly, my memories of Dr. Rao are his visits to Penn State to work and collaborate very closely with Professor C.R. Rao, as well as his other colleagues, Dr. Shanbag in Sheffield. And really, he is very global in his approach. He has mentored so many people, but just his talks are extremely interesting and so well thought out, and he's like a storyteller. So I'm going to shut up and let him talk now, but he's our last speaker of the day, and I thank you very much, Dr. Rao, for taking this on.
Thanks very much, Shailaja, for inviting me. This is really wonderful, and getting back to all the known faces here. Wonderful. So it's I feel as though I'm in India. Shankaran is also here. Okay. So let me try open up my presentation. It is a little bit of history. Okay. Very light-hearted talk, but I thought the students should know about it. And I'm clicking on present now, and our entire screen or a window. Maybe let me click on window. Okay. Yeah. And then I click on my Word document. Can you see the document? Hello?
No, not yet. Not yet, sir.
Not yet. I can see on my screen. So what I will do, let me minimize this and let me try something else. So present now, I'm clicking on it. Should I talk about your entire screen? Maybe let me click on that.
Yeah.
Okay, I did an entire screen, and I try to find where my talk is located. Okay, let me see. I don't see it here. Oh, let me click on share. Okay.
Yeah.
And let me click on my presentation. Can you see my presentation now?
Yes,
now
we
it is-
can. Thank you.
It is there. Oh,
fine.
Good. Okay, guys. And this is a light-hearted talk, The Wonderful World of Simulations, a tribute to Stanislav Ulam. And also, the statisticians who come into the picture, Fisher and Carl Pearson. And I know Fisher was a mentor of C.R. Rao. And there is something going on currently with respect to Fisher and Carl Pearson. I'm not too happy about it. Okay. So let me, okay. Suppose we talk about what is the integral of 0 to 1 x to the power of 3 dx. Oh, trivial. Now I ask the question, what is the integral of this complicated function between 0 to 1 with respect to dx? X to the power of 2.7 sine x to the power of 1.9 exponential minus x. There is no explicit answer. You cannot find an integrand, okay? You cannot find a function whose derivative is what is inside the integral. So what do? Use a quadrature formula to get an approximate value of the integral. If you are lucky, you might get to know how good the approximation is. My training in numerical mathematics comes handy. Okay. Can probability and statistics help? Can simulations help? Okay. You look at the integrand here. F of x is equal to x to the power of 2.7 sine x to the power of 1.9 exponential minus x for x in the interval 0 to 1 is continuous in the compact interval and therefore bounded and integrable. Then the question is, what is the value of the integral then? Let us see what probability can do for us. Suppose the random variable x has a uniform distribution over the interval 0 to 1. I know its mean is half and the variance is 1 over 12. Very simple density function. And look at a function of x. X has uniform distribution. Look at the function of this random variable, capital X to the power of 2.7 sine x to the power of 1.9 exponential minus x is also a random variable. What is the mean of this random variable? It is precisely the integral I spelled out. So this random variable has mean the integral. I'm struggling to find the value of this integral. And this random variable is a finite variance. Okay, it's not a problem. The expected value of f squared x is also finite. At this stage, we do not know what mu is and what sigma squared is precisely. So let us invoke two pearls of probability theory. Suppose x1, x is a sequence of IID random variables with a common distribution uniform. Then same f, I defined f clearly here, is a function of x. F of x1, f of x is also a sequence of IID random variables with a common mean mu. The one I'm trying to evaluate, the integral and the variance sigma squared. So we have a strong law of large numbers. Take the average of fx1, fx2, fxn, the first n observations divided by n, and the strong law of large number says this average converges to mu almost surely as n tends to infinity. Okay. What do we get out of this? So what I'm saying is simulate the random variable fx a large number of times, calculate the average of the sample, and my estimate of mu is the sample average. So thus we have the value of mu to the best of our sampling. Is simulating the distribution of x difficult? No. You simulate the uniform distribution 0 to 1, which is basic in every statistical software, n times. Let the sample be x1, x2, xn. Then fx1, fx2, fxn is a random sample from the distribution of fx. The problem is solved. You don't need to know precisely what the distribution of f of x is. Okay? You are hanging on to the coattails of the uniform distribution. Okay? So, if n is large, I am giving you an approximation of the integral, the average. How good the approximation is? And another part of probability theory, the central limit theorem. So the entities is a sequence of IID random variables with a common mean mu and a variance sigma squared. And the average minus the mu, the mean, divided by the standard error or the standard deviation of the average converges to normal distribution as n tends to infinity in distribution. So in n is large, this entity is approximately normally distributed to mean 0 and variance 1. And we can write down the large sample 99% confidence interval for the mean mu. So the mean, and this is the percentile, corresponding percentile, and this is the standard deviation of the average. And my mu, the integral, is right in the middle, and these are the bounds, lower bound, upper bound. But I do not know the standard deviation sigma. No problem. Estimate it using the data. Let the estimate be Sn, then the confidence interval is given by this one. Instead, replace sigma by standard deviation. You're done. Okay. So, the two pearls of probability theory helps us to estimate or to get an approximation of the integral under focus. And people are trained in R. You can use, you can get this using R. You simulate 1 million observations from the uniform distribution and calculate f of x. Evaluate each sample value at the function f x, x to the power of 2.7 and so on and so forth. And look at the top 6 observations and look at the mean of this, of 1 million fx's, 0.06149548. This is our estimate of the integral. And you can do the confidence interval. Okay? The lower limit using that formula and the upper limit using that formula. And then what you have here is the lower limit is 0.06129997 and upper limit is 0.06169127. The observed confidence bound is the value of the integral is between 0.0613 and 0.0617. Okay, with a 99% confidence. And the point estimate of that one is this one. The length of the interval is 0.04. 004. Okay. And if you apply numerical mathematics, you use the Newton-Cotes formula, Gaussian quadrature formula, they can also provide a bound for the estimate and by doing work on the function itself. Okay. And you look at the easy integral. I know the integral is 1/4. You simulate x 1 million times and calculate x to the power of 3, just mimicking this function, and find these fx's, 0.25022, the actual value is 0.25. So this is our point estimate of the integral, whose value is 0.25. Okay. And you can find the standard deviation, you can find the lower limit of the confidence interval, 0.249495, and you can find the upper limit of the confidence interval, 2.095. Okay. So what I want to say is, what I'm saying is any complicated integral can be approximated using probability and simulations. That's the thing I wanted to say. So this is the idea promulgated by Stanislav Ulam. Who is he? So when I was a graduate student, 3 books challenged me and some of my classmates. Ulam's book, Collection of Mathematical Problems, published in New York, 1960. And then there is another book Ulam edited, the Scottish book, a collection of problems, a notebook kept at the Scottish Coffee House for the use of this Lwow section, Polish Mathematical Society. Okay. And every week, once a week, all these mathematicians join for a cup of coffee at the Scottish Coffee House and talk about the problems. So somebody jots down the problems in a notebook. He compiled all of them and published it. It's available, this book. And another book that fascinated me when I was a graduate student, Exercises in Theoretical Statistics. I can tell you, we worked out all the problems. There are more than 100, 150 problems. We worked out every one of them. And recently, I got this book, Stanislav Ulam, Adventures of a Mathematician, University of California Press, 1991. Okay. So let me give you a short biography. He was born on April 13, 1909 in Lemberg, Galicia, part of Austro-Hungarian Empire. The modern name of Galicia is Poland. The Polish name of Lemberg is Lwow. Now this particular city is in Ukraine with a name change. And the Scottish Coffee House is also in Ukraine now. So he got his PhD from Polytechnic Institute in the same city where he born and grew up. And his PhD advisor was Kazimierz Kuratowski, a topologist. So at the invitation of John von Neumann, he visited Princeton University in 1936. He had a teaching job at Harvard University from 1939 to 40. And he decided to stay back in the country. And he got a teaching job at the University of Wisconsin from 1940 to 43. And then he became a citizen in 1943. So he wanted to contribute to the war effort of USA. Second World War was raging at that time, and America joined. He joined the Los Alamos laboratory to work on the design of atomic bombs. He joined the lab in 1943. He, along with Edward Teller, were credited with the design of atomic and hydrogen bombs. He was the architect of what's so-called Teller-Ulam designs, which are the basis of all thermonuclear weapons. Ulam recognized that with increased sophistication of a computing machinery, statistical calculations will play a major role in advancing research. And the following is a classical paper espousing such ideas. It is a joint paper with Metropolis and the Monte Carlo method, Journal of American Statistical Association, published in 1949. Okay. He estimated success of a design by large-scale simulations. He named a simulation work as a Monte Carlo method. He named a method as a Monte Carlo method because his uncle frequented Monte Carlo, okay, principality within France for his gambling activities. Okay. He died on March 13, 1984 in Santa Fe, New Mexico. Many of his contributions in ergodic theory are outstanding. I would say he claims to be a physicist as well as a mathematician, but quite a bit of work is also in probability. He and von Neumann were the architects of cellular automata. This is the theorem, so-called antipodal theorem, that fascinated me. You take any continuous function from the spherical surface of any n-dimensional Euclidean space. Okay, a spherical surface with the center at the origin. Okay, there exists a point x on the surface that fx is equal to f of minus x. Okay. Okay. And a consequence of this well-known theorem was the ham sandwich theorem of Steinhaus. Taken a sandwich composed of bread, ham, and cheese, one can find a plane, a knife, which cuts through the sandwich, dividing equally bread, ham, and cheese. The bread comes in 2 equal parts, ham 2 equal parts, and cheese equal parts. It's funny, but this is a very deep mathematical theorem. Okay. What is remembered for designs for thermonuclear weapons and Monte Carlo method? Okay. And of course, when it comes to the simulations, we were doing it. We were doing it for quite some time. And when I was a student, this episode attributed to William Seeley Gossett with a pen name student comes to my mind. Okay. If you have a random sample of size n from a normal distribution, so what is the distribution of the average minus mu divided by sigma over square root of n? Standard normal. What if I replace by standard deviation, sample standard deviation? At that time, people believed it still has a normal distribution, and William Seeley Gossett started doing simulations to try to find the distribution of that entity by simulations. He found that normal distribution is not fitting well. Later, Fisher found the exact distribution of that one. It's a so-called T distribution. So William Seeley Gossett was doing simulations. They were all by hand. He did not have the advantage of the computing power we have now. Okay. Look at a Carl Pearson. It is a gamma function. And Carl Pearson is one of the founders of mathematical statistics. He was the head of the Department of Applied Statistics, University College London. Okay. He is remembered for many things. Pearson's correlation coefficient, the chi-squared statistic there are many quotes attributed to him. Statistic is the grammar of science and many more. So what is the gamma function? So gamma at the number p plus 1 is integral 0 to infinity x to the power of p e to the power of minus x dx. And the integral is finite if p is greater than minus 1. If p is an integer, one can show that very explicitly gamma p plus 1 is equal to p factorial. And there is a nice recurrence relationship between gamma p plus 1 and gamma p. Okay. We all learned in our studies, and the gamma half is equal to square root of pi. What is the value of the gamma function for other values of p? He also talks about the incomplete gamma function. He introduces an argument u, this integral 0 to u of the same function, whole divided by integral 0 to infinity of the same function. This is always a number between 0 and 1. How do you do this? Numerical integration, maybe good approximations of the integrands. So Carl Pearson, 1922, formed a group of people who are entrusted with the job of calculating the gamma function and the incomplete gamma function for a comprehensive range of p and u values. The original is out of print now. The reprint is available. I bought the reprint. It's not that expensive. And the reprint is tables of the incomplete gamma function computed by the staff of the Department of Applied Statistics, University of London, University College, 1922. Actually, this project started much earlier, 1905. And they did some work and then they abandoned the whole thing because the approximations were not good. And again, they revived it in 1922. He gathered about 10 people. And what is your job? Okay. What is your job? Evaluate this integral approximately. Okay. It was published by the Department of Scientific and Industrial Research by His Majesty's Stationery Office. You know, when I was a graduate student at a presidency college, I knew this book. We used this book in our statistics practicals every Wednesday afternoon. Okay? The teacher will give us some statistical work, and we have to use this incomplete gamma function. It's a very bulky book, but the reprint is very slim, and the font size is very, very small. So the book is reprinted from the personal copy of somebody. On one of the pages, it is scribbled stupid. Okay, what it's trying to say is, who would do this kind of work, the stupid work? That's what it's trying to imply. Okay. There is a quotation inside the book. Somebody is commenting it. The old English, a painful work. It is, I will assure you, and more than difficult, wherein what toil hath been taken, as no man thinketh, so no man believeth, but he that hath made the trial. Anthony Wood. So on the body of this quotation, somebody scribbled stupid. Can one undertake such work nowadays? No, we can't do that.
Yeah. So, Dr. Rao, just sorry to interrupt you, but we can wrap up in like 5 minutes if possible. Thank you.
Okay. So I'm done, or so you want me to wind it up now?
Like in 5 minutes.
5 minutes, sure. This will be done, almost done. I'm almost there.
Okay, thank you.
Okay. What do software do? What I'm trying to say is, I'm following Ghulam's ideas. I want to evaluate this integral. Can simulations help us? Well, the integral range is from 0 to infinity. You convert the range to from 0 to 1 and use R. Okay. And 1 million simulations of a uniform distribution, and calculate this integral at every value of the uniform distribution generated, and then to find the mean. That's my estimate. The estimate of the integral, 7.700802. Well, I also provide the confidence interval. Done. And what does R actually give? 7.75669. Okay. Okay. Gamma distribution, the method of movement. Does anyone know about a Pearson's family of density functions? Does anyone use it now? But during my student days at Presidency College, we had to fit a Pearson's curve for given data. It's very painful work. We have only facet desk calculator. The whole afternoon is spent by fitting a Pearsonian curve to the given data. I think that's the end of it. I really wanted to talk something about Fisher as well, and the mentor of C.R. Rao, and something unsavory is happening, and these icons called Pearson and Fisher are being pulled down. This is a very sad thing. What can you do? Because those forces are pretty strong, and they were successful in demeaning Carl Pearson and Fisher. Thank you, guys. I think I'm done.
Okay. Thank you very much, Dr. Rao, and thank you. It really piques my curiosity to find out what's going on. Okay. So I will be searching the internet for that. Yeah. But again, my grateful and humble thanks to everybody for making this a good session, and especially the presenters for coming in and presenting the ideas. Was really refreshing and a nice session, I felt. Thank you very much for everybody's time. If there are any questions for Dr. Rao also, please do so, but I didn't want to take off too much time from our next session, which is another keynote one. Yeah, I think Dr. Kumar.
Just a very simple query. Professor Rao, this is really very interesting actually. I wanted to know whether there are any comparative studies between the numerical method and the simulation. I mean, like you have shown for a few integrals, but are there some bounds or some comparative thing that how much difference is there?
Yeah. Hello?
I do not know any such work actually.
On behalf of the Indian Society for Probability and Statistics, we extend our gratitude to each one of the speakers, Professor Jogesh Babu, Professor Aravind Rao, and Professor MP Rao for their excellent talks, and Professor Dr. Shailaja for chairing this session in a nice way. Give a big clap to each of the speakers and the chair.
Okay.
Please join with the other venue, MCMK2, in the Zoom meet for the keynote talk, which I think started. There's a time for it. Please join her.
Okay. Thank you very much.
Thank you all. Thank you so much for your support.
Bye.
Thank you.
Thank you. Have a nice day.